spit out basically a JSC solution that takes the and then the implementation of that loads up using sourcing words if possible or otherwise.
So yes, Siemens have
do you really have to know, am I pulling out to components or am I pulling out to use this name, use the signature, it's LVM, just
they should run the microphone. If it's not set up on microphone, it's not the airport.
Can you close the door?
I think so, yeah. That was the first question. Yes. Super tough. Would be like in theory, you could spec it in terms of workers.
Okay, let's get started, I think. So welcome everybody to our very first workshop on WebAssembly in ACM setting, I guess. Nice you're all here. So we kind of wanted to stress on the, this workshop should work as a way to show how WebAssembly is, much of WebAssembly is rooted in actually academic work, how close the clinicians are. And this workshop is meant to be a place where both these sides can interact a little bit. So the spectrum of the talks we're going to have is quite wide, from real type theory stuff, some problems and that, and to talks like Thomas' ones, which give you an overview of some of the tooling aspects of WebAssembly ecosystem, and try to have like a full spectrum for you guys. I don't want to talk much. I think Conrad will tell you a little bit about the structure of the day, and then we get started.
Yeah, hello everyone. I'd just like to echo Andreas' thanks to all of you today. Thanks also to the speakers, some of whom have travelled quite well to be here. So general structure of this day is going to be 45-minute slots for a half-hour talk. So we really are trying to encourage people to get into long arguments with the speakers about whatever they care about. And we've tried very broadly speaking to group the talks into some kind of theme such that you might want to talk about both the talks after the second talk. So if people aren't causing a large argument after the first talk, we may move on to the second talk more quickly, and then allow more time for discussion afterwards. So please feel free to ask wide-ranging, open-ended questions, provoke the speaker to rant about whatever their special interest is. And then, at the end of the day, we may break a little early if we end up not using all the time. But we'll always start the session at the timetable time when the next session time rolls around. For the very last session, we're going to have one talk followed by a series of lightning talks from attendees. Currently, we have 3 of those talks registered. So if you have your own slides for WebAssembly from some other talk that you've given, and you'd like to Frankenstein together a last-minute lightning talk, please feel free to do that even at this late point, and I'll just be checking who's registered at the beginning of the last session. And then finally, we're going to end the full program of the workshop with a brief discussion on what people would like to see if we do this again in the future. This year, we've kind of done an oops all invited talks thing to try and draw as many people to the workshop as possible and give a broad overview of what we think are some of the important problems people are thinking about with WebAssembly. But we'd like this to grow into a thing where everyone comes and shares their experience with WebAssembly. So for future workshops, for example, we'd be interested in hearing whether you'd like to do more submission-based talks, things like that. Something to think about for the last session. So without further ado, I'd like to introduce Luca Wagner, one of the co-creators of WebAssembly, who's going to be talking about what is the WebAssembly component and why. You probably don't need this one.
All right. This is all right. This is how it works. Hello, everyone. Yeah, my name is Luke. I work at Fastly, and we're trying to answer the question: what is a WebAssembly component and why? And this is a modified version of a talk I gave last year at WASMCon, which is definitely an industry sort of focus, but hopefully it's like interesting to this group too. So first, before answering, asking what is WebAssembly components, let's start with the question, what is WebAssembly and why? I appreciate most people here already kind of know that, but bear with me for just a second. So, the boilerplate, definition, WebAssembly is a binary instruction format for stacked instruction machines designed to support compilation target programming languages, And I think the operative phrase here is compilation target, meaning that we can take all a variety of source languages, and in addition to all the native instruction sets we can compile to, we can compile to WASM. And then given that WASM, we can send it to a browser, a WASM engine, turn it into whatever actual instruction set that we're running on. And why we do this, we get portability, determinism, if we want it, control flow integrity, and sub-process sandboxing. And so using, what do we do with all these cool superpowers? So just kind of looking at the whole ecosystem, what are the popular use cases? Inside a browser, the two big clusters, that I see are, there's a whole bunch around porting a whole large code base that you've already written, especially this is like the famous way we started with mscripton. Big examples include Unity, AutoCAD, Photoshop, Earth, and Figma. And another emerging class of use cases is finding compute-intensive subtasks and punting them out from JavaScript to WASM. So, big examples being codecs, compression, inference, encryption, and filters. So that's in a browser. But we're also seeing a bunch of emerging use of WASM outside the browser. And trying to cluster these sorts of use cases, one whole cluster is around using WASM as a plugin into some existing physical system you've built. So you already have this whole system already working, and you want to take some of your users' code and put it in there. So the last plugin you'll ever need is a little catchphrase that we've been using, throwing around. So there's the CDN use case, which is what Fastly does. We had a big CDN, and we want to run users' code in our CDN to make the cache way more effective by controlling exactly what the cache key and what goes in when where. So that's what we do with it in Fastly. But also people are using WASM as user-defined functions in databases and in client apps and SaaS apps and Kubernetes sort of plugins and also streams like Kafkas and Red Pandas and such. And another cluster use case is using kind of the novel properties of WASM to explore alternative models of distributed computing around serverless or distributed actors or record and replay durable execution or edge computing, which is also a way to look at what we're doing in Fastly. So this is all a bunch of really cool stuff using WASM's unique powers, really neat things and absolute value or absolute volume. A lot of people doing a lot of stuff, but compared to the size of the overall software ecosystem, this is still kind of niche. It's cool, but we want to see just a ton more WASM. I think a lot of people here would like to see everything by default be WASM. So the question asked is well, what would it take to make WASM more ubiquitous? What big new use cases could we unlock that would make WASM become far more ubiquitous? And I'd like to consider 4. So number 1, today on many kind of compute execution platforms, the client controls their application code, the platform vendor controls of course, their implementation and interface, but they also control the language runtime, and therefore the choice of language that you have when running on this platform. And the platform also controls the SDKs that you use in that language to access the platform. And this is both a lot of work for the platform vendor. Now you have to maintain all these SDKs and worry about all these versions, which is not actually your interest. And clients have a more limited set of choices of what languages they can bring to these platforms. So instead, we could lean into WASM's language neutrality and linkable modules and say, yeah, of course, platform controls their implementation interface, and the client controls their application code, which they'll compile to WASM. But also, the client gets to choose and bring their own language toolchain, which will have a language runtime, which is a WASM module. And we don't want to have to duplicate this into every client app, so let's factor this out and share this via some registry, so we're actually sharing the machine code of this language runtime between all the different applications. And the client also gets to bring a bindings generator, which will take that platform interface and synthesize an SDK for that language, also compiled to WASM. And now the client application is a linkage of all these 3 modules running on this platform. And this is not new. If you look at what people are doing with OpenAPI and gRPC, it's this in an HTTP kind of microservice sort of setting. So it's not new. But in those cases, that's fundamentally going through a network stack. So there's a decent amount of overhead in these existing approaches. So the wins from doing this in WASM is we let the client choose their language. The host does a whole lot less work. We're not forcing network round trips or forcing networking into the situation if we didn't want networking. And we're also giving a new opportunity for emerging languages to go into all these platforms without having to be allowed in by the platforms. So I call this cluster of use cases SDKs for free. Number 2. Today, if I want to reuse code, there's tons of registries with lots of packages in each one, but they're relatively siloed from each other. It's harder to reuse code across these registries. Furthermore, when I build a single application using lots of packages from a single registry, they all kind of exist in the same, share the same global mutable state, which is an opportunity for them to have conflicts and cause bugs. And also they share the same privileges and capabilities for the whole application, which means if an attacker takes over one package upstream and I pull that in transitively in my application, that's, what's called attack code has access to all the capabilities of the application, so they can like steal like my secrets, even if there's no reason for that particular package to have access to that particular capability. So this is like ambient authority. So to address these problems, we could lean into WASM's language neutrality and sandbox support and say, let's have a single registry where it can have packages compiled from all sorts of different languages compiled to WASM. And we put them in an app. Let's put each of these packages, give them their own separate memory and just the capabilities they need, so that way their attacks are somewhat limited in the extent. And the wins from doing this is we get to reuse code from other languages, we can mitigate supply chain attacks, and this helps, again. Very good. All right. And again, we can help emerging languages, because now when you start a fresh language, you have access in your registry to all this code in all these different languages. So call this use case secure polyglot packages. Number 3. Today, if I want to avoid, in software engineering what's called sometimes a big ball of mud architecture, a popular kind of architecture you see a bunch of folks using, sometimes overusing, is microservices, where I put what could have been just different modules in wholly different services, and I have them talk to each other through HTTP, which is like a very big sledgehammer of modularity. They're really quite separate, which achieves that, but at the cost of significant complexity to deploy and manage and operate these things, and a decent amount of runtime overhead. And maybe that's what I want. This is part of how I want to scale independently these services and do all this auto-scaling stuff. But if I don't actually want that independent scalability, this is kind of overkill. So it's like a very popular thing, in popular media, where somebody makes a blog post where they're like, look, just because you need modularity doesn't mean you need to whip out a whole microservices. This is too much. Can we not just go back to monolithic deployments and just be write modular code? And it's yeah, sure. You can definitely do that. You could always have done that. But we are, have them just communicate with function calls. Just ye old, function calls. It's much faster. Avoids a lot of that complexity. But we are now generally limiting ourselves to a single language or language family, depending on the VM. And they're less isolated, because often these module features still have a fair amount of global shared state. So that's a thing I think people, why they go to the microservices. It's just this very hard boundary of we are not sharing anything except of course the database, but that's a different story. So instead we could lean into WASM's language neutrality, sandbox support, and linkable modules, and say let's put our modules, compile them to separate WASM modules, and give them separate linear memories, because we can do that in WASM. And let's have them talk to each other through just function calls, because that's also a thing we can do in WASM. And by doing that, we combine the memory isolation and language choice of a microservice architecture with the efficient cross-module calls of a kind of a modular monolith. So I call this use case modularity without microservices. And lastly, number 4, today if I want to factor out code between different teams, I have a large organization writing tons of code. I have all these different teams, each maintaining their own service, let's say. And there's some shared code that's I just want to factor out and share between all these teams around authorization or RPC or observability. And it's increasingly popular to have a platform engineering team in your organization that kind of maintains this stuff for the benefit of other teams in your organization. There's 2 popular options. The original one is you just develop a library that you embed into each one of these services. And that library often takes care of talking to the network for you. But this is harder to update, because now when you make an update to the shared code, you have to redeploy every individual service. This amount of per language effort if you're using different languages in different services, and it can be a leakier abstraction. You can get around a library somewhat easier. So instead, to avoid this stuff, another approach people use, which is called the sidecar proxy pattern, is you have your service talk through the network stack to the shared code, as a sidecar, sometimes container, and then that shared code then talks to the actual network for you, which works and kind of draws a harder line between them, but it comes at significant measurable overhead. But it's still worth enough that people do this in mass. It's called service meshes. Service meshes. So instead of doing all that, we could say let's lean into WASM's sandbox support and linkable modules. Say we'll have our different teams compile their code to different WASM modules. And then between them, there's this like interface. Sometimes it's called an internal developer platform, which is like the abstraction that all these teams like target that is maintained by the platform engineering team. And when we deploy this WASM module, we will link it with our shared module and have a composite module. And then that two linked modules is what we run on the underlying infrastructure platform, which supplies an actual WASM engine. The important thing is the infrastructure platform didn't really have to know about these higher levels. And this lets us combine the low overhead calls between modules of the kind of embedded shared library with the strong encapsulation between layers of the sidecar proxy approach. And this really starts to matter as soon as you have like multiple of these layers as they stack up, because this example shows two, but it's actually, I think, going to be common to have like multiple of these layers. So, for starters, this business logic, let's say it's targeting POSIX. It's using traditional file system code because it was written a long time ago, or I'm using a library that uses file systems. Like, that's very common. But internal developer platforms just tend not to actually have a file system. They don't give you NFS because like nobody wants that. They have like a key value store or a SQL database. So what do we need? We need a little virtual file system that kind of lets us have that abstraction of a file system in terms of what the actual underlying storage is. And so we can just link that together, deploy that to the internal developer platform, which links that with the original logic, and now we have three modules linked together running. And again, this infrastructure layer doesn't have to care. These are just higher layers. And let's do it one more time, because this internal developer platform in my company, let's say I'm building on some sort of platform as a service or function as a service. And of course, they're going to build their own features as a WASM module, let's say, that's linked to this thing. And now I have four modules linked together. And so you can see as the number of layers grow, you really want that low-cost, strong isolation. So you can you don't want subtle bugs that only show up in certain compositions, because those are going to be impossible to debug. On the other hand, you don't want stuff like, every time I add a layer, everything gets like exponentially slower. And this sounds like maybe pretty theoretical, but this is actually the leading use case that we want in Fastly. This is what we're starting to do now. We're building stuff at this level. We're doing work so we can build our own features as WASM modules that we can rapidly iterate and deploy without worrying about some wacky new feature taking down the whole system. So we want to isolate them to more rapidly develop features. And meanwhile, some of our users are working at this layer. They're building their platforms on top of Fastly. Their users don't know about Fastly. They're just deploying to their platform, which is on top of Fastly. So they're also excited about using components to be able to, again, build these abstractions at reasonable cost. So I call this use case virtual platform layering. So hopefully, some combination of those things are exciting enough that, can cause a lot more WASM usage. So the question is how do we actually do this? And I think fundamentally what we need to do is expand the scope of what we're building from a new compile targets for existing ecosystems where we're comparable to things like x86 or ARM or RISC, to a whole new ecosystem which is built around a new compile target, where instead we're comparable to things like containers, NPM, Nix, Maven, Helm, or Debian. So what makes an ecosystem? I don't have a general answer, but if you just look at containers and say what's the pattern here, and and the things I just listed, you start with a standard-ish distributable formats. You have tools to build one of these things from sources. You have tools to deploy and run them, and tools to share and compose them. So if we take containers as an example, OCI has that standard-ish distributable format for what's an OCI image or container. We have tools like Docker build to build these things, tools like Docker run and Kubernetes to run and deploy these things, and tools like Docker push and Docker compose, share and compose these things. So the natural question is well, we have WASM. It's obviously a standard distributable format. Is that not enough? Can't we just use that? And obviously there's lots of existing WASM compilers and more every year. But the challenge is WASM mostly only supports shared memory linking. So if I have two WASM modules and I want to link them together, pretty much the only effective way, a practical way to do that is for them to share memory today. And WASM GC somewhat improves upon the situation, but it's still shared low-level memory. It's still a very low-level feature, so it doesn't really address the problem either. And plus, lots of languages are just using linear memory. Instead, what we want, and so this is like operating system DLLs or shared objects, which is they're cool, they're useful, but that's not your standard unit of distributable code. People don't sling DLLs and combine them in these sort of ways I'm talking about. They're very fragile. They're fragile, man. So instead what we need is when I have multiple WASM modules and put them together, I want them to be able to maintain their own linear memories and have some way to be able to copy values between them or pass handles to non-copyable resources between them, more like an operating system executable. So we could almost use WASM, but it's just a little too low level, quite intentionally, but it is too low for this purpose. So the next question is, well, POSIX has been around for a while. It's a very popular abstraction level. Can we just take WASM, wrap it in POSIX, and have some sort of WASM executable concept. But let's speed run this because, POSIX executables have been around for a while. Is there an ecosystem of people like distributing POSIX executables in this way? No, because you never just want one. You want a group of executables and some configuration code and then some static assets and a little directory structure. And what's that unit? That's containers. So if we speed run this, we just end up with containers, but WASM's the instruction set, which is like totally fine. Like that's useful. It'll provide value to some people, but it's not going to like unlock just like all these totally new use cases because containers have been around. They exist. Swapping out the instruction set won't change their fundamental physics. So we need something new is our opinion. Something, of course, that it reuses existing WASM compilers, and that's something we're proposing is called a component. So finally, getting to the title of the talk, what is a component? So in one sentence, component is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module, which is like a super loaded sentence. So let me break that down word by word, going backwards. So I'll start by saying, so a component is a module by having imports, internal definitions, and exports. That's what it is at a 10,000-foot view, just like WASM. And imports are, I could import like functions, like this log function or this get function. And in general, imports are how we capture the I/O performed, the effects, and implementation dependencies, instead of having a fixed set of syscalls or a runtime global namespace. Internal definitions, these are just WASM modules that have like the meat of the actual code. This is just WASM modules with, and this is 99% of the bytes. And these WASM modules can call these imported functions. And components can also nest other components, so they're recursive by nature. And lastly, exports just, export imports and internal definitions, again, just like WASM. And exports are meant to capture host events and triggers and how generally client code calls into this component. Again, just like WASM. But instead of having a single fixed main function, which is kind of the thing everyone kind of gravitates towards naturally, which is sort of like saying everyone has exactly one export and has this fixed signature. Importantly, all interaction with the outside world goes through these component-level imports and exports. There's not some sort of side door where the WASM gets to reach out and talk to WASM and other components or the system. It all is going through imports and exports, which means if you want to summarize it, if you would say, viewing it as a black box, which its type, all you need to summarize it are what are the imports, names and types, and exports, names and types. And that's it. That's the entire, description of a component from the outside. And all you need to know to understand its interaction with the outside world. And this concept's very important. So in WIT, which is an IDL that we're building for the component model, we have a first-class concept for defining these things. And in theory, it's just a component type. But people tend to get confused if you say type in all these contexts, if you're not like inherently a typey person. So we were calling them profiles for a while, but now that term's taken for WASM. So we now call them worlds. So world is just like a synonym for type, but it's like the world you run in, which is nice. It's nice to say. So it's just a component type, and it defines the contract between guests and hosts, that are defining and running components. So a guest components target a world and when you target a world, you get to call the imports and implement the exports. And host runtimes duly, of course, support the world. They can by implementing the imports and calling the exports. And here, this example, I'm just importing only functions. We can also import groups of things, functions and abstract types, with an interface. So here I have a file system interface that I can import, or an HTTP handler interface that I can export. And then once I have interfaces, I can name them, give them standardized names, so that when we mean the same thing, we can say the same thing and then share code and actually achieve interoperability. So this is now, we can recontextualize WASI. Originally, WASI was just this fixed set of host calls. It's like, this is what the host gives you, exactly this set, monolithic. With this with the component model and this concept of interface, we can say WASI's job is to define a bunch of common interfaces for use in various combinations by many worlds. There's not one fixed WASI world. There's a collection of interfaces, and any particular component can import and export some subset of them, and any particular host can provide and call some subset of them. So we're trying to have multiple worlds here, because that's just going to recognize the heterogeneity of the overall compute ecosystem that WASM's being used in. There's not just one fixed world that everyone's running in. And if you try to do it, it just becomes very dynamically typed, because you can't really say anything, and everyone just hacks everything through modules, and it's like, it's a dev file. It's like, okay, sure, everything's a dev file. So we don't want to do that. So that's what it means for components to be a module. What does it mean to be a compositional module? Aren't all modules compositional? Isn't that what they are? Not really. And this is like a subtle thing where people abuse this term a lot, but just to hand wave at it, I think we need fundamentally two things to be able to do things. One, we want to be able to compose components together and still produce a components. That is to say, components are closed under composition. We don't want to compose components and produce some new thing like, a container or a zip or a jar. No, it's still a component, which means you can do this again and again. And this was this key for this virtual platform layering, is we compose, produce a thing, and then compose again. So that's one thing we need to be able to do. And the other is after composition, all the child interactions of the child components with the outside world are mediated by the parent in three ways. So a parent can forward its imports to the children and re-export its children's exports. A parent can link two children together as just an internal detail of the component. Or a parent can have its own core WASM that implements the imports of the child or calls the exports, allowing it to kind of create a whole virtualized world that the child lives in. And because both these adapters on both sides can share the same linear memory, the parent has great power to just like create its own complete virtualized execution environment that the child is running in, which we'll see in the next slide how that's useful. And these can be used in combinations. So I can have a parent that like links two children together, adapts this import, adapts that export, re-exports that thing. So that's fundamentally kind of the primitives that we have. So let's see like how this is actually useful in an example. So in this example, let's say I start with some C code written 20 years ago that like makes a thumbnail, and I want to turn this into an HTTP web service. So I'm going to start by compiling it with WASI SDK, which is a general tool for compiling C, C++, now to components. That will give me a component that's really POSIX shaped, right? This is old C code. It's going to assume there's a file system, and it's going to assume it's called via main. So we're going to get a component that imports and exports those things. But that's not really what I want to run, because I don't really have a file system in a lot of cases, and main's kind of like not great. So what I want is a component that has no imports, and it just exports this like pure function. That give it a stream of input bytes, I'll give you a stream of output bytes. That component is a lot easier to reuse in a lot more contexts. So to perform that wrapping, I'm going to use a tool being developed in the Bytecode Alliance called WASI-Virt. And the whole purpose of this tool is to virtualize WASI file systems and sockets and main in terms of not these things. So in this case, what it'll do is it'll take that incoming stream and store it to an internal virtualized file system, producing a file descriptor that you can read from by reading from the stream. And if you try to write to it, it'll say, no, it's a read-only file. And vice versa for the output stream. And it can then implement the file system using these streams that it's stored and store all these data structures in a linear memory in this parent component. So now I have a component that like is very reusable. Like if I want to thumbnailify a thing, this is the thing to use. So I can publish it to a registry of components, so it can be reused by other folks. So now I want to take this component and I want to turn it into some HTTP API. So I'm going to write, let's say, this in JavaScript. And I can componentize this JavaScript using another Bytecode Alliance tool called componentize.js, and that will make a component that imports this thumbify function. And let's say I want to cache it, so I'm not recomputing the same thumbnail over and over. So I'm going to import a WASI key value cache, which is a interface that has lets you cache stuff in like a Redis or a memcache. And I'm going to export a WASI HTTP handler, which is how I receive a HTTP request and return an HTTP response. So now I have two components, but I want to link them together so I can have one thing I can run. So to do that, I use another Bytecode Alliance tool called WASM Compose. WASM Compose links these two together to make one parent component. And if we say, what world does this parent component target? It's a very minimal world that just imports a cache, which is very widely implementable, and exports an HTTP handler. So I can run this on all wide variety of cloud and edge and other sorts of server stuff. So that is the component I end up with. Very portable sort of component that I can run in production. But now let's say I want to locally test this. I want to run this on my local machine, which let's say doesn't know anything about HTTP or caches. It just knows about a traditional POSIX world because it's like running on my command line. It knows about file systems, sockets, and main. It's a traditional POSIX command view of the world. So to run this deployment components in this local testing scenario, I want to wrap it one more time with WASM Compose, and I'm going to do that by implementing this imported key value cache in terms of the file system, say by using this directory, some particular directory, as the cache. So there will be some mock testing components that was published in a registry that I can reuse. And then I can call into my HTTP handler by having an HTTP server component that speaks sockets, parses the HTTP protocol, and calls into my handler when it parses an HTTP request. So those, again, can be reusable components and as part of like a local testing sort of registry. So with this, now I can test my deployment component exactly in terms of local stuff running on my local machine. And the kind of neat thing to notice about this is we have two totally unrelated implementations of WASI file system. There's the outer one, right, the one that's actually probably talking to the actual file system. But then we have this inner one way back that's been fully virtualized, right? So in a lot of systems, you know, if you have a name, like thing like file system, it's like a global symbol and like a global namespace, and everyone has to mean the same thing. Here, they're just parameters. They're just imports of a component, which, of course, I can link them separately because they're just parameters. But achieving the shift from saying there is no global namespace, there is no global whatever, syscalls, is kind of like the big part of the key that allows us to do these kind of complex compositions. And that's, you know, often what's a pain in practical software development today. So that's kind of an example of what it means to be compositional. And this is, I think, you know, also key to this virtual platform layering, because each layer is going to have its own concept of what does a file system mean at this layer. So what it means to be cross-language, let's say I'm wanting to target this world that imports a log function, exports a run function. From JavaScript, I can just write a JavaScript import to import the import. So I import a log function. And I export a run function. And you know, that's all I have to write in JavaScript. The type I see in the wit is list of string that gets turned into automatically by the bindings generator to a JavaScript array of JavaScript strings. So I can call join on them, makes a string. I pass that out to log. So I can pass this JavaScript file to componentize.js, which will generate a component that targets this world. And I can also do likewise for Python, writing a Python import. Python doesn't have exports, but the bindings generator can say, well, I'm going to look for a world that has the matching name, and it's the methods of this class will be the exports of the world. So that's where I can stick my run function. I can componentize that with another bytecode alliance tool called componentize.py, which will generate a component that targets that world. And lastly, with Rust code, I'll implement traits. You know, I'll implement a run my world trait that has, you know, a function for, you know, the exports of the world, and I can call the imports via a extern crate generated by the bindings generator, so I can call the log function that way. I can componentize that with another bytecode alliance tool called cargo component that builds components in Rust. So here I'm showing, you know, lists and strings, but there's a whole bunch of value types. Characters, numbers, strings, lists, records, tuples, flags, variants, enums, options, and results. And these are all passed by copy between components. But sometimes you don't want to pass by copy. Either it's because it's not copyable or because it's large. So we have what we call resource types, which are really just abstract types that have a very clear concept of lifetime because we don't assume a global GC. And they're passed by handles instead. So just to show an example of what it looks like in my world, I could import buffer, which is a resource type that has these constructor and append functions. And they look like methods, so you're like, oh no, is this object-oriented? No, it's not object-oriented. It's just syntactic sugar. It turns into functions and abstract types, but with annotations that let bindings generators that are in object-oriented languages generate nice bindings. And once I have that type, I can use it in other function signatures. So to target this world, in JavaScript, I could import buffer, and it would just show up as a constructor function. So I could call a new buffer on it, and then call a method, the append method on this object that's wrapping the handle, and then I could return the handle. So that kind of gives like a sample of what it would look like to use these resource types from, say, JavaScript. So that's kind of a sample of the cross-language experience in components. So now let's look at like how does the sandboxing work? How does this work kind of like at a lower level? How does, you know, this work out? So if I have two components, they're going to have disjoint linear memories and tables. That's like the fundamental thing. There's this kind of, we call this the shared nothing model. And so just to work it through an example, let's say we have one component that implements a secret store interface. The secret store interface defines a secret resource type that like hides a secret, although it does allow you to expose it, and have a get function for looking up secrets by name. And then we have another component that imports that secret store interface. So let's say I implement this, the first component in Rust, and I don't have space to show what it would look like, but you're basically going to implement one trait for the secret store interface, and you're going to implement another trait for the secret resource type. And then JavaScript, let's say, can just import the get function, and then say I'm going to get and look up a key to get the secret. That's going to be an object that I can then call expose on. So that's like in this sample, let's see how the like control flow actually works like under the hood. So the call comes in to this run function. So I'm executing run. The engine's going to put that key string into linear memory, let's say at address 4. And now when I want to call get passing this key, I'm going to call get passing the address of the string in memory, which is address 4. But of course, Rust can't see this 4. Like, first of all, I can't see the JavaScript's linear memory, so something needs to happen. So the component model very precisely specifies how this key string will get copied into the Rust memory using the Rust memory's allocator, ultimately putting it some other address in Rust, which is like 8 here. So Rust will get the call to get, getting past the pointer 8 into its own linear memory. So now we're running in the Rust code. Rust code, let's say, makes an HTTP request to the database or the secret store or whatever, getting back the secret, which is, let's say, XYZ at address 1. So now we don't want to just return the string. We want to like wrap it up into a resource. So Rust code will be able to create a resource that encapsulates the address of this string in this resource. So that 1 is the representation of the resource, and now I have a handle of the resource in Rust's table at index 0. So if Rust wants to now return the secret resource to JavaScript, it says, okay, return the handle at index 0, and then the component model will specify that this handle gets moved into the callers table, which is JS here. So now the handle shows up in JS's table at index 0, and JS receives the index 0. So JS can't see that 1 that's hiding inside the resource. All it knows is that it can call the expose method, passing the index of the secret it wants to expose. So hopefully this kind of gives an example of how this is cross-component communication is a whole lot like inter-process communication, right? We're copying values between memories, and we're passing handles kind of like typed file descriptors. But we're using function calls here. We're not switching threads. We're not doing context switches, syscalls, all that stuff. There's no network stack. So it's on the same thread, in the same stack, in the same process, at least if we want it to be. So it's like processes, but lighter weight. Speaking of lightweights, components support the same lightweight execution model as WASM today, which is a part of the big reason why people are choosing WASM in all these outside the browser situations. So today, if you have some WASM and you have an execution platform, like a server execution platform, there's generally 2 phases you can do stuff in, the ahead of time phase and the runtime phase. So in like a server context, you would say the ahead of time phase is the part of the control plane, and the runtime phase is part of the data plane. So when I deploy this WASM, I'll AOT compile it to machine code, and then I'll distribute that machine code over the whole fleet. And now when a request comes in at runtime, the WASM runtime can cheaply create these little instances with fresh memories, all sharing the same machine code. And this is, today how we achieve our sub-process sandboxing and microsecond instantiation times, which is like, really pretty cool. So with components, we have now multiple nested components and modules inside that thing. But the compilation model doesn't really need to change. We just do this upfront fuse step where we take all those things and we fuse it together, synthesize some WASM that does the copying between memories, and we ultimately can make one WASM module using multi-memory. And now we can just flow into the existing pipeline and compile it the same way. The only difference is now the instances have multiple memories inside of them, but it's basically the same. And so importantly, if you're familiar with previous component models that had big runtime services and other sorts of like heavyweightness to them, they're like, it's really not the case. This is like the same as WASM runs today, just more memories. But that's only one way to compile the components. The other way, which is really just an optimization, if you so choose to have it, is if this component is reusing modules or components in a registry, the platform can maintain an internal machine code cache of compiled versions of all these shared modules, so that when you deploy components, it figures out what can I reuse that's already in the cache, and so it can synthesize effectively a little internal linker script that says, combine these different linked blobs of code together to synthesize the components. So at runtime, this ends up looking kind of like DLL-like code sharing, between components, which is a lot good in a multi-tenant, highly multi-tenant situation. So yeah, that's how components can execute in a lightweight fashion like WASM today. Lastly, the standard portability story is, again, roughly the same as WASM. So the component model is being developed as a specification that's layered on top of the WebAssembly core specification, kind of like TCP is layered on top of IP in a sense. WebAssembly core, of course, has a formal spec, reference interpreter, and test suites. And we're working on the same with Lucy Amidon's doing a lot of the heavy lifting on the formal spec, reference interpreter, and we're getting a lot of help and advice from Amal and Andreas on this. So we're working to have something that is just as well defined as WebAssembly core. Of course, WebAssembly is in browsers today and is accessed by the rest of the browsers through the JS API. So we're also proposing to extend the JS API so it can also access in the same way components. Of course, this isn't implemented today. So we have a tool called Jaco. Jaco is like a kind of a general purpose component toolkit, Swiss Army knife thing that's NPM package. It has a transpile command that takes a component, which is a new binary format, and translates it into Core WASM 1.0 and JS glue code that can execute in browsers and Node today. So people are running components today in Node.js just using the polyfill technique, and that's how some people actually do their REPL iteration loop, is using Jaco transpile. So even before, of course, the goal state is browsers implement it natively, but that'll take quite a long time. So, the polyfill works pretty well in the meantime. WASI proposals are now layered on top of the component model, so they can define their interfaces in a language agnostic way in terms of these component model interfaces. And when possible, Jcode Transpile will also offer, and is already starting to offer, different polyfills of various WASI interfaces in terms of web APIs. So, in a nutshell, that's what a component is. And I know we've been talking about this for kind of a long time, that some of y'all have been hearing about, but it's finally becoming real. We're weeks away from stamping the Preview 2 milestone complete. This has been implemented in WASM time and Jcode Transpile, and WASM Edge, which is a totally disjoint WASM engine, is also starting development. Preview 2 covers both the component model and a subset of WASI interfaces. And we're planning to have a vote in the next WASI standard subgroup meeting to say officially, we're not done, but this is Preview 2, and we're not going to change Preview 2 anymore. And the top line goal of this is stability and backwards compatibility, because if you've been following along with this, it's so many different tools all working together, and they're all changing slightly different times. It causes everything to be broken all the time, which frustrates everyone greatly. So we're trying to get out of that state. No, there's Preview 2. By default, that's what tools will emit, and run times will continue to support it, even as we move forward on future iterations. We also have built an automatic conversion that takes Preview 1 core modules and converts them into Preview 2 components. So you can, a whole bunch of existing Preview 1 stuff can just automatically run in Preview 2. And we're committing to build such a tool that goes from Preview 2 to our future iterations. So that way we can kind of migrate code as we make breaking changes. The Preview 2 feature list includes a first wave of languages. In particular, the Bytecode Alliance is working on Rust, JS, Python, Go, and C. A first wave of WASI proposals, namely file system sockets, command line interfaces, and HTTP. Preliminary support for WASI virtualization in the form of this WASI virt tool that I talked about. Preliminary support for component composition with this WASM compose tool. And more recently, this kind of new language that's basically like a linker script that lets you kind of wire up DAGs of instances and have like a lot of fine-grained control of exactly what component gets what, which is pretty useful. And lastly, experimental component registry tooling in the form of WARG and OCI component artifacts. That was last year. That's what we worked on. All last year is getting to this Preview 2 milestone. That's almost done, pretty much done. So this year it's all about improving the concurrency story. It's because Preview 2 does the best it can, but concurrency just ends up being unavoidably gnarly. As in the async interfaces, just to achieve the concurrency we need, like where we have lots of streams going in and out in all the directions, it just ends up making these interfaces like way more complex than you think they should be, and you have to end up writing manual glue code, which is the whole point of this stuff is you don't have to have the manual glue code, you have bindings that are just like usable as is. Also, we have suboptimal streaming performance, and concurrency is not composable in two ways. One, if two components are doing concurrent stuff and one blocks, then they both get blocked. Why? Because they're not in separate threads. We don't want them to be in separate threads. We kind of like that they're on one thread, but we just need to figure out a stack switching story between components. Two, if you virtualize one async interface, you end up having to virtualize them all for subtle reasons. So in Preview 3, basically we want to solve these by just adding a native future and stream types directly to the component model and WITs, which can make things just so much nicer. This can allow us to have ergonomic, language integrated automatic bindings, because futures would bind to promises, streams bind to readable streams, that sort of thing, in JavaScript at least. And efficient IOU ring friendly ABI for these streams, and composable concurrency. In particular, like in Preview 2, for complicated reasons, we have to have two interfaces for HTTP handlers, one for outgoing requests and one for incoming requests, and they fundamentally have different signatures, just for reasons that don't have time to go into, but that's the best we could do. There's two different interfaces. In the transition from 2 to 3, we'll be able to class them down to just one interface that just has the obvious signature. You have a function that takes a request, returns a response. I'm kind of slightly oversimplifying it, but roughly that. And what this means is that a component can import and export the same interface. The imported interface is how you make outgoing HTTP calls. The exported interface is how you receive incoming HTTP requests. And because it's the same interface on both sides, I can now compose two components directly together to achieve what's today called service chaining, where you have multiple services like chaining going through the network stack. Well, we can achieve that just using direct component linking, no network stack, which supports this whole modularity without microservices use case. Yeah. So that's what we're working on this year. If you see what's today in Preview 2 and you're like, ew, well, hopefully give us some time, we're working on that. So in conclusion, a component is an emerging, standard, portable, lightweight, finely sandboxed, cross-language compositional module. We want to use components to grow WASM ecosystem, providing SDKs for free, secure polyglot packages, modularity without microservices, and virtual platform layering. We are just about to release a stable preview 2 developer release for widespread use. And if you're interested, get involved. The component model and WASI specifications are described in their appropriately named repos. There's a Bytecode Alliance meetings repo where you can find lots of open to anyone, not just official Bytecode Alliance members, meetings you can join on the implementation of these things. And there's a Bytecode Alliance Zulip chat that people can ask questions to helpful people on. And that's it. Thank you.
So I have a bunch of questions I could ask you about that, but first, does anyone else have any questions they'd like to ask?
I have a very simple, basic question. I am speaking into the microphone. Can you hear me? Uh-huh. I need to eat the microphone or something. Yeah, so you said when you compose components together, you should get another component. And then you showed these worlds, and you were composing them using interfaces, which seem to be a different thing. What's the difference between an interface and a world?
Interfaces are these things we define as fragments. Components can import and export multiple interfaces. A world describes the totality of a single component's imports or exports.
Did you think about just conflating the two?
In practice, working out like what people want to write when we're standardizing, you want to be able to standardize a thing that's a fragment, and that the usual term people use for that is interface, at least in this context. And in a separate context, you want to talk about classes of hosts and what they provide. And you want the thing when you talk about the totality of what's provided, you want that to be structural, where it's kind of duck typey. It's like, well, I'm going to provide all these interfaces. You don't have to care what world I support explicitly, just that the interfaces you want are provided. And so worlds are kind of structurally typed. Interfaces, the name matters, because we're saying this is the name of this, fragment of functionality. And so it ends up being, in different developer toolings, I guess we're really very much in the space of like providing developer tooling that's like not too surprising or hard for people to use, and interfaces end up serving one role and worlds end up serving just a different sort of role in the developer experience.
Okay, I'm not entirely convinced, but...
Please take your disagreement as long as it needs to in the break and so on. This is why we're here to talk about this. Anyone else have any questions?
So one of the key selling points, of course, is like cross-language, right? So, and this is great. But you also showed that you have all these tools, right? There's a lot of tool chain going on here. So if I was a language vendor, what is the amount of tooling that I would have to develop and provide to plug in my language into this whole ecosystem?
That's a great question. Yeah, it's so there's a lot of stuff you can reuse. Is I guess the point is I think fundamentally your job as a language designer is omit core WASM, kind of like always. When you're talking about leaving your world, your components, you're talking about binding to WIT, so adding a WIT bindgen generator. So WIT bindgen factors out a lot of the common stuff, like parsing the WIT, resolving the types, giving you an internal AST that says, okay, here's the WIT. Bindgen what your specific language bindings for this. So you can add a WIT bindgen bindings generator. There's already a number of generators, and you would just kind of add one more. So that's one thing. And then roughly at the top level, usually your language has like a standard like compiler driver, like cargo component, cargo, or NPM or whatever. Add like a subcommand that has various all-in-one tools for like build me a component, given a target world, and then some source code, invoke the compiler, and then passing in the WITs and generating the bindings, do all the normal compilation like usual, and then we have another reusable tool called WIT component that takes the core WASM, wraps it up into a component with like the right types on the outside, and spits that out. So just a top-level driver to like wire up all these reusable tools together into a single-shot pipeline. But mostly it's like bindings generation and a little bit of, and also registry integration. As component registries become a thing, you'll want, our deal is that if you're using your language's native registry, like NPM or crates, you want to make these component registries look like they are just in your registry, maybe in a little namespace, by bindgenning what the interfaces are in your language as if they were packages in your language. So there's some amount of registry integration you might also want to do to like pull in this component registries by default. So that's another sort of optional thing, but in theory, this reduces a lot the amount of work a language designer has to do in like mapping out the space of OMG, what do I even generate? Like write WASM that runs in a browser, but also not a browser, and like it's just like no, we've kind of said a lot of that's been figured out. Just like do some bind gen for these high-level types.
And the bind gen front end stuff you mentioned that already exists, presumably written in Rust.
Presumably, you presume correctly.
Perhaps not the most pleasant language
actually,
to write a compiler in.
Now there's a tool that says there's an executable. It happens to be implemented in Rust, but you don't have to care about that. That spits out a JSON file that has like all the process stuff that's like a lot closer to the AST. And the Go folks use that so that they do their bind gen in Go.
And the language you currently support from your end, from the Bytecode Alliance?
Yeah,
end?
it's these ones. Yeah, Rust, JS, Python, Go, and C have the most work, but .NET's having a lot of work more recently. I think Kotlin's poking around, has been doing stuff. I forget exactly where they are. And there's a bunch of other languages doing some amount of stuff, but you wouldn't say it's supported. PHP is poked around.
But some of them are like third-party contributions, I guess. And
Yeah, that's right. The Go people are doing a lot of their own stuff right now. Bytecode Alliance is heavily working on Rust, JS, and I think more recently there's been some C work, a little bit of Python work. Anyways,
Hi. Do I understand correctly that you are basically implementing a new type system of a higher level on top of the basic WASM type system? Because I saw some generic types like list of string or stream of string.
That's right. Yeah.
So how is it specified, this type system, and how do you choose to?
Yeah, it's so yeah. These are the value types, and some of those are type constructors like list, and variants and stuff. Yeah, the component model defines a bunch of new AST of types and a binary encoding of them and a type section. It's okay. Like WASM, but just different set of types. In fact, a disjoint set of types. If you look at the binary format, the component defines an outer binary format that's like a container format that has a type section, imports and exports, just like core WASM, but totally different sets of types. And then nested inside the binary, you can have just core modules exactly as defined by current core WASM, just like inline in the byte stream. And so, yeah.
So you specify how the types are represented in memory, but they're going to be represented differently depending on the language, right?
Yeah, I wouldn't say we specify how they're represented in memory. What we specify is during a cross-component function call, there will be parameters and results that have high-level types. What we'll specify is the layout in WASM linear memory that we're going to expect when we're serializing out of your linear memory and copying into the other side's linear memory. So we have what's called the canonical ABI that says, if your target is like a list of string, pass me an I32. Here's exactly what we're going to do and expect it to be laid out in memory. And it's slightly configurable. So, and it could be more configurable over time because you get to specify these options as part of your component implementation detail. So you could say, what string encoding do I want? Well, I want UTF-8, UTF-16, or Latin 1 plus UTF-16. And this is all just an encoding detail that's not observable to the outside world that configures how the spec parses linear memory to produce that abstract value, and the other side then does the opposite to say how it's written into their linear memory. So we don't specify a stable representation that's like persistent in memory. It's more of a copying serialization scheme.
So does the type definition syntax include things like whether the list of string can have strings that are actually shared, like the same value? Do you have a difference between pointer types and?
No, they're always semantically copied. In some cases, only.
Yeah, but a single list of string could share the same substrings, right? Two of the string elements could point to the same string value. Yeah. And the whole thing could still be copied, right?
Yeah, you're right, and that is actually allowed. If you have a list of strings, they can have pointers to the same shared memory, and that will work. It'll be a copy. It won't. They're just values, so you won't know that they're the same. But it's semantically there's no sharing.
Yeah.
But
the sharing will be lost.
It will be lost on the other side. You're right. There's no deduping. Yeah.
So in your example where you're sending a string from JavaScript to Rust, what if the strings are pretty big? Is there a better way of doing it? You have to make a resource then, right? And pass a handle?
Yeah, in the preview 2 timeframe, your choices are copy the whole thing with values or pass a handle and then define an interface. In preview 3, you would pass a stream of char.
And can the copy type include resource handles?
Yeah, they can be nested, so you can have lists of tuples of, we have 2 kinds of handles at the moment, linear owns and borrows, which are scoped to the call. So you can have a list of owned handles to whatever.
Okay, thanks.
We have to move on to our next speaker for now, but please find Luke in the breaks and in future sessions, and he will never stop talking about components, so I promise you.
I promise you.
So next we have Ben Titzer, another co-creator of WebAssembly, who's going to be talking about Wally, the WebAssembly Linux interface. Once I get this working.
Can I have that microphone? I might wander around.
Oh yeah, go for it. Just be careful. Speaking into both at once might cause some problems.
All right, thank you. So I'm going to talk about some work that we've been doing recently on the WebAssembly Linux interface, or Wally.
If you do wonder, you've got to.
Okay, I'm going to try to, I got to figure out some strategy here. So we're going for pronunciation Wally and not like Whaley or Woolly or anything. There's some difference in pronunciation, WASM, WASM, and things like that. We're going with Wally. I'm just decreeing that. So the PhD student here, Arjun Ramesh, super hacker of the highest order, implemented all of this. And another student, Tian Shu, has also worked on this too. And the faculty member that I've been collaborating with is Anthony Rowe. He's in the ECU department at CMU. So I am trying to motivate people to think about WebAssembly as the universal execution format of the future. So my quote goes something like this: I know that Unicode can trigger people because Unicode has got a lot of weird things in it, but just think of this as an analogy that fits in the advantages and not the disadvantages. So WebAssembly will be like Unicode. All the previous character encodings that people had before Unicode, they were all eventually discarded, and we moved forward with one standard. So WebAssembly is going to be that for executable code. So if we look at the core strengths of WebAssembly, Andreas likes to use the term a portable abstraction over hardware, so the instruction set architecture, and that's what WebAssembly, core WebAssembly gives you. It's an open standard, which is great. Anyone can implement it, anyone can use it. It gives you close to native performance, so you can compile low-level languages and low-level code and run pretty close to what you would get on the CPU, and of course, it's language agnostic. It's well specified thanks to efforts of people in the room. It's been formalized and machine checked, so we're pretty sure that this is right. So we've got a level of rigor that's unheard of in the software world. And there are many engines out there. So different domains, including the web, including cloud, and embedded systems have engines now available. There are many application domains for WebAssembly. Eventually, any place where you'd want to run code, I think that you should have WebAssembly as the format for running that code. So obviously, it was born in the web, so there's web applications and libraries. Cloud and edge systems have started to appear, so there's many different cloud platforms and edge platforms and many proposed academic systems, and it seems to be that WebAssembly is emerging as the standard for accepting applications to run, which is great. It's also a subject of PL and VM research. There's probably close to 200 or 300 papers now that use WebAssembly. People have been thinking about the Internet of Things, and I'm not talking about necessarily washing machines, but I'm talking about like medical devices, like something that you would use in a hospital. Those kinds of things, actually, maybe WebAssembly is the executable format that they use for exchanging code. We talked to some industry partners, and so for example, Siemens, the name of this room, is one of the partners in the research center, and they do critical infrastructure stuff. So think about things in power switching grids, things in, I don't know, nuclear power plants and stuff like that. What code do they run? They want to have some systems that actually have some security guarantees. So maybe there's an application domain there. So under this concept of cyber physical systems, so computers interacting with the physical world. So maybe critical infrastructure is somewhat under that, but also things like factory automation. So robots that build cars and build other things, they run code, and those are embedded systems that have been developed since the 80s and 90s, and those are starting to upgrade into the modern world. That also is related to real-time distributed systems. So for example, if you think about a robot that's building a car or building, I don't know, whatever item that you think is interesting, like a guitar, there's robots that build guitars. The control loop, part of that can be run on the actual robot, on the device, and maybe some of it can be run on some software which is located in the factory, so like a mini cloud or like a mini edge system right there. And so that's all real-time distributed control. Augmented reality, virtual reality, these things are all taking off. So The issue is that there's not been a lot of WASM adoption here. People have written papers about this, people have experimented with it, but there's not really like production systems that are using WASM quite yet. And partly it's because there's not a lot of interfaces yet, and the existing software stacks that they have, there's been a lot of investment. So Siemens, for example, might have 100 million lines of code. I just made that number up. That's not, they didn't give me any information on that. But they have like millions of lines of code, and of course they're robots. They're not gonna rewrite them in, I don't know, Ruby, just on a whim. They want to reuse that investment. And of course they have stability requirements too. So when they have a deployment into a factory, this robot system might work for 10 or 20 years. And so they want to be able to have some guarantee that their software is going to keep working in that time frame. So why do we want to build a WebAssembly Linux interface? So this is a picture of Mount Everest. And so, because it's there, right? And that quote actually comes from George Mallory. He was one of the first people to try to summit Mount Everest. He did not succeed. He died in 1924, so 100 years ago. And he was actually very close to the summit. But they found his body in 1999. So maybe don't use this entire analogy. But why are we building a system called interface? And I would say that it's basically inevitable. If you look here, so the system software is down there. It's inevitable. It's the lowest level of abstraction in user space. We've been doing that for half a century. It's pervasive. Basically, every software system is going to have a bottom layer, which has some user space. So there's no way of getting around it, and it's everywhere. It's typically very stable, too. So, system call interface, since everything is built on top of it, it can't really evolve at the same speed as application layer APIs. And also, system call interfaces are designed to be the minimal overhead. So they try to do zero copy as much as possible, and they try to be as close as possible to the performance that you could get if it wasn't there at all. Another great thing is that they're kind of done. They're already specified. There's not a lot of design problems to solve there. Things are already built on top of them, and so they have already solved the problems that they have set out for. Of course, you might talk to someone who works in operating systems and say, no, they're not done, and we're doing new things. And that's true, so there's like new kinds of async I/O interfaces and things like that. But relatively speaking to the kinds of evolution that we see at application layer, these are effectively done. Why did we pick Linux? For the same reason that we pick WebAssembly. It's an open platform. It's pervasive on so many devices. There's probably 100 billion devices in the world that actually run Linux. It's stable too, and it's more stable than most operating systems. So in particular, Linus Torvalds himself has the quote that don't break user space. So the actual ABI for the kernel is so stable that you can take a binary from 1995 and it will run on today's Linux if it's the same CPU. This is also proof of concept. So this is an academic project. We're just building one example to see if this can work. It's good to pick an example that has a wide adoption already. It may be the case that other operating system interfaces follow, so I'm not going to posit that Linux is going to take over the world and everybody must run Linux. And of course, all the WASM engines, or nearly all the WASM engines today, they already run on Linux, mostly because they are written in C or Rust or another language which runs on Linux. So what is it? We're talking about a low-level WASM API. So it's a set of imported functions. It could hopefully fit in the component model in the future. It mostly maps one-to-one with Linux system calls as they are today. And we've done this in a way that preserves the in-memory isolation properties of WASM. So nothing about the system call interface opens you up to some kind of memory vulnerability. So you can use it just like any other WASM API and communicate through linear memory. Key thing is it's not an application sandbox. We are not trying to sandbox the file system or devices or resources or network. When you're running against the WebAssembly Linux interface, you have the same privileges as a native process. And so that means that we're not thinking that you're going to take random code from the internet, which is compiled against the WebAssembly Linux interface, and just run it. That would be a bad idea, because a Wally program is effectively a native program. So it has all the privileges that of a native process do. There is a little bit more than just being a native Linux program, though, of course. You get additional security guarantees. In particular, since WASM is a memory-safe executable platform, you cannot inject code into a WebAssembly program. Like you can't overwrite some buffer and overwrite the stack, right? So a Linux program here that's compiled against Wally is going to be just by design safe from any remote code injection attack. The great thing is that since we've designed it as a one-to-one mapping, it is really easy to implement. In fact, it's mostly just a forwarding from the application to the kernel. Like you almost have no adaptation whatsoever. So it's a pass-through implementation. The entire implementation, we chose to implement it in the WebAssembly micro runtime, 2,000 lines of code. And probably 3/4 of that is just like line by line, many system calls that go directly through. And so the idea is that eventually we will allow WASI APIs to be built in WASM, so their implementation won't be built inside the engine, because WASM will have the capabilities of expressing the low-level things that you need to do to implement WASI. And the idea there is that even though WebAssembly itself gets more capabilities and you can do more things that are potentially more dangerous, the overall system architecture allows us to introduce a layer. And it allows us to run WASM on whole new domains that doesn't run yet. Okay, so this is a bit of an OS review. I'm just gonna kind of make it a little bit more clear what I'm talking about. The way native applications run is that obviously there's this process abstraction here, which is we have some layers here. They cannot invoke the privilege instructions. So when you're running on the CPU, you can only kind of access the things that are in your memory space. The operating system is what gives you the capability to do anything outside of your sort of own little memory space. It's very analogous to WASM, and that's the system calls at the bottom. And that's also the way you communicate with other processes through the API. So on x86-64, it's the syscall instruction. And it's literally like you put the arguments in the registers that you want, and then you invoke the system call instruction, and you go directly into the kernel. And obviously different kernels, they have different system call interfaces, they have different memory layouts, they have different process abstractions and capabilities that they give you, but they all go through the same mechanism at the bottom. And Linux is a Unix, and it's inspired by Unix. It does not implement POSIX exactly how POSIX is specified, so any difference between what POSIX specifies how the semantics of something like shared memory works, that can be papered over by libc. So there's some software at the bottom, which is actually in your executable, which you link against. So one of the first things that we looked at is, actually, this seems like a crazy idea. It seems also like a gargantuan amount of work. It's actually not. It turns out that most applications don't use the entire system call set. There's about 500 system calls on Linux, and if we look at these various things like bash, so that's the actual shell here, memcached and SQLite, they actually, between the three of them together, and this is actually their dynamic frequency, you can see that it's like very much like a power law. They don't use they don't use the entire system call set. Only about 130 covered all the ones here, and we're able to run many things just with that set. That's less than a third of the overall set. And again, I mentioned before, most of them are just passed through, so they're simple implementation. And that means that it's not like a big burden to implement these system calls. Another question is, isn't Linux portable across lots of CPUs and systems? Is it like totally different? Are the system calls totally different? And actually, it's not the case. So of the 500, this is actually 500 total over all of the ISAs. Actually, most ISAs are more around 300, and there's like this core set, which is common. So across, that's ARM64 and RISC-V 64 and x86 64. There's basically this green set, which is the same. And the yellow, and we actually looked at, there's probably 24 or so Linux ISAs that are supported in the kernel source tree. The ones that are really weird are some porting of something like maybe AIX. So IBM did a lot of work to develop portability for AIX applications onto Linux. And so they would introduce like maybe 50 calls which were AIX specific so they could get their applications running. And so maybe on S390 there's a bit more. But typically like the core set here is actually very common. And the small differences here, like between ARM64 and RISC-V, like RISC-V is effectively just they took ARM64 and they added or removed a couple. And it's like combining a few things that are like similar but minor differences. So it's not a big difference. So we can categorize the functionality that's in the system calls, at least the ones that we targeted for Wally. About 40 of them fall into the category of dealing with files, dealing with I/O, and so it's the normal things that you think of: opening paths and reading and writing from socket, from file descriptors and stuff like that. But it's also stuff like statting files or doing I/O control and things like that. So those are like the long tail of things that applications actually do, or at least libraries actually use. But if you don't have those, then these applications don't work right. And thankfully, there's not too many of them. Also, you can manipulate the process's memory address space. So you can protect different regions, you can map different regions. There's actually only a couple of calls there, so mmap in particular. There's lots of flags and things that you can use to mmap and lots of different things you can do with mmap. But we mostly are allowing you to do that in a sandbox way. I'll show that in a minute. And so actually it doesn't take that much additional work. Signals are important because that's an inter-process communication mechanism. There's only like 5 calls. Those are the complicated ones, dealing with signal handlers. We'll talk about that in a minute. But also manipulating scheduling, that happens too. Timers for all kinds of things. And then process control. So we're able to run bash on top of Wally. And so bash is a shell that runs all kinds of different processes. So talking about child and parent processes and sending signals and things like that, there are about 20 calls there. Sockets work, mutexes work too. And then on top of the system call, sort of just listing all the things that you need to do, there's a kind of basic things that are assumed in the Unix process model, like you get arguments and environment, and then you have to deal with threads. So our thread implementation is based on how WASI threads work. And so when we map that onto WASM, it means, for now, an instance per thread. We basically made no modifications to the tool chain. We just reuse what is built into the WASI SDK for threads. And then we can talk about the process model. So Wally applications are effectively going to be a WASM memory with some additional system calls. Well, these processes actually have identifiers. When you're talking to Unix, their PID is really important. You're talking about other processes, those processes' PIDs are important. And like WASM has this superpower where you can locate many processes in the same one. We chose a simple model where the Wally process literally is a native process. So you have a WASM engine, and that WASM engine's PID is your PID. And so you run as if you're sort of that native process. And then for mapping, you have to talk about what does it mean to have shared memory. And we came up with a shared memory model that kind of makes sense. So Luke talked a lot about the component model and mentioned WASI. So WASI is this collection of APIs, which are high level and going to be portable. Wally, you can think of it as a complementary interface to WASI. So if we were looking at, before Wally existed, we had this kind of setup here where you think about a WASI application and it's compiled against WASI APIs. The WASM engine needs to implement at least some of those WASI APIs. Some of them can live compiled into your application and integrated through components. But ultimately, the things that need privilege, the things that talk to the actual operating system, are going to be implemented in the engine. With Wally in the picture, now we actually can move some of that up. So in addition to being able to run unmodified applications that run directly on the engine and use Wally APIs, we can implement that stuff that was previously needed to be privileged and be in the engine, can move up into a library that instead uses Wally. And so then the same unmodified WASI application can just move over, and it doesn't actually see the layers underneath. This happens to be then WASM. And so we'll get some security benefits from that, which we'll see in a minute. Okay, so obviously when you interact with the kernel has got lots of different things that have to deal with memory. So when you're talking about system calls, many of them take like individual scalar arguments, which are just integers. That's no problem. There's no safety issue there. But some of them take structures and various other things. So if you think about like stat, you pass it a data structure which has got like a C struct definition in the man page. Actually, we need to do a copy in and out because we don't want the WASM application to be able to talk about the process memory. And that's actually pretty easy to do. There's effectively a small address translation. So if you're calling one of these Linux system calls that takes anything to do with memory, we'll do a bounds check and make sure that the WASM application's memory is what we pass to the kernel. So that means, for example, like copying the structs, In particular, we had to define one particular ABI for structs, so it's effectively a 32-bit. It looks like a 32-bit system call API from the WASM point of view, but underneath, of course, your kernel might be 64-bit, so you have to copy and adapt them. But the great thing is that we don't do any copying on I/O buffers. So if you do a read or write call and you pass the kernel like a megabyte, you just have to do a bounds check to the WASM memory, and then you drop right into the kernel. So there's a constant overhead, and it's pretty small. So you can do high-performance I/O, no problem. And so, of course, that's so that even though you have these now kernel system call superpowers, you can't actually break the WASM sandboxing model, right? So you don't actually get to see the whole process that you're in. You see this sort of like this virtualized WASM process. And that also means that Wally effectively doesn't need to ever really interpret the arguments to the kernel, because we're not enforcing additional privilege. We really just want to be as thin as possible. It mostly just passes everything to the kernel and just let the kernel do its kernel security thing. And so we have this model where you're effectively the native process. That's not entirely true, though. There are some things that are virtual file systems on Linux that actually do give you superpowers, because the Linux and Unix model is that, yeah, you're a process. You get to do whatever you want with your own memory. There's no such notion of a smaller thing inside of a process. So a thing like proc_mem, so this is a virtual file system where you can actually do things to your own process memory, that needs to be further sandboxed. So you can't just like open up proc_mem self and then go read what the engine memory is. Signals, this is an inter-process communication mechanism, which is in POSIX. So POSIX has all kinds of standard signals, like what happens if you go out of the bounds of your process memory that's mapped, like SIGBUS, you get a SIG_SEG_V, or if you divide by 0, or other things can happen. So they can happen synchronously and asynchronously. And the way this works in POSIX is that you install signal handlers. So there's a SIG action call. Some of that is in user space, and some of that is in the kernel space. And so we implemented effectively stuff in the engine that needs to deal with signal handlers. In particular, if you set a signal handler for SIG_SEG_V, obviously you're not going to get SIG_SEG_V signals that have to do with engine stuff. You get to service signals that have to do with WASM out of bounds memory. So if you access WASM out of bounds memory, we'll deliver a SIG_SEG_V to you for your memory, but not for other. And of course, engines might do other things with SIG_SEG_V or SIGBUS. For example, there are engines that implement like orthogonal persistence for memory, and so those kinds of signals, like they basically read only. They map parts of your WASM memory as read only and to detect changes. So you're not going to see those. But there are some important asynchronous signals too. So something like bash, I mean, it has like forks off child processes, and like you can kill those child processes, and you get signals when those child processes do certain things. And so we have asynchronous signal delivery in Wally, and the way that works is there's some polling. So the engine actually, when it compiles WASM code, there's some checks that will insert into the code. Do I need to service an asynchronous signal for this program? If so, then we'll branch into it. And so there's a little bit of overhead there. We actually measure that. I'll show that later. There's some more ugliness with signal handling. Signal handling is one of the ugliest parts of all of Unix, honestly. So you get this ucontext T, which is effectively the machine state when you trapped, for example. We just didn't implement that. You might want to use that if you're doing something super advanced in it. So I've done plenty with ucontext in my life. So far, we haven't had applications where we need to implement ucontext and give it a machine state. If we want to go further with Wally, we would have to figure out what does ucontext mean in the context of WASM. Is it like your stack frame, operand stack, like frames, all that? So we have to figure out what that means. So far, we didn't have to go there. So there's this thing called the Linux test project, and it is effectively a unit test for the system call interface. And so actually, that was the first thing that we started with, is like, how do we get going? How do we know anything works at all? And so we actually started running the unit test from this Linux test project. We can now pass most of them. I think it's around 80% of them. And the interesting thing about the Linux test project, it's kind of designed for testing a kernel which is probably broken. And so it forks processes to run like one system call, and then to check whether or not that system call works, it actually sets up a shared memory buffer and uses signals. And so all of that actually kind of has to work. So like the signal stuff and shared memory, all that kind of has to work to even get off the ground. And so the driver of that thing actually has to do some pretty advanced things, and the sort of unit test processes kind of have to work. We actually managed to get all that working so that the whole like test harness runs. And of course, I mentioned Bash several times. An interesting thing about Bash is that when you build Bash, it actually compiles little programs and then runs them to configure itself as part of the build process, which is pretty atypical. It's kind of like got autoconf built into it. And so Arjun, he implemented, so there's a thing in Unix where you can set up a command handler, so for a file type, so you can make a file executable. So he set up a handler for .wasm, which would invoke the engine and run them, and before he had actually tried to do Bash. And apparently, since Bash does this, it was just trying to run things that it compiled. So it was actually running some WASM code using the engine to get going, and we didn't even realize that until it finished. So it was like just one of these things where, you know, virtualization, just like amazing technology, right? Okay, memory mapping. So this is pretty much the bread and butter of Unix. It's all about virtual memory system and the file cache buffer, all the kernels. So if you read and take operating systems, implementing virtual memory and implementing the file cache, that's like where all the smartness is, right? So this is super optimized. This is designed like back in the day before they had like networks, they had computers that had processes, and the processes would communicate, and so that was where all of the action was in the operating system world. And so this was designed so that you could do all kinds of things without copying. And that's actually really important, not just for having a multi-process architecture on one computer, but also for talking to devices too. So super fast networks like InfiniBand or 100 gigabit Ethernet, and even GPUs, they memory map devices. So in the hardware itself, and the actual memory buses and subsystems and all the cache hierarchy has to deal with that. And so you really want that to work, because if you want to eventually run on these devices and on these machines and do the sort of things that these robots do, it needs to work. It's actually relatively easy to do that in Wally. Obviously, you can't make pages executable, but you can make pages read-only. You can map devices and all that. And since we mostly just pass that down to the kernel and you sort of memory map into the sandbox WASM memory, that pretty much just works. If you memory map something and you want to put it at a specific address, we of course just translate that to the sandbox address and pass it through to the kernel. If you want to map something and you don't care where it goes, normally the kernel would manage that mapping and put it wherever. And so in Wally, we just append that to the end of your WASM memory. So if you just like memory map this thing, we just grow your memory and put it at the end. So that means that there is some state in the engine that manages these maps. So if you unmap them, then we don't shrink the memory, but we do drop that part. So that has to have a little bit of engine support there. So we do allow all this read-only and read-write mappings and manipulating that. Okay, so you need to modify the toolchain and libc a little bit. We started with musl, so this is also where WASI starts with implementing their libc, and it was a little bit easier to do. So we started with unmodified musl, and we effectively used the same kind of if-defs in C that you do for like a different Unix, and so it fits in as kind of like just a slightly different Unix. And then all the things that in the tool chain for managing the C ABI and stuff like that, and also for managing threads, we make use of that, so we didn't modify that. And again, like this is specifically because we chose not to try to come up with a different system call set, but have a one-to-one system call set, we could just drop in and everything pretty much just worked. So I call that relatively clean. And so we mostly use stock LLVM. There was some minor changes for this. Okay, so what about the overhead? So the big table here, there's three columns here. One is the overhead for a call, so that's the dynamic overhead. And this is actually includes the overhead of measuring the overhead, so like the actual timer calls and stuff like that. So this is like an overestimate of how many nanoseconds it adds. The floor seems to be around 120 nanoseconds. So like a kernel system call might be on the order of tens or 50 nanoseconds, so we add 100 something to that. And the key thing is that some of them have a little bit more overhead than others. In particular, for example, you see mmap 500 nanoseconds. That's because, again, we have to do some in-engine work. We might have to decide, is this some mapping that we're doing? There's some things that we don't allow you to do, so there's some checking that you shouldn't do every mmap call ever. Same for something like pread. That's because there's like stuff that we have to adapt, like one of these structs. So basically, whenever there's engine work, that's when the overhead is more. Otherwise, it's really just go through. And you notice there's one glaring outlier, which is clone. So that's the Linux system call for make me a new lightweight process. That's how Linux threads work. You get a new process which happens to share all of your virtual memory mappings, so it's effectively a process that has all the same memory, and that's how Linux threads work underneath. So in addition to that work, we have this instance per thread model, and so that means the engine actually has to go and make a new copy. So that's effectively all the WAMR overhead for making a new instance. So WAMR is not as optimized as WASM time, so it's not quite as cheap as WASM time. So that's like, let me multiply that out. That is actually milliseconds, so that's like 5 milliseconds. So that's a lot, and hopefully that could get a lot smaller with some of the optimizations that, for example, WASM time does. But notice other things too. So fork works. You can just fork your process. You can exec your process, so you can just like launch another thing. So like, again, think about how bash works. It forks and execs some native executable. You can actually do that in Wally, and so that will work. This lower left-hand corner here is the runtime breakdown of some applications. So this is the overhead, like the sort of intrinsic overhead to one call, and this is like the aggregate overhead. So for Lua, Lua is a language that you mostly spend time running user code in the interpreter, and so correspondingly, you almost never spend time in the kernel. So there's almost no overhead to using Wally. It's like literally 0.1%. If you're running Bash, you spend a lot of time in the kernel, but you don't spend a lot of time going through the adaptation in Wally. So that's only like 1% overhead. SQLite, it's a database, spends a lot of time in the kernel doing lots of page mapping and stuff like that. It's a database, so they do a lot of this copy on write type of stuff. Again, like you're only getting in and out through these small overheads. So there's not a lot of overhead here. So you almost don't measure time in Wally at all. We also measure the overhead of doing a polling for asynchronous signal handling. So that's again to support things like, your window changes or stuff like that. These numbers are probably can be brought down a little bit too. So here we actually modified WAMR's compiler to inject a little bit of code into every loop header, and so that's on the order of like single-digit percentages there. Okay, so when we wrote the Wally paper, so we have a Wally paper on archive, and we were not entirely sure what we should compare it to. And so we had these different ideas. We came up with the idea of like, let's compare it to different virtualization technologies, even though they may be in slightly different categories. In particular, we compared to Docker. So Docker is effectively a container solution where you run processes natively, but then there's like interception of system calls in a similar kind of way. And then we also compared to running on QEMU, which is an emulator. It gives you the portability guarantees. So the idea is that we're comparing the portability guarantees that you might get from doing ISA virtualization a different way and the virtualization of system calls that you get from doing it natively. And the results are kind of interesting. For one, Docker takes a lot more memory than we thought. You can be a little bit smarter about how you build Docker images to get that down, but the default one is actually pretty heavyweight, so it spends a bit more memory overhead. Docker also imposed, so if we look at, I'll break down the results a little bit more. So this is the execution time, so 3 different applications, Bash, Lua, and SQLite. What we see is that, so this is if we make the program do more work, so the native execution time, so increasing the load of an application, and then this is the corresponding execution time on whatever virtualization it is. So this dotted line is like if you ran the native executable, that's 1-to-1. So anything above that is going to be overhead. So if we look at Docker, which is this orange line here, there's some offset. So there's like some startup cost to Docker, even though it mostly traces native execution time for Bash. Obviously, an emulator, ISA emulator, even though QEMU does have a JIT compiler and all that in it, it's actually pretty slow. So that's why this goes up like this. Of course, it has like effectively no startup cost. And so the blue line is actually Wally. And so there's effectively no startup cost because we use WAMR in AOT mode. But there's this like region here, for example, where you actually run better than Docker because you avoid the startup time. And similarly too, like there's always this region where Wally is kind of better. We're not really selling this as a performance thing. It's more of a a layering thing, but this is, part of our due diligence as engineers to figure out what the overheads are. Are there questions about those performance results? So there's like lots of things going on there. Okay, so that's like the technical details. So you can kind of see it's quite predictable when you start with the idea of making it one-to-one system calls. You crank through the work of it and you measure it. What is actually the future of this afterwards? What are the benefits and opportunities and risks? So I see a lot of benefits to the WASM ecosystem. I see a lot of benefits to WASI in particular. So in particular, WASI needs to eventually be implemented. It needs to hit the bottom. So any API which gives you a new capability in WASI has to make its way into the engine. As it is today, that can only be done in the engine because the engine is the only thing that has privileges to do it. And my dream is that eventually you have a WASI implementation that is against the OS interface, so Wally in this case, and then it's not per engine, and so you don't have to do engine work if you're doing WASI work. So if you introduce new capabilities, you can write that in a language, compile it to WASM, and it will run against Wally, and then now it runs where every Wally engine is. WASI has some implementation state, so it introduces new kinds of security mechanisms. It has capability-based security. It has some additional sandboxing, and it has new concepts. All that is some state that's associated with the user application that's using WASI, and that now can be a WASM module because we can move it up so we can separate WASI applications from each other and also from the engine. We got fault isolation. So programs have bugs. WASI implementations may have bugs. So what happens when they do have a bug? And that means that we can isolate the fault from the WASI implementation from being able to take over the engine. In terms of specification, we're going to eventually need to talk about what every WASI API does, what its semantics are. We can have a reference implementation against an OS interface, compile it to WASM, and now we can reuse sort of the executable semantics of WASM and say it's this WASM program executing against this operating system API. And hopefully, in the end, we can also verify WASI applications. So we can use the properties that you get proving things about WASM programs and WASM engines, but also prove that about the WASI implementation itself. So that little library that implements WASI, maybe we can actually prove that it's correct. So just to give that an illustration here, so in the world before we had Wally, the WASI implementation would live inside this WASM engine, and so it could potentially have bugs in it. In the new world, that lives inside of a WASM module. It's a WASM sandbox thing. And so, my amazing art skills here. So if we have a bug here, an out-of-bounds write, for example, which could happen because not all of them are implemented in wonderful, safe, memory-safe languages, that means that you could compromise the entire WASM engine, which means that you can take over the entire process. And so you could do anything that this engine could do, including talking to the kernel. Now you can start attacking the system, right? Whereas in this world, if there's an out-of-bounds memory write, you get the memory sandbox of WASM backing you up, so you can only access the state which is in that module, and therefore you could start attacking the engine, but you can only attack the engine with the things that what are the capabilities that have been given to this module, which should be smaller than the entire Wally set. So I'm an engine person primarily, so I think about this from my perspective. There's lots of benefits to WASM engines. So we reduce the trusted computing base. So all of the system interfaces, those no longer need to be, anything that uses system interface can be moved up and outside of the engine. This gives the engine a more clearly defined role. So we need, I think that Luke ran over a little bit. We have a break next, is that right? We are into the break. Okay, I'll try to speed up a little bit. So engines now have a clearly defined role. So they validate and execute code. They're for composing and sandboxing modules. They give you debugging tools and introspection. And then they give you this thin operating system interface. And that's like the end of their job, right? So they don't implement a new security model. They don't give you new I/O abstractions. You can do that yourself above. And I demonstrated the fault isolation. And this also helps engines develop faster because they have a clearly defined role. So engine experts, compiler people, they don't have to go spend time working on system APIs. And they can run more things. Once they have the system API, they know that they can run modules because they're a layer above. Applications that are out there, well, what is the portability benefit, or what's the benefit to them? They get portability, so you don't have to think about a native CPU when you compile your Linux application. Maybe in the future, Linux packages actually come as WASM by default, so you can compile away your source language, and then you produce this binary package, and the code inside is WASM. For security, there's some really important processes that run. For example, SSHD, and there's like lots of other system things. It makes sense to me that you could have them be WASM or Wally processes, and so they could never, ever, by design, have a remote code injection attack. There was a really comical one recently with SSH agent. Obviously, SSH agent is not the kind of thing that you want to be able to have any executable writable pages of memory, but there was an exploit change where they managed to load several shared memory DLLs in a row and unload them, and they were like kind of in a partially initialized state. So they exploited the dynamic linker to be able to get writable executable memory, and then they did a remote code injection attack on that. So even though people know about this, we're in 2023, now we're in 2024, that was last year, there's still exploits like this. So I think that like WASM and sandboxing technology, we can just completely eliminate that. It's more lightweight than a full process because you can have a little WASM module that runs against Wally, and it doesn't need like libc and all the other stuff that drags in. And of course, WASM is not the world's best development platform as it is today, but eventually it'll get better, and as it gets better, it means that all of these Linux applications, they will get access to all the WASM tools, so fuzzers and race detection and all that. I think it'll be better for the ecosystem, so we can WASM even more things, so more targets, meaning more collaboration and investment, so we're no longer just a niche technology, and we can build WASM applications in Linux directly. So again, our research partners, they like WASI and they like the component model, but in the brass tacks, like they're still building Linux applications directly. We can run more things on more engines. We can access functionality which has not yet been figured out how to put into a WASI API, and also means that WASI APIs that are envisioned now, they become available more soon because they can run more engines because there's an implementation against the Wally, for example. And it's a stable target, which is something that we've heard from some of our partners, that they're a little bit scared by the evolution of WASI and they don't know how they would use it or justify to their ancient upper management what it means that a WASI API is still evolving. It's not standard yet. It benefits programming languages. They get sharp knives. That's, if people have seen the paper, we have sharp knives in the title. That's what we're referring to. It means that a programming language that targets WASM gets to do all the things. They don't have to rely on the native libraries, assembly or libc to do that, and they can directly target the powerful capabilities, and they get all the WASM level tools. Research community benefits because all of their research is higher impact. Right? The bigger the ecosystem, the more impact it is. Eventually, this whole tower, we can start thinking about attaching proofs to all of these things. Will it run the web? I don't think so. I don't think it will run Wally on the web. And, well, is Linux going to now be the only thing ever? I don't think that's true either. I think that we could maybe have operating system interfaces for other key kernels as well. That's pretty much the end of it.
So we are now a bit into the break. If anyone has any questions, please put up your hands. Great.
Thanks. A very brief question about portability. I maintain a JavaScript engine, and we frequently get requests for implementing a syscall API in there, which we don't do. Instead, we're going for an FFI thing, mainly because of portability. And the main problem there is that Windows doesn't have a syscall API that is specified in any way. There is no public documentation of these syscalls or so, or any stability guarantees. Do you see any future? You mentioned Windows as one of the platforms where you could have such an API. Do you have any approach for that?
I've thought about this. It's a similar but not quite as bad situation on Mac OS too. They have a stable kernel API. They change rarely, and they kind of recommend that you link against libc. I think Windows is a similar situation. You're recommended to link against DLLs that have a more stable ABI, and they might do that for security reasons. So it may be that an operating system interface isn't the exact syscall thing, which might change. So whatever operating system vendor, they get to decide what level of stable interface that they offer. So you would want to pick something that they are committed to already maintaining as a stable interface.
Okay, makes sense.
One more brief question, then we'll break. Okay, we're looking good. So we are, unfortunately, 15 minutes into the break time. I would like us to start maybe 5 minutes late. Let's do that. So you've got a 20-minute break now. We do have one advantage. If you would like to go directly to the tea room, you can go through the balcony door there. Walk directly through the balcony, open the door at the other side. It opens directly onto the tea and coffee room. So we do have a shortcut.
move this mic too far away from my mouth? Someone just put their hand up. Warn me. Okay. So yeah, I'm going to talk about this work that we've been doing on something we call rich WASM, which is WebAssembly with a rich type system. And the goal here is essentially what the subtitle says, bringing safe, fine-grained, shared memory interop to WebAssembly. All right, so how we got started on this was, there are many different languages that compile to WebAssembly right now, and many of them are type-safe languages. And my group does a lot of work on studying interoperability between different source languages. And in particular, we'd like to have a platform for studying safe interop between languages like, let's say, OCaml and Rust, which are very different type systems. So can we use WebAssembly as a platform where we can do, provide better support for this? So the goal is to support safe and flexible interop between languages with very different type systems. But the problem with WASM as it exists is that memory sharing between WASM modules is currently all or nothing. I'll say a little bit more about this in a second. And the current interop proposals, Luke talked about the component model this morning, very rightly, are focusing on lightweight isolation and therefore focus on shared nothing interoperability. So what we'd like to do is actually, when you know that safety is not an issue, we'd like to be able to safely share memory. So that's the goal of our work. So fine-grained memory sharing with strong safety guarantees. So let's look at sharing memory in WebAssembly right now. So right now, WebAssembly has every single module has its own memory, and it's all private unless you export it to another module. So module B here can import this memory, and now it does have access to module A's memory. Everything is good, except maybe not so good because module B can just go ahead and do pointer arithmetic, which means that every single thing in module A's memory, now that it's been imported into B, is accessible to B. So, with pointer arithmetic, you can just read everything. Nothing is private anymore. So there is a proposal, the WebAssembly multiple memories proposal that seeks to, provide sort of a solution to this. If module A knows that it would like to share some stuff and keep other stuff private, it can keep, put all of the data that's private in memory 1 and all of the data that's public that it wants to export to module B or other modules in memory 2. And then module B only imports the second memory. But again, this is kind of a coarse-grained sharing approach, right? Because module B can still do pointer arithmetic and read anywhere in the second memory, which you can say is okay because it's public. But there is a problem still because source programs have to be aware of the distinction between private and public so that the compiler can appropriately make the right choice. What stuff do I put in the private memory? What stuff do I put in the public memory, right? You have to sort of a priori make that choice. And in general, I was talking about safe interoperability between source languages. So, this proposal doesn't help us with enforcing abstractions that might exist in different source languages, such as ownership, for instance. So it doesn't really give you the memory safety guarantees you might be looking for with shared memory interop. And another challenge that we wanted to address is supporting sharing memory between languages that have very different memory management strategies. I've been talking about interop for many different years, and almost always, someone will bring up this issue, like, what about if I have a language with a garbage collected memory and another language which manually manages its memory, right? Like, how do you handle these things? So that was something that we wanted to be able to handle going in. Okay, so our goal, safe shared memory interop between high-level languages compiled to WASM, even if they have different memory management strategies. And in particular, we've been thinking about ML and Rust, though we can't fully do Rust yet. I'll just say that right now. Let's take a look at what happens when a language like OCaml and Rust currently interoperate, right? You can break memory safety guarantees, and I just want to use this example to show you how. On the left, I have an OCaml program. On the right, I have a Rust program. The Rust program is going to use some of these functions that OCaml provides. So let's take a look. What's happening? At the top here, I'm just creating a mutable reference to a function. The function takes a unit, returns a reference to an integer. Then I have this increment function. It takes a reference to an integer, right there. But then it stashes it away in that function that's stored in the mutable reference f, and then it increments the reference. So it's doing this extra stashing before incrementing. The name increment just indicates that it's doing the last line. And then there's this read again function. which basically goes ahead and reads the function out of that reference f, calls it, and then returns the location that we stashed into the function. Reads the contents of that location. So now let's go over to the Rust side. Here, Rust is allocating a mutable reference. Then we go ahead and we increment that using the ML increment function, which means that the reference got stashed, right? Rust mutable reference just got stashed in OCaml code. And then, we print, etc. But when we get down to the end of this scope, the Rust compiler thinks that it's perfectly OK to deallocate that Rust reference. So it deallocates X. But then after the end of that scope, if we read again, this is going to be a problem because we're reading a location that is no longer there, right? So that's going to cause our code to crash. OK, so this is the kind of thing, right? Because OCaml doesn't understand Rust's notion of ownership. It can stash away a reference, which should not be allowed if you really want safe interop between languages like this. OK, so what we've done is we've developed this richly typed WebAssembly that includes something called capability types to capture memory ownership and memory access. And I'll explain what that means in a second. Let me just sort of say something about the overall picture or architecture that we're after. We're thinking of, type-preserving compilers from languages like ML, and we, as I said a few minutes ago, we don't actually do Rust yet. We do this core calculus called L-cubed or L3, which has ownership types, but it doesn't have borrowing. So that's the sense in which we can sort of do a subset of Rust, because we can do ownership but not borrowing. OK, so we have type-preserving compilers from ML and L3 down to rich WASM. And then from there, we compile down to WebAssembly. So we erase types, et cetera, and just compile down to standard WebAssembly. The way that we're sort of achieving our goals, if you will, is we have a very simple FFI that allows some additional annotations to do interop between ML and L3. But then the goal is that it's after you build your type-preserving compilers, it's type checking at the rich WASM level. When you link the two modules together, that's where you catch the errors. That's where you catch the type unsafety or type safety violations, such as the one that I showed you before. And I'll close the loop at the end and show you, give you a slight sense of how we do that. So let me dive into the design of rich WASM. Basically, let's start by talking about the memory model. So we have two global memories. They're shared across all modules. This is the rich WASM memory model. It's different from the WASM memory model. So we have this memory that we call unrestricted memory. This is the garbage collected memory. Okay? And then we have a memory that we call linear memory. This is the memory where we will put any data structures that are manually managed. Okay? Now, I know that linear memory in WASM means flat memory, right? So that's an unfortunate thing, but I'm using, whenever I say linear, I'm using it in the sense of linear types or unique types so that you have only one pointer to something in the program. OK, little unfortunate thing. We keep thinking about whether we should rename it. OK, so both of these memories are maps from locations to values. Okay. They're not byte arrays like WebAssembly has. So it's a higher level memory model in that sense. And only pointers to the beginning of data structures are valid. Okay. Now, what is a pointer? A pointer in rich WASM is going to be a pair of an address and a sort of qualifier or annotation that specifies, does this address live in the GSeed memory or in the manually managed memory? So that the unrestricted means this lives in the GSeed memory and this lives in the manually managed memory. OK, let's talk about types. The most interesting types in rich WASM, and these are actually pre-types, I'll explain in a second. We separate out this type for pointers. So this is the type of a pointer to a location L, and a capability to actually use or reference that location. So the capability, this type says that I have a capability or permission to use location L in either with a read access or with read-write access. We can choose either one. And it says that the shape of the data, the content stored at location L, is described by this type psi. Greek letters. Okay. All right. So then you saw the letter psi, right? That describes the shape of data that lives in memory. What we have is, we have structured data in rich WASM. We can have variants, structs, arrays, existential packages. And you'll notice something strange here. This is a struct with a bunch of fields tau, but for every single field, we also need to keep track of the size. Similarly, for an existential package, we keep a bound. We say, oh, alpha is a pretype. That's going to be some data somewhere. But what is the upper bound on the size of that type? And we need this so that we can ensure safe, strong updates of the fields of a struct and for local variables. And I'll talk about that a little bit more later. But basically, this is a low-level type system. It's talking about memory layout. It must track sizes because it's allowing strong updates. You can't go, update some location in memory if you don't have enough space there. You can't put a value that's bigger than what will fit there. And the type system is keeping track of that. Okay, so what are the types? Again, P is for pretypes. I'll put a qualifier on those in a second. But we basically have unit, numeric types, tuples. We have this interesting type which says there exists a location row. Row is just a location variable, such that I have a package type tau. We have the capability types that I showed you before, and the pointers that I showed you before. But we also have these references, and basically all that a reference is it pairs up or packages up together the capability for a location with a pointer to the location. So just think of the combination of those two things as a thing that we call a ref. Okay? We also have this ownership, own-L type. And this is useful because often we want to be able to take a read-write capability, split it up into a read capability, but then we need to keep its ownership capability somewhere so that we can later combine them. So we can go in both directions. We can go from here to the pair of these two things, and later we can combine them and go back to that. Okay, now I've been calling these pretypes because all of these data types, if you will, come annotated with a qualifier which says, is this data to be treated in an unrestricted fashion, which means you can make unlimited numbers of copies, or should it be treated linearly? And we also have qualifier polymorphism. That's why I have this qualifier variable delta in order to support that. We're going to have a lot of different kinds of polymorphism. Brace yourself. Okay, we're here. So we have this code ref type, which is just a code pointer, to some function whose type is C. And function types, if you ignore the for all kappa, right, this is just a regular function type, right? I take a bunch of things on the stack, a bunch of tau 1s on the stack, and the function produces a bunch of tau 2s on the stack. But we have polymorphism over a bunch of different kinds of things. So I've already mentioned qualifier polymorphism, but we also need to support location polymorphism, size polymorphism, qualifier polymorphism we've already talked about, and then pretype polymorphism over alphas. And you can see that I don't just have rho, sigma, delta, alpha here. I have a bunch of constraints on these things, which are very useful in the type system. In the case of sizes, we end up in the type system wanting to collect lower bounds and upper bounds on the sizes. And we can have a bunch of them kind of coming from different parts of the type system. We have, again, lower and upper bounds on qualifiers. And just to be very clear here, our qualifier ordering says that unrestricted is less than linear, so in case I end up sort of referring to that. And then we have the size bound on a pretype. Why do we need that? Well, if I instantiate an alpha, with something, let's say a struct of a certain size, it better be smaller than whatever this size bound is. Because in my function body, I'm going to be relying on the size bound to make sure that if I use that alpha and plop it into somewhere in memory, that memory size is big enough. Okay? So basically, this kind of function bound is going to appear here, right? this kind of pre-type bound is going to appear in the function signatures, and we need to know that when you instantiate the function, you're doing it with a value that's not too big. Yes?
So that's where upper bounds on size come from. Where do the lower bounds come from?
The lower bounds are often collected in other places. I think I have another example that I can show you.
If I want to use a type only behind a pointer or something, can I also just say don't care about the size?
Could you repeat the question?
If I want to use something only behind a pointer, then can I say that I don't care about the size? Yes, you don't always need to care about the size. So for example, if the function body, so for instance, if you're instantiating a function with an alpha and it's a box type, you don't care about what it's pointing to, right?
So the grammar allows me to have an alpha with all the size.
Yes. Mm-hmm. Okay. All right, so then once we have, this set of features, ultimately what we're after is if you have module A and it has a pointer to this location 1, which is an unrestricted reference with read-write capability to an array of I32s, location 1. Since this is an unrestricted memory, we want it to be the case that we can make a copy of this and give it to module B, and now module B will also be able to point to it. This sort of thing should be allowed, and I'll go through an example later and we'll get a flavor of it. Conversely, if module A is pointing to something in linear memory, again, it's at location 1, it's an array, but it's linear this time, then if we want module A to sort of share this linear reference with module B, then it has to give it up itself, right? Because it's in linear memory. You can only have one pointer to it from anywhere in the program at any point in time. So that means this has to go away. A has to give it up. Only then can it sort of pass it to B. That's the rule. Okay, let's talk about garbage collection. So basically what we've done in Rich WASM is we've axiomatized all of our rules of garbage collection, the way that, we've done the formalism. We've axiomatized the various rules. So let me give you a flavor of what we can and cannot do. So we do allow unrestricted memory to point to linear memory and vice versa. The garbage collector will reclaim any unrestricted or GC'd memory by following all the unrestricted references from the roots. Okay? Now, there's a tiny subtlety, and this is not a big deal, but I want to explain it anyway. There's this question of, can we store capabilities in the heap? Okay? And you'd say, okay, why not? But the tricky part is that, let's say L1 is a root, and it's pointing to something in the heap, and we want to go collect it. Let's say we're the garbage collector, we want to go collect it. The problem is that not problem, maybe good thing is, that when we compile Rich WASM to WASM, we erase all the capability types. So anything that's only needed for static checking, for checking type safety, is going to be erased. Okay, so capabilities are going to be erased, pointers are not. Right? Pointers are actual addresses. Something of type PTRL is an actual address, and that address will not get erased, but anything that's a capability is just a static thing, it's ghost state, and that will be erased. So basically, since capabilities get erased at runtime, the GC doesn't have a pointer to follow if we only allow a capability to be stored in memory, and then it gets erased. So we follow a very simple rule. Don't allow capabilities to be stored in the heap by themselves. They should always be paired with a pointer. That way, when the capability is erased, the pointer is still there, the garbage collector still can do its work. Yeah?
I had sort of the opposite question.
Yeah.
A pointer by itself doesn't have any ownership of anything at the other end.
Yes. Mm-hmm.
So how does the garbage collector know not to follow the pointer?
It doesn't have ownership. So this is the opposite question, which is that a pointer doesn't have ownership of anything that is actually pointing to. So how does the garbage collector know that that it should not follow it? The garbage collection is a very runtime concept. By the time we get to that stage, we've already done type checking of the full program, and we, assuming that you're not linking with any other code that didn't come from Rich WASM, you have a safety guarantee. So that problem doesn't really arise. We erase the capabilities because we already know that everything that's happening is correct, in a sense. Okay, so just don't allow capabilities to be stored in the heap alone. Always package it up with a pointer if you're going to store it in memory. Okay, there are some additional things. I mentioned the roots of the garbage collector before. So the roots are locations on the stack, and they are unrestricted locations that might be referenced from linear memory. So remember I said we can have pointers from linear and pointers in both directions from these memories. But in particular, if you pay attention to the pointers from linear memory, they are our roots, right? Because you may not just have pointers from, roots that come from the program, you might have some pointers from here. So to avoid scanning the linear memory, looking for unrestricted locations, we assume that the runtime maintains an outset. So all of the pointers going from red to green here should be thought of as an outset. And they're just a set of linear locations that point to unrestricted memory. You can think of it as a pinned set, if you will, right? That's all we need to keep. Okay. Now, what if we have a pointer from unrestricted memory to linear memory, and then it might point to some other linear locations? A linear location can only have one pointer to it at any point in time. That means that this location is only pointed to from the unrestricted memory. There's nothing here that can point to it. So if the garbage collector comes along and collects this location, then it must also collect this and this and this. Right? So it must follow those pointers and free the things in linear memory so that we don't have leaks. So we assume that the GC will recursively claim this chain of linear references starting from some location L. And to support this, now this is where we connect to don't connect to the WASM GC proposal. So in order to support this kind of pattern where we go and clean up, the garbage collector just goes and cleans up in linear memory as well, we basically need some notion of finalizers in order to implement that, which the GC proposal doesn't currently support. So that's a problem for us. Okay. How am I doing on time? As in, tell me what time it is. Okay, great. Thank you. I didn't bring my phone. All right, so let's quickly go through an example just to give you a flavor of how this works. So here's a function. It abstracts over size sigma, which you'll notice can be, has both upper bound and lower bound 64, so that says sigma must be 64. It abstracts over a pretype alpha that is upper bounded with the 64, and it abstracts over a location variable rho. All right? And what does the function do? Well, it takes as input a linear reference to a struct that has one field. It has a linear field. This is the size, so size 64. And then, by the time the function is done, it will basically take this value out of the struct field and return it. Well, you could have, I could have not, I wanted to show quantification over some kind of sigma. Otherwise, I could have just not done that and just put the 60. Oh, that actually should have been, I quantified over it because I'm trying to say that this struct has a certain size. Actually, I think maybe I should have made this sigma as well. I can inline it all. Yeah, this is just for the purpose of putting one more quantification up there, just to confuse you guys or illustrate more things. Illustrate all the crazy things that we can quantify over. Okay. I mean, this example is so trivial. The lower and upper bound are both 64, so you're absolutely right. Now, it couldn't just be concrete. Okay, so that's the function body. Yeah, so basically what this code is going to do, and I'll step through it, is it'll extract the value stored in that struct and return it. So let's see, when we first call this function, what happens is that the argument to the function gets put into the locals of the function. All right, so that's what's happening over there. We have a pointer to some location where the struct will presumably be stored, and our locals support strong updates. That's why I have to put the 64 there, because I have to remember what is the size of this local. Because if I updated it, I can't put something bigger than 64 there. Okay, and what does lin point to? Well, it points to something in linear memory where my struct is sitting. Struct is of size 64, and it contains the number 42. Okay, now I'm going to do a get local 0, which means that I'm going to copy that reference to lin onto my execution stack. Okay. After that, I'm going to push unit onto the stack. So I just push that unit onto the stack. And And now what we're going to do is a struct swap 0. Before I actually do that, let me explain what struct swap 0 expects. Struct swap 0 says, go find me a struct pointer, that's this guy, find me the 0th field of that pointer, and I'm going to put this value in there. That's what it's going to do. So let's go do it. So what it just did is it took the 42, put it on the stack, and it took the unit and put it in the struct. It swapped the 0th field of the struct. Do you want me to go back? I saw 2 confused looks. Right? It's like that. There's a 42 sitting in that struct. We're going to swap that with the unit. There. Okay? Then set local 0 is basically just going to set local 0 is going to put the 42 in there into the locals. And now we have this reference left to our structure, which we're going to deallocate because this is a linear thing and the function is not returning it, so we have to free it before the function returns. So go ahead and free the struct right there. And then to finish up, we're just going to do a get local 0 and copy that 42 from the local stack to the execution stack, and that's the result. Okay. All right. So jumping ahead, here's the shape of the typing judgment. So if you just ignore everything on this side of the turnstile for a second, this is basically a sequence of instructions that expects a bunch of tau 1s on the stack and produces a bunch of tau 2s on the stack. All right, but we keep track of so much additional stuff, right? Like there's all this kinds of polymorphism, there's stuff about memory, etc. That's why we need a lot of different environments. So let me just explain what's in the environments. Oh, I just realized we've actually changed the store typing to the letter S. I forgot to update the slide. But yes, store typing here keeps track of basically the types of data in unrestricted memory and the types of data in linear memory. And something to keep in mind is that as you type check subterms, you will have to split that sigma. You will have to make sure that you take disjoint parts of linear memory and give it to the subterms to type check, just like you would in any linear type system. Then there's the module context, which is pretty standard. It just keeps track of the, like WebAssembly, it keeps track of function types, globals, tables. F is the function context. We have polymorphism over a lot of different kinds of things, and F keeps track of polymorphic variables and the constraints on them. And then we have this context with locals. And again, because we support strong updates on locals, we're basically saying what are the types of the locals and what are the sizes of the slots. This sequence of instructions might do strong updates on the locals, so we have to thread the environment through and say, oh, what did you change the types to? Okay? All right. I'm just going to very quickly walk through one typing rule for struct swap. So we've already seen the struct swap instruction in the example. It's going to say, give me a reference on the stack to a struct which has a bunch of taus in it. It wants to go and update the ith tau, and it's going to update tau I in this struct with tau I prime. Okay? All right. So what happens after it's done the update? Well, it's a swap, so it takes the tau I and puts it on the stack where the tau I prime was. It takes the tau I prime and updates the type of the ith field in the struct. So straightforward, just like walking through it. There's the update. This instruction doesn't use anything in linear memory, so we make sure, it basically says that the linear part of S should be empty, since we're not using any resources. And then it says, ignore how it says it, but make sure that the new type, tau I prime, fits in the struct field so that its size is less than the size of the tau I, the ith field of that struct. That's why we keep the sizes of the structs. All right. Getting close to wrapping up. We proved type safety in Coq. It's a standard progress and preservation. A configuration which contains a store, the locals, and sequence of instructions can either, be a value, be a trap, or take a step. Preservation. Preservation says that if you have a well-typed configuration, then you can either take a normal instruction step or you can take a GC step. So again, this is why we axiomatize the GC. A GC step will, sort of conform to all the rules that a GC can and cannot do, right? Like how it can munge the state or not, and you'll still have something well typed. This was a Herculean effort. So I've put lines of code up there. We still have a few substitution lemmas left, but even substitution is by and large mostly done. Okay, so just to wrap up, back to the example that I showed at the beginning. How do we, just a very, very simple flavor or sense of how we use this. So with this OCaml set of functions, basically our simple extension to OCaml in terms of the FFI is that we add this linear annotation on references. The OCaml type checker completely ignores this, this linear annotation, but what we use it for is essentially this FFI, tells the compiler, the ML compiler, that when you compile this down to rich WASM, you better annotate that reference with lin. So it'll end up being a linear reference, which means that then type checking at the rich WASM level will complain about this code. It'll say, oh, you're trying to stash a linear reference into an unrestricted cell. And therefore, type checking will fail at that point. And you can play with variants of this, but essentially type checking will fail at the rich WASM level if the wrong thing is happening. Right there. Okay, final slide. There's a whole bunch of different things that we'd like to do. Really the goal here is to develop a platform for interop between different typed source languages. There are many, our focus so far has really been like what we thought of as a very hard case study, how do you get GSeed and manually managed memory to safely interoperate if you have kind of the safety assumptions at the source. But there, we don't deal with control effects, with many other things right now that we need to be able to handle. The first thing that we're tackling right now is actually extending this to Rust, because we can do ownership, but we can't do, in particular, immutable borrows. We don't know how to represent in the rich WASM type system yet. So how to represent immutable borrows, how to represent lifetime constraints. My student Sarah Marshall is actually working on that right now and has some very nice ideas. Then the rich WASM to WASM compiler, right now we erase all of the type information in rich WASM when we compile down to WebAssembly, but we could use WASM's custom sections to keep that information around and actually write a rich WASM type checker at the WASM level. That would be like sort of akin to doing proof carrying code then. So the rich WASM platform is great for exploring all kinds of safe FFIs between typed languages right now, right? The type system, we want it to be rich enough to be able to give you errors when you have type-safe languages interoperating. But you have to build the type-preserving compilers from those source languages. But what about interop with C code that was compiled to WebAssembly? We can't compile C code to rich WASM. The type annotations required would be, like, where are they going to come from? So ultimately, the thing that we'd like to be able to do is take typed languages, compile them to rich WASM, take untyped or unsafe languages, compile them to WebAssembly, but now you have the problem of safe interop between rich WASM and WASM, right? And this is sort of an instance of gradual typing, but a little bit different. But of course, you have to do it in a performant way. So can you use, one of my students, Michelle, wants to look at, Michelle Talakoter, she's actually a co-author on this paper as well, wants to look at whether we can use static contract verification to avoid dynamic checks at the boundary. We won't be able to do it for everything, but can we minimize them? Another approach is to use something like compile to Cherry so that you can do capability checking dynamically. And then finally, we'd like to do a semantic model of rich WASM types as sets of WASM terms. Such a model would allow us to prove correctness of optimizations in the compilation from rich WASM to WASM. So the rest is, yeah. Okay, that's it.
So we have plenty of time for questions. I think we only have this mic, right? So I might need to go around and give it to you so we hear the questions.
I have a kind of vague question. I'm not sure how to phrase. So my impression of rich WASM is you've added a lot of new abstractions, and they feel kind of like source level abstractions. You've sort of added new primitives to the language. Maybe that's necessary because you have new concepts you need to enforce. How do you enforce them if you don't know what the abstractions are? But that seems at odds with the goal of a low-level language, where you want a very small set of low-level primitives.
Yeah.
And what you would prefer is to sort of enforce a derived concept. So let me be concrete. You have struct axiomatized into your language. And it feels like what you're saying is, I know a priori what a struct is. It's a thing with a certain number of fields. It's a separate object from all other objects. But from a low-level perspective, you'd like to say a struct is an a posteriori, after the fact, I have this large chunk of memory. A struct is some subsection of memory that I want to treat as different, right? It's not a primitive concept, it's this derived concept.
Yeah.
That feels more like the low-level perspective, where you have this high-level version of a struct.
Like in the proof-carrying code work from years ago, right?
Exactly.
We encoded structs using simply references.
Yeah, so I
individual
guess my
cells.
question is basically, have you thought about how you would do something like ritualism, but from a more low-level perspective where you're deriving rather than axiomatizing more concepts,
So
or
I
whether
think-
that's possible?
Yeah, I think that we already are pretty low level. Like, we are not taking just source level things and building them in. The reason we built instruct and variant and array is because we were actually inspired by the GC proposal that was being worked on at the same time. Andreas had pretty much exactly those types, except not existentials, in the GC proposal, and so we decided to adopt them. But you're right, we could encode them. But the way in which we are low level is, we have these capabilities, and actually, even as we compile Rust in a type-preserving fashion down to ritualism, our struggle has been, what are the lowest level concepts that we need at the WebAssembly-ish level, just only slightly higher than WebAssembly, at the WebAssembly-ish level, to encode these notions that might exist in high-level languages without baking in too strongly anything from any individual high-level language. So yeah, I'm very much a believer in the whole proof-carrying code concept, in code or typed assembly language concept, right? Find the most primitive building blocks that you can. It's just that, yeah, you're right, we didn't do this with struct and variant, and I think partly we were just sort of inspired by the GC proposal. We adopted them very early on. I think we could do it. I have to think through it a little bit more. I shouldn't promise it, but yeah.
Okay, a question here about sometimes your language would like to come with its own garbage collector. And that would mean that you would have to be able to express the garbage collector in ritualism itself, right? Would that be is that possible? That's one question. And the other thing is, one of them might be a copying collector, right? And so then suddenly there will be other problems with borrowing and so on. So maybe you can comment a little bit.
So the way that I think about, I keep saying that so far we've axiomatized our garbage collector as far as the formalism is concerned, as in we haven't implemented one and verified it. And secondly, when we compile from ritualism to wasm, we have our own little simple naive collector. But the way that I always imagine doing this is, you pose a very good question. The way I always imagined doing this was that you would implement your GC and verify it. Then that way you can use some pretty sophisticated separation logic. You could use Iris or something to actually verify the GC implementation. Can we do GC implementations that would type check in ritualism? That's a very good question. And to be honest, I haven't thought about it before. If I had to venture a guess, I think a simple collector might be okay, but anything more sophisticated, with subtle kinds of invariants that the type system can't express. Maybe the issue is, if you can write your type checker in Rust, then most likely yes. By the time we're done, at least with the Rust type preserving compiler, we'll be able to type check it. Assuming you're not using too much unsafe Rust. Right? So yeah. But thank you. That's a very interesting thing we should think about.
More questions, yeah.
I think the settings went to the screen.
Hi, thanks for the talk. You were talking about interoperability of two languages, and then you had these two different kinds of memory that sort of corresponded to the way memory was treated in those two languages. So I was wondering, if we want to have more general interoperability of a set of languages that could maybe be useful, would you need a different kind of memory for every single language, or do you think those two are enough to express anything that's plausibly useful?
I think those two are enough to capture anything that's useful, because that's the fundamental divide, garbage collected versus not. If you do some sort of reference counted memory implementation, you can do that using the manually managed one. So everything can be mapped down. But yeah, these two ought to be sufficient.
Amal, you mentioned C, right, where you might have to go into gradual land, but like even ignoring that, how would that interoperate then in terms of memory?
How does that interoperate in terms of memory? Like if it's...
Like where would the C world memory live, right? That would be a third kind, wouldn't it?
I was thinking of C as... C would be manually managed, but it wouldn't be compiling to rich WASM, right?
Yeah.
So now we're looking at a world where we've compiled from rich WASM, like effectively we have the rich WASM types, but now you have C. I think the problem simply comes down to what are the rich WASM types, what are the constraints the rich WASM types are imposing on normal WASM at that point? Oh, sorry. I think it simply boils down to an issue of rich WASM at that point having statically checked capabilities and normal WASM coming from C having dynamically checked capabilities. Or, we need to dynamically check them if we want safe interop. So on the C side, you'd have implemented your own memory allocation and so on. So I think everything should be fine.
Right, but there would be a third kind of memory.
There would be a third kind of memory that's coming from WASM this time, yes. Not in rich WASM, but outside, yes. Sorry, I didn't understand the question.
Well, it was kind of confused, but anyway.
Okay.
We have maybe time for one more quick question.
Hello. So you did mention you must not have too much unsafe code in the Rust, right? Do you propose to annotate all unsafe code with this type system? How would it work?
The reason I said that, and it was just a throwaway comment, like it just suddenly popped into my head that what if you're using a lot of unsafe code to write your garbage collector? Here's the issue. Right now, we're talking about type-preserving compilation from Rust. And at least for starters, we're focusing on what type system features we need in rich WASM to capture the types of safe Rust, right? Unsafe code has, Ralph's done a ton of work on this, like unsafe code has different invariants. If we end up augmenting rich WASM with richer types than what you need for just safe Rust, then we'll be able to type check any, more unsafe code as well. How far do we want to go? And there's this trade-off, right, between type checking and verification. And I don't think we want to go all the way to the verification end and have like unbelievably sophisticated logics and have a crazy fancy type system. At that point, you just have a logic, not a type system, right? The reason we're trying to do a type system is because we're trying to give compiler writers a simple way of implementing safe interop. Like write a type preserving compiler, just do that, and then get some errors from rich WASM, right? It'll catch them for you. If we get too fancy, then the compiler writer's job becomes hard. So where's the sweet spot? I'm not sure.
Thank you.
Okay, I think we should move on. Let's thank Amal again.
Your machine.
So the next talk is by Daniel, and he will talk about our work of integrating effect handlers, algebraic effect handlers, into WebAssembly.
Yes, thank you. Am I audible? Do you need that? I think I have a mic here, but I don't know if this one is audible. It's audible? Okay, good. Yeah, thank you very much. My pleasure to be here. As Andreas said, I'm going to talk about sort of retrofitting effect handlers onto WebAssembly for the purpose of giving a way of doing stack switching inside core WASM. And this is joint work with a lot of people. And as you can see, this is like a pretty full slide already. But one thing I want to draw attention to is that if you think this work is interesting, and if you would like to work in this, I'm sure I can fit more pictures onto the slide. So just get in touch with me. And I'm interested in everything from like students to do research on this, also to engine implementers, to prototyping this in their engines. So there's a little address down here. You can follow that. If you cannot remember this, it will also be on the last slide of this talk. Okay. With that in mind, let me dive straight in. So what is the motivation here? Well, the motivation is, if you look at all the program languages we have out there, very often you have some kind of non-local control flow feature in the language. And even some languages have the whole identity spun up on non-local control flow. So I made a list here. I've just sort of handpicked a few, and I hope you all will agree with me. These are like real-world things you'll find in languages out there. I hope you also agree that the languages that are sort of listed here are all real-world or industrial strength languages. So this is not something I'm just making up from my small research language. And in particular, I decided not to put any of my own languages here. But async await, for instance, is a thing that many people care about. And right now, it's not easy to express in WASM if you want to compile that. And same with coroutines and generators like wait threads and so forth. So the question is really, how do I compile this? And the answer is, you can't. Asterisk. And then there's some subject to term and conditions. And those are, of course, is possible, but it's not possible in core WASM itself. So what could we do to address this? Well, we could add each abstraction as a primitive to WASM. And then, the next 700 of these will come around. If we add 700 different instruction sets to WASM, it's not really going to scale. So let's just forget about that idea immediately. What you can do, though, and you can do this today, is that you can do a source-to-source transformation, which basically is akin to doing a CPS transform over your source program. And that's what people do today with a thing called Asyncify. So let's look a little bit at what Asyncify is doing. So here's a little program. It's a do something. It calls a function called bar first with an argument arg. And then whatever that returns, it plumps that into foo. It might look simple on the surface, but I can guarantee you this program is nothing but, it's not very simple at all when you look through the lint of Asyncify. Because you have to ask a question here. What can bar do? Can bar suspend execution? Okay, because that's going to have a sort of a ripple-up effect, a bubble-up effect on how this code is going to be compiled. And similarly, you have to ask, can foo do the same? And okay, so basically when you compile this with Asyncify, this is sort of the result you get. Okay, so those lines of code expands into this kind of thing here. And I should say here, disclaimer, this is not exactly the code Asyncify gives you, but I've sort of fitted it for the slide here. But it's in essence what's going on. So I don't expect you to read this code. It's just to show you what's going on. But I will highlight a few sections here. So the first thing you'll see in your function, you have like a prelude in all your functions. That's basically to test, am I in a state where I'm restoring, or am I in the state where I'm calling this function for the first time? And once you've done that, then you actually have to walk your way down through all these branches to say, okay, now I need to either call it or restore my context. And then once you're done, you have to check, am I actually suspending, unwinding the stack, or am I done computing? So you have these phases in your function now. Right, so let's try to characterize a little bit. So I sort of divide up to three pros and cons here. I would say one pro is it is expressive. I would hypothesize you can probably not do all the applications that I listed before, the features that I listed before. It's a source-to-source transformation, so it works today, and it's heavily optimizable under closed-world assumptions. So that means you can actually get rid of many of the branches that are showed. Sort of a con is that in the general case, you cannot actually get rid of all the branches. So you are going to have some kind of code blow up. And your sort of pure line, straight line code, if it has a function call inside it, then it's no longer straight line. It will have branches inserted to deal with this unwinding and rewinding. And it's sort of inherently a whole program approach, which is unfortunate if you're interested in separate compilation and stuff like that. Okay, so what are the sort of key primitives that we have in Asyncify? Well, they are called unwind stack, delimit unwind. So that's saying unwind up to here. And then you have rewind stack, which reinstalls the thing you have captured, or goes back to where you were before. And if you look at this, and if you're me and you look at this looks really familiar. So we could sort of rename these terms a bit, and we could say, what if we call them like suspend continuation, and we call them delimit suspend, so suspend up to here, and then resume continuation. Then basically what we're looking at is just a particular implementation of what is known as delimited continuations in the literature. And I would say that's exactly what Asyncify gives us, more or less. It's delimited continuations over unit to unit. Which is insufficient to implement many of the things we care about. And the way to look at this sort of intuition is that you see continuation as sort of a handle to an execution stack, to a particular stack. You get to veer it through continuation. Whatever remains to be done on that execution stack, that's your continuation. That's the way to think about the relationship between stacks and continuations. Right. So what is the solution? Well, why don't we just take whatever Asyncify is doing, this idea of delimited continuation, and we turn it into a bespoke instruction set. Very good idea. But now, where do you start? Because if you open the literature, you'll find that a lot of work has been put into this kind of work before. The earliest one I put here is Verleisen, but it actually goes before that with Core CC and others. So which one do we pick? And the one we picked is, well, no surprise from the title, is the latest one based on plug-in Pretner's effect handlers. And maybe just justify that choice quickly, is that you can basically see effect handlers as a structured form, a structured interface for programming with non-local control flow. And given that control flow is already structured in WebAssembly, we'd already seen like, maybe there's some synergy here. And the way I think Andrew Rao put this best, and he said this many times over the years, is that effect handlers are basically to limit continuation what while is to go to. And I think that's a very good way to conceptually think about it. But more than that, I think where effect handlers excel over the others is that actually it's very compatible with the simple types of WebAssembly. And in particular, it synergizes really well with the stack typing. We don't need to do any changes to how the type system works, which is not true for many of the others. They have a very complicated typing schemes, mostly. It's also an imperative control structure, unlike many of the others. You can make the others into imperative control structures, but it will require some changes. So basically, effect handlers are like exception handlers, if you like. Predictable performance, I think more or less all of them have that, but you get that here too. And it also works with and without garbage collection, which is a plus. I put here in parentheses one-shot continuation. So I think this thing here is only true if you have one-shot continuation. If you have multi-shot continuations, then you can form cycles, and then you probably need full-blown garbage collection to clean it up. So what we restrict ourselves to here is one-shot continuations. And another reason for that is also it works really well with what's already in WASM, and the assumption that WASM makes, basically like it's a linear world. So being able to only enter a context once is basically what many systems would expect. Once you can do it multiple times, then yeah, funny things can happen if you do not expect it. Okay, so this is my favorite slide of the talk here, because this is the entire instruction set of what we call WASM effects, the extension to WASM with effect handlers. So there is one new type. That's a continuation type. This is your type of a stack, if you like. This is the one that gives you a view over the stack. And it's parameterized by a stack type. So for those who don't know, well, stack type, function type is basically the same in WASM. But the way this says here, like, I expect some sigmas to be on my stack. And these are exactly the arguments that I need to run. To start me, you need to supply these sigmas. And when I'm done, I'm going to return you these taus on the stack. That's what you get back. Okay. And then the next extension, which is not really an extension, is the tag here, which we call a control tag. The reason I say it's not really an extension is that they actually come in with the exception handling proposal. So the only thing we add is this result thing. So now, instead of only being able to throw them up in a context and never come back, now you can actually come back from throwing these. So basically, this says here, like a tag is a thing that carries some payload sigmas and returns you some taus. In the literature, this is what you usually call a control verifier. This is what we're going for here. So this is your shift, if you're really familiar with shift reset, or this is your control prompt. And then we have three core. Sorry, yeah. Well, it is basically a function type in the sense that I have. It has the same type as this up here, right? It's the same stack type. It is saying, like, in order to invoke me, you need to supply me with the sigmas, like the arguments to a function. It's the same thing. And when I come back, I'm giving you back all these taus. So it is a function in that sense type. I have not introduced this type. This is something that's already in WASM.
There must be some difference here. I don't understand.
Well,
Phil, are you asking about the tag or the continuation type?
I'm asking about the tag.
Okay, just to clarify.
Right. Okay. So the question is this just a function type?
Andreas can correct me if I'm wrong. My understanding within WASM, the way a continuation type would be expressed is it actually is a function type underneath, right? So the WebAssembly modules has a list of function types. The way you express a continuation tag is its continuation indexed to one of these function types that have already been declared. So we're not creating a new way to express function types, just a different place you can reference them. Does that answer your question, Phil?
So he's just putting up syntax here. Really,
Yeah.
param result is a function type.
It is a function
but
type.
the tag is a runtime value that is associated with this function type, right? Like.
Yeah.
So functions are fixed statically, whereas tags might be dynamic.
No, tags are also statically fixed.
No, but
I just wanted an intuition about what the difference is.
it's like.
Maybe you should just go on.
Yeah.
Like an exception identifier, right?
Yeah.
A tag's like an exception identifier. So it is a name you can raise and catch somewhere.
Yes.
Which identifies a certain effect. And there is then a continuation with a certain function type attached to it, but that is a separate kind of thing in terms of semantics.
Yeah. Ben?
Yeah.
There's a pattern match built into resume. This one here, yeah, I'm getting to that. Yes. It is. We're using the function types here, but in a technical sense, and this is not really an important point, it is a different space we are operating in. It's not the function space, but we're just using the same syntax. And it's the same way you declare them, and it's just an index into. Yeah, but they're already in Vasm today. It's not a thing we add with this, but in a technical sense, they are actually different. But in Vasm, they are just all conflated into one, to the function space and using the same syntax.
I think once you explain resume, that becomes clear how they.
Okay, we try. Yes, we move on. But 3 core instructions. The first one is cont new. It's a way to create a new continuation. So you give it a function, and then it will create a new execution stack for you, where that function is ready to run. Then you have suspend, and it's parameterized by a tag. One of these up here is saying, I want to suspend execution of this stack, and the sort of signal I'm giving is this tag here. If you think of it in terms of exceptions, it's this exception that I'm throwing, this tag. Okay. Then you have resume. That's the one that starts or continues a continuation. So it does both. It's the one you invoke initially to start a continuation, but also if you get back a suspended continuation, you use this. And it has, as Ben was saying, like it pattern matches on tags. And what it does here, this is the name of a tag, so this one up here. It maps that to like a label that's in scope of the resume. And I'll make that very concrete in the next slide when I'll give you an example. But that's basically how we implement the cases. So you can pattern match on the different tags by saying, well, if this tag is raised, then jump to this label in my ambient context. So it's a jump table, basically. Okay, so those are the core instructions. I also just want to say briefly that there are 3 other instructions, but they're not necessary, actually. You can get around without these. One is cont bind. That's partial application for continuations. I'll get it back to later why that could be useful. And then we have sort of a thing just like resume, but resume throw, that injects an exception into the continuation. That's useful for cancellation if you want to clean up. But you technically don't need any of this. And then barrier is a thing to say no control shall pass through here. So that gives you sort of a catch-all handle around your context. Yes, so if you're a compiler, you can get around this bit code by duplicating the code you're generating. This one here, you can get around by having a special values fit into your resume. So you define your own API, and then you can do that. So you technically don't need them. But given that exceptions are already coming in, it seems kind of natural to use them. So to do the cleanup and give a way to do that. But if you don't want to use it, you can also get around without it. No, but that will come. It'll be on the stack. I'm not giving you the types yet. I'll get to that, but that's a very good point. Yeah. So just the status of where we are with this proposal and this work. All of it has a formal specification now, and all of it has an implementation, a reference implementation that we have built on top of the Vasm reference interpreter. And then most of them have an implementation in Vasm time. That's what we're currently working on. And you'll see 2 of them that don't have is resume throw and barrier. And resume throw is not there because there's no exception support yet in Vasm time. It's not landed yet, so we're waiting on that to land before we can implement it. And then barrier is just out of laziness. Don't really have any, not really been really keen to do this. So maybe one day it will be there. All right. So let me give the example, and let's make the instruction set concrete here. Let's try to do some yield-style generators. So first, what I do is I declare a tag. I call it gen. It's parameterized by an integer. The result type is implicit here. This is just syntactic sugar. Maybe I should have written that out, but it's basically unit when you don't write it. Okay. And then I have a function called nats. So what do I do first? I declare a local called I, and it's by WebAssembly semantics zero initialized, so I don't need to say that explicitly. And then I start a loop, which I give a label called produce next. Okay, I'll get back to that in a moment, what we use that for. The first thing we do is we suspend inside that loop with the value of I. So that's immediately going to suspend execution and transfer control upwards in our execution context. Then when we come back from that suspend, then we update or increment I by 1. That's what this slot is doing here. And then the next thing we do after that is we then branch to produce next. So that basically saying do this loop one more time. So in WebAssembly semantics, the way you do a loop is you have to explicitly say you branch to that loop. If you don't, then you fall out. Okay. So that might seem a little bit odd, but that's how it is. Okay. Then let's define a sort of a. So that's our generator. Now let's define something that uses this generator. I call this sum, and I take as input some number of iterations we run, and then an initial continuation that we're going to run. And then the first thing I have is I have some setup where I need to set up what is the current value we have and what is the state of our accumulator. And then I set up this handling loop. So you see here I have a loop that says consume next. And then inside this loop here I define a block called onGen, which when it's done, it will have an I32 on its stack, on the stack, and it will have a continuation on the stack. Okay. And then inside that block, that's when I actually run the resume. And what do I say in the resume here? I say, well, if the gen tag happens, then jump to the onGen in the context. Then onGen is in the context, it's just above it. Okay, and then I run with the current value of k, the current continuation that I have. And then I print the result. Oh, that's a missing thing. There should be a return here also. But yeah, okay. Then if or maybe I should say this first, actually. So the only point where this print executes is when I return successfully from resume. So if I don't suspend, that's when I flow down into here. Okay. But if there is a suspend, then I flow to I branch to the onGen. And now you need to know something else about branching in WebAssembly is that when you branch to a block, you branch to after it, not to the beginning of it like you did with a loop. So that's a bit different. That's the semantics. So if I'm suspending with the tag gen, I'm going to jump to this code block here. And in here, I set up the next continuation because that's on the stack. That's what it says here. And I set up the next save the current value we have. That's the I32 that I got. And then I increment my sum. And then I say down here, I say, well, I branch to the next consume, so I continue the loop if I still have more things to run, or if I want to get more values. And then finally, if this doesn't run, then I flow through here and I print the value. Okay. So if you write this expression here, call sum of I32 const 10, so that means I'm calling sum here with 10. And, oh, there's a typo there too. It's not be a bracket there. Then I give the initial continuation to be the function nats. That's the one over there. Then it returns 55. I don't know. I don't know. Maybe you don't believe a slide. I could run it for you here, and we can just see it with our own eyes. So I have the reference implementation here. So WASM-FX, I think it's called generator. And then I think I just call the program main. Oh, we should see the same output here. Let's pray. Ooh, yes. So we get a 55 out. Okay. So that's basically that's how we could do a yield start generator. It's one way. You can do it in other ways also, but this is one way you could do it, and it fits on a slide. So that's why it's nice. So to address Phil's question about the types, let's move a little bit on and look a little deeper at what the instruction set looks like. So as I mentioned, there is a new reference type called cont, which is parameterized by the function type or stack type. And then we have the instruction cont new, and here's the type of cont new. it says I should have like a reference to a function that expects some sigmas and returns some taus. And then what I give you back, I give you a reference to a continuation that has exactly that function type inside it, okay? But it's suspended. I don't run the continuation. You get like a sleeping thing back, and you have to explicitly run it in order to execute it. Okay. Then we can suspend continuations. This is really simple. It says like if you suspend the tag, then you better have some sigmas on the stack, and then I give you back some taus. Where are these sigmas coming from? Well, it's exactly what the tag expects, okay? And the return type is exactly what the tag tells you it will return with. So there's nothing really fancy going on there. This one here, resume, is the more interesting one, okay? So if you sort of ignore the tag list for now, you can see I put like a little white space here, so maybe you can imagine what's going to appear in a moment. But if you just look at resume, then basically what I'm saying here is that there better be some sigmas on the stack, and those sigmas should be the same as what the continuation that's on the stack expects, okay? And that continuation is going to return a tau, which is going to be the ultimate return type of resume also. So once the continuation is run to completion, I'm going to return via the resume. I'm just going to bubble that value that I got out, okay? Where it's interesting is when you add the sort of a filter list here with the tags and handler labels. So this says here, like, I have a mapping from tag to H, to the label H. Then it better be the case that my tag will expect have some payload sigma i's. It better be the case that in the block where I handle tag, I should expect to have exactly the same sigma i's on the stack, okay? But I should also expect to have a new continuation, the way I can resume or go back to where I suspended. And here I say, well, it better be the case that my continuation takes whatever my operation or my tag expected as output. So the return type of the tag becomes the input type of the continuation. But still, the ultimate return type of the continuation is the same as what I expected in the context is tau. Okay, so that's really all that's going on. It's just making all the types line up. Good question. They don't relate at all because these sigma i's here are coming from the tags. They're coming from the context you are running in. So this is the payload you suspend with. Okay. The resumes up here, these two here, these are like when you apply the continuation. So if you're inside the block H, then HI, then what you'll be continuing with would be the tau i's you apply here instead. That's what will happen. But these sigmas here are not related to these sigmas here in exactly. Yep, that's right. So the tag is exactly telling you what's going to happen when you suspend the execution context. You move up to the ambient context, and then yeah, absolutely. Okay, let's do one more example. So let's do lightweight threads. So they might look like this. We have a type, a task C, so the continuation task. It's a continuation from unit to unit, and then I have a tag yield for suspending execution. It's also unit to unit. And then I have an interesting tag here called spawn, which is parameterized by a continuation task. So it takes a reference to a continuation as input. And then I have a definition of a task here. It's just taking some ID as input, and then it's printing its ID, and then it's suspending, and then it's printing its ID. Okay. So here's what the scheduler for this would look like. So first, again, as we had before with the generator, we have some local setup. What I'm setting up here is I'm just declaring some local variables to handle the next continuation to run, or next thread, if you like, in this, or task in this analogy. And then I have this whole scheduler loop here, which is really interesting. So like before in the generator, I had a loop to sort of keep looping around and handling the next continuation. This is the same thing that's happening here. But now you'll see I've layered two blocks on top of each other. I have on-spawn and on-yield because I have two tags I can handle now. And then inside the on-yield, that's when I actually do the resume. I'm saying here, if spawn happens, then jump to on-spawn. If yield happens, then jump to on-yield. And just get the next continuation and run it. Then if we are done, we need to check if the queue we have is empty. So I'm assuming a queue somewhere. if it's not empty, then we can just we just dequeue the next continuation from there, and then we branch to the schedule next, which is going all the way up here and then running the resume one more time. If yield happens, then we fall through to, have I animated this? I think I have. Oh, well. Then we fall through to this block here. We jump to this block here, where we first enqueue the continuation that's on the stack. Then we dequeue from the continuation queue, and then we schedule again. We jump back. Okay. Same with on spawn. We have we have actually two continuations here. We have the payload we got, and then we have the continuation arising from the suspend itself. So here we set one, and we enqueue one, and then we branch to schedule next, and we run around again. Okay, so that's how we could do a scheduler. And this is called BFS because it's going to actually schedule your tree in breadth-first way, if you look at our concurrency graph. All right, so here's how we might glue it together. You have a main task. It's going to spawn 4 tasks, but there's a slight problem here. It doesn't type check. Why doesn't it type check? Well, if you look at the type of task, it expects an ID as input, but I have given no ID here. Like, my task C here is of unit to unit. So it's not good. So what can we do about this? Well, one thing we could do is I could sort of thread the parameter around. That would be one way to do it. But I've just written all this code, and it kind of sucks to have to rewrite it. So can I do something else? Yes, I can do something else. And this is where comp_bind comes in. So comp_bind allows me to partially apply a continuation. And it has this signature here. It's parameterized by 2 continuation types. CT is the type, is the source type. That's what I'm given. And CT prime is the type that I'm transforming my continuation into. Okay. So I'll have some sigma zeros on the stack. I consume those, and I give you, and I have a continuation reference of type CT. Then I give you back a continuation of type CT prime. So I try to line things up here to show you. CT has this type here, and then CT prime is the same as CT, except I have consumed the prefix. Okay. So this is a way to sort of change the type of a continuation, but it doesn't run the continuation. It just sort of pushes the arguments down to it. Okay, with that in mind, you can write code like this instead for the main task. So you see here I've introduced a new type alias also for an I task from like I32 to unit, and now I'm going to transform an I task into a task. And I'm going to give them IDs, initial argument 0, 1, 2, and 3. Okay, and if you run this, it should print this sequence here. So that will tell you that they're not all run in straight line sequence. So let's just try to run this also. I think I call this LWT. Boop, yes. And that should be the sequence. You see 0, 1, 2, 3, 0, 1, 2, 3. So that's been some interleaving in between. If there were no interleaving, you will have seen 0, 0, 1, 1, 2, 2, and so forth. Okay. Almost at the end here now. So one thing that we often don't talk about with this, but I think it's a really key feature of it, is that it allows you to do modular composition. So now we have 2 things we have defined so far in the talk. We have a generator, and we have a lightweight threading scheduler. Okay. So one way we could compose them is what I tried to draw in this picture here. Is we could have like our scheduler lightweight threading at the outermost level, and then inside that I could run my 4 threads, and each of those 4 threads could run a generator. Okay. If I do that, then it will print the sequence 55, 55, 55. So I think I have that. Now we need multiple modules because I'm using previous code, and then we need LWT gen, this one here. And I think I called this compose LWT gen. Yes. Okay. So here each strand, each thread has run a generator, and the gen effects or control attacks that's happened has been handled by each local gen handler, and the yields and spawns have been handled by the outermost scheduler. Okay. But there's another way we could layer this. We could do this instead. We could have the generator at the outermost level, and then have the scheduler inside that. What does that mean? That means now each of these threads here contribute to the generator, to what we're going to sum up. Okay, so it gives us a different semantics. The only thing I changed here is the order in which I call things. I have not changed like the logic in the code. And if you do this, so this is compose gen LWT. Now I get another number out, and I get only a single number now because now only the generator is only invoked once, and it's the one that's printing. and it will give me a 190 now. So yes, so that's another way. So that gives you modular composition, which I think is a key thing that it's very hard to achieve with many of the others I talked about earlier. Right, last instruction I'll talk about is resume throw. So it's basically like with resume, except that we now have an exception tag that we inject into the context. And otherwise this is the same. And we have some kind of payload to the exception tag. With this, you could do something like this. I think maybe you could do thread cancellation. So if you just want to get if the first thread that finishes, then you might want to clean up all the other ones if they had some resources or stuff they were closing over. In our example here, there's none, but we can imagine there are some. Then this is what you'll insert in the scheduler loop. So when you're done, you enter this cleanup loop instead, and then you do a try catch, and then you resume throw inside there. So you are called the exception cancel, and it will inject the cancel into the continuation, and then they can run that and clean up. Technically, if I wanted to be really safe here, I would need to add some tag list here to bind the yield and the spawn also, because locally the continuation could handle the cancellation by spawning a new thread, if you like. But you can do that. And also, I'm sorry, Ben, people will know and some people will not know, this is really old exception handling syntax in WASM. It's not what it looked like today, but this is the state the reference interpreter, and we have not updated for a while with the exception stuff. But yeah, so there'll be some minor syntactic changes to that, but that's what it is. Then what you can do is, if you take the example from before where we composed the lightweight threads with the generators in each strand, then you'll find that instead of 55, let me see here, I need to use the one that has the exception in it, and then I need to revert this order here. Then only one strand gets to complete, so we only see 55 printed out once. The other ones have been killed. Right. Okay, so the very last thing I want to talk about is what is the power of this thing? And here is sort of an attempt at sort of trying to characterize it a bit abstractly, so looking at some reduction relations here for control. So I have here changed the syntax a little bit. I have a suspend that's parameterized by continuation, and then it will continue with the term m. And then my resume is now taking one of these cont objects, which is subscript by the context that's been captured. That's the notation I'm using here. And it doesn't really matter if this is called by value or called by name. This is called by name I've used, but it's just because it lets me write less. But it doesn't really matter, and we don't need that for this discussion. So that basically what I'm going to do now is I'm going to say, okay, if you're going to look at what can we encode for this thing, we could look at how do we interact with the context. Okay, that's two things we could do. At either the suspend or the resume, and that leads to 4 different options. The first thing we can do is that when we suspend, so this is what I call abortive capture, when we capture the continuation, we could erase the current context we're in. That's what this line here is doing. You say here, I suspended the context E, then I'm just going to continue as M in a blank context, okay, with the continuation, with the context I've captured. And then when I resume, I'm resuming some context E. Then what I'm going to do is I'm going to erase that context, and then I'm going to install the E prime that I had captured and continuous with M. This gives you some semantics that's kind of similar to what threads are doing. It is what I like to call double abortive. So you abort context both when you suspend and when you resume. Another thing you could do is that you could abort when you suspend. So this is what's happening here. We're in some context E. We capture that E as a continuation, but we run M in a blank context. But what we could then do, we could be composable when we resume. So instead of aborting the context we're in, the E here, we now splice the captured continuation with the current continuation, the current context. Okay, that's what's happening here. And this semantics here, this is what effect handler, shift reset, control prompt, all of them I showed earlier, I think, they do. This is the characteristic reduction for those. Then you could also do this thing here. You could have composable capture. So beforehand we were aborting the context, but we could actually also leave the context in place. And that's what I'm doing here. So I suspend in some E, but I leave the E in place. And then I verify the context and give you a continuation to that context. And then we could compose when we resume also like we did before. Okay. Then the final option. Oh yeah, I should say, this is like what in Racket what Colbert the composable continuation do. This is exactly the equations for that. Then the last thing we could do is we could say we do composable capture and abortive resume. So it means like when I capture the continuation with my suspend, I leave it in place, but when I resume, I erase the current E and install the E prime that I had captured. And this is what CoreCC does. Okay. So there's something funny going on here. I want to draw your attention to. Don't know if it renders here, but I've highlighted these in red here. And you'll see up here. So this E here appears twice on the right-hand side. It's a bit weird. And also down here. So when I capture the continuation, I have a copy to the context that I'm running in. That's basically what it says. And that's not the case up here. And it turns out that I think this is where a lot of the wacky behavior for CoreCC comes from. Because what you can do if you have this is you can actually, from one-shot continuations, encode multi-shot continuations. So you can get multi-shot continuations for free here. Why? Because the semantics is already giving you that. I've not said anything about the shotness, the one-shotness and multi-shotness of these operators here. But there's a paper from POPL'24 that shows how to do this by Freeman and Haynes. It's called Constraining Control, where they suggest that you argue for that. Let's just have CoreCC1, where you can only invoke the continuation once, because, hey, it's enough, and they then give a construction for how we can construct CoreCC from CoreCC1. But that means when you do this, what you lead in through the back door is also you get all the wacky behaviors with multi-shot continuations and linear resources, even though you only have one-shot continuations. Okay. It also means something else. It means that the effect handlers and shift reset and whatever we choose as a basis and what we're running with cannot encode these because there's no way to simulate an extra copy of the context up here. Likewise, CoreCC, if it can simulate effect handler shift reset, but only if you have state in the language, which WASM has. So this will be able to simulate this up here. Okay, so we in some dimensions we're less expressive than CoreCC, and in other dimensions we're more expressive if you remove some of the language. Yes, Phil?
So you've given us 4 semantics.
Yes.
Presumably you pick one of these.
Yes.
I guess I'm picking the one which you let the other 3 in.
No. It's purposely not for that, because of the reason I'm saying down here. If you pick the 2 of the latter ones here, now you can get multi-shot continuations from single-shot continuations, and that can lead to. No, we don't want that. We want to keep the linear view of the world. Right, it's number 2. This is the effect handlers one. This is the one we run with.
The most powerful one that remains single shot.
Yes, and with this one here, you get. You can, this is the thing that any paper you read after the 80s will have done. Okay, so this is what I think people agree on. This is sane semantics. This one up here is interesting. This is basically, if you read a paper from Verleisen, also Verleisen C basically has this semantics. Okay, but we want to avoid this situation here where you inadvertently can copy your context. And it sort of also sheds a little bit of light on the power of CoreCC, I think, and I think this is only known as folklore in the literature. I don't think this is widely known. You can look at this paper. There's no proof of the construction, but I think I have a proof of it. But a conjecture for now. But yeah. Yes, Sam?
Worth pointing out that if you do have multi-shot continuations, then the second one is able to express everything.
Exactly. That was a question from the back also? No? Sorry. Yes. Okay. I'll do that.
You got mine.
Yeah, got yours, yeah.
Just a quick question about the last construction. Do they somehow have to reify the stacks on their own? Because don't multi-shot continuations require copying stacks?
Yes, they do. But in order to implement CoreCC, you need to copy the stack already. This is the insight, I think. This is where I get it from. Yes, but when I saw this first time, and I was a PhD student writing up my PhD dissertation, I was like, oh, this was mind-bending. But I was like, I'm writing up, I better stash it to the side and not look too deep at it. And then I went back last year to look at it, and yeah, it's kind of interesting. But it's kind of clear, once you understand the construction they give, it's quite easy to see why it works. Okay, but as Sam said, if you have multi-shot continuations, you could do all of them. And that's one of the extensions we could do. And we have a clone extension that take a continuation and give you back two copies of it. Another thing we could maybe do is that our resume blocks are unnamed. By that I mean like there's no way to refer to the exact resume you want to hit in your ambient stack. We could do that. We could give a name to them and then pass that name down. And then what you'll do is you say, I want to suspend to this particular handler. Then you go to some particular place in your ambient context. That'll be one way. And that gives you some kind of generativity also now, which we don't have with our approach. If you wanted that generativity, we could also do first-class tags. And by that I mean like we could give some way of generating them dynamically, and then match them dynamically, and then be able to pass them around like tags. And this is actually, if you know OCaml, that's what they do in the OCaml implementation of effect handlers. But we could do that. And with that, I want to finish and leave you with this resource list. And here is the link again. And if you're interested in any of this, please find me, and I will be happy to talk with you about opportunities and things here. Thank you.
Yeah, we already start running into the break again, but I think we can extend a little bit for more questions.
Thanks for a nice talk, Daniel. You began motivating this by showing Asyncify, the current state of the art. And you said, oh, look, it gives you this really long thing. So have you rewritten a version of Asyncify where the target is your new language set, and is it suitably smaller?
Yes and no. I've not rewritten Asyncify. It is on the to-do list to do. It's just it's a lot of engineering work. What we have done, though, is we have done experiments where we have, in C, we have defined like a fiber interface, so you can spawn different stacks. One is backed by the wasm-fx instruction set, another one is backed by Asyncify. And there is a massive code size difference in that. So yes, we shrink quite a lot, and that's also unsurprising given that we add primitives that are not there before. But yes, so we've done that experiment. It's on the to-do list to do the thing you suggest by actually taking Asyncify and then swapping our instruction set instead.
I mean, it's even worse, right? Because your function didn't even have any control flow, right? All this blow up is on every level of control flow, right? Every basic block basically has to do all this mess,
So I didn't implement this yet. It's on the top of my stack to implement. But one thing that concerns me, since we don't have linear types, is that you create a continuation. We have a little tiny garbage object. I can see implementation-wise, it's actually easy to reuse this continuation object in the same type. But that requires another resume instruction. Have you thought about that?
Another resume instruction. It requires you to be able to tell what state you're in.
Suspend instruction. Sorry.
Suspend instruction. No, I don't think it requires another suspend instruction. You can do this entirely in the engine. This is at least what we're doing. So in our implementation, we reuse the stack underneath. We don't actually create a new continuation every time. What we do create is that we bump a counter to tell whether or not what version of the continuation are you in. So when you actually invoke a continuation, we're going to compare two numbers and check if they are.
I'm aware of that one. The stack resource is separate in mind. There's a continuation object, which is a small thing, and the stack is the big thing. And you can actually reuse the little continuation object too.
Yes, with a fat pointer.
But without using a fat pointer.
All right. Okay. Then I'll be happy to talk to you. We are using a fat pointer. Yeah. Okay. Yeah. Well.
Hi. So. I think one thing that the Asyncify approach could give you, I haven't tried it, so I'm not sure, but I think it could give you a way of being safe in the face of Stack Overflow. You keep a counter on the depth of your call stack, and when it reaches a certain value, you stop here and go all the way back to unwind the stack, and so you can have a handler for catching this kind of
to catch those stack overflows.
And so you could avoid it, right? So you could make your language Stack Overflow safe, right?
I suppose that is possible, yeah.
So could you do something like that here, or it's not possible at all?
It's not something I thought about in the source language at all. It's something I thought about in the target language, and there we do have checks to check that we don't overflow the stack, and if we do, we either crash or we expand the stack. Yeah, but I've not thought about it in the terms of can I do this in my source language?
I see. Yeah. So can I compile a language to WebAssembly using wasm-fx in a way that doesn't have Stack Overflows? Can you have like segmented stacks or something?
Yeah. So that basically that's what we have in the implementation. We do segmented stacks.
You have this?
Yeah.
Oh, okay.
That's what we do in the wasm time implementation. Yes. That's exactly what we
So
do.
this is something specific to your project, or is something about WASM in general?
All right, that's specific to this project, but not really, because Wasm Time already had it. We just reused the
Can you remind me what WASM Time is?
Wasm Time is an engine for Wasm developed by the Bytecode Alliance.
Oh, okay.
Yeah, it's a production-grade engine.
Okay.
Yeah.
But if I run this in the browser, then it won't actually be able to...
I don't think Wasm Time will run in the browser.
No, but
yeah.
do you think eventually browsers will have Stack
Yeah.
Overflow safety?
Yeah, I think so, yeah. I think,
Okay.
like, I hope V8 will pick some of this up.
Oh, okay.
Yeah.
Cool. Very nice. Thanks.
Yeah, so Sam said that this has already been implemented in V8 for the JS promise integration. Yeah, thank you. There's always some form of stack switching in there, but they do not have an implementation of this instruction set yet. I hope we can figure something out in the future. Yes.
Okay. I think we should leave people into
Yes.
a break.
Thank you.
Thank you again. Jenna. We continue at 2. Yeah. Okay. See you back then. Thanks.
Yeah, thank you.
Test. Check. 1, 2. You put it to 1, right?
Yes.
Test. Check. 1, 2. Testing. 1, 2. Audible level. Check. 1, 2. All right.
Should we also check this one? For this?
Sure. Testing. 1, 2. Check. 1, 2. All right.
All right, good.
Goody gumdrops.
we have a double length cable running to the back with a repeater, and it's apparently not.
What's the exact time right now?
2.
2. Let's give it 1.
Lucas, you're looking like you're falling asleep right now. You're really struggling. Okay, everybody, welcome back. So this next session is about... Come in. So one of the things I'm particularly proud about regarding WebAssembly is the fact that it's fully formalized, right? So most of you here are probably aware of that. The complete formalization is part of the official specification, right? And as I like to put it, it's actually formalized really from the first byte of input to the last bit of values in memory, like really end to end. And that, of course, was a lot of manual labor going into that and a lot of work going into mechanizing stuff. And just last year, we have kind of, some groups have gotten together and started a great new project about making this better. And there are at least 2 lines of work that flow into this, and we're going to hear about both of them in this session. The first one is by Philippa, and after that we will have Suk-Young showing the other side of things. So, Philippa.
So, hello everybody, and just to say that's not quite the right description of what my talk is going to be, but by the end of my talk, you'll go, yep, that's what he meant. And I've been wondering whether to take my coat, have my jacket or not. It's too hot. I'm channeling Simon Peyton-Jones by taking off the jacket almost immediately. Or jumper. So I've been working on mechanization of language standards for really quite a little time, using the Koch theorem prover. And it's sort of, I don't even know why I'm doing it. In the sense, I mean, it's brilliant, the area. I'm from Edinburgh. I knew Robin Milner. I very much have that in my bones, but I'm not a Koch theorem prover expert. I rely on others to do really, a lot of the work. But I do have opinions, and sometimes those opinions have some effect sometimes. And so I actually want to point out Rao here. You have to look round and be embarrassed, because he's through his PhD has learnt the Koch theorem prover and has been part of that, and had lots of help from many people, including Conrad Watt down here, who's the mechanization guru for Watson. So you know what WASM is. I'm not going to say. Let me just point out there was the draft, and now we're on WASM 1.0. And Conrad, he knew about language mechanization from being at Imperial, and then moved to Cambridge, and he did some mechanization that had real effect on that draft specification that I think people probably know. And because of our previous interaction with the Koch theorem prover for mechanization of the JavaScript standard, Conrad and I came together to work on this WASM-Koch mechanization with a huge number of people. So this is Jean Pichon, this is Martin Baudin, and they're doing different things, but both in their way quite Koch experts. So some of this is their story, and then we veer off after a while. And there's a huge amount of work that's gone on from that basic starting mechanization. And well, huge, but mechanization is quite hard, so we're really doing quite well in terms of we've started. But I only want to put, and there's these awesome guys doing lots and lots of stuff. That one's just nodded. But I actually want to pinpoint this one today, because what Conrad has done is a fast interpreter that's verified correct in Isabelle, that's used for as a fuzzing oracle by the Bytecode Alliance. And so, that's getting right embedded in the heart of things. And so then we were going, yeah, but what about WASM-Ref for the Koch theorem prover? And why might we want that? Well, it's all about what does it mean to mechanize WASM well. And in particular, the way Conrad was doing it was totally the right way from the point of view of Isabelle, but there was a lot of work and repeated work happening. And what does it mean to go to WASM 2.0? Ha, we've got type safety, he hasn't, he's got lots of work to do. So, that's not at all fair, but at the same time, it's, this is about how do we do this in a way that we can keep up with the standard we're clinging on by our fingertips sometimes. And what Conrad did from the reason why it's fast, two reasons. One to do with he has better evaluation contexts, so he's not wasting work by having these more optimized evaluation contexts. And he's using mutable arrays to get speed up in action on the memory. But now we're in Kochland, having said how awesome Conrad is. And in particular, we've got an old interpreter that we've had for a long time. And basically, the idea is you run in one step. You've got a configuration consisting of WASM store frame list instruction, and it does a one step to one of these guys, meaning either it goes to another configuration, it just does that one step, or it's saying, nope, no more left to do, we now got a value, or no more left to do, we're crashing, or you have intermediate results associated with break and return that I actually don't need to talk about at all in this talk. We can stay extremely simple, but there is this other stuff going on there that, of course, we've done. So this is old interpreter. And we've got, we have to do quite a bit of work. So we've got two type soundnesses, preservation, progress. We've got the executable interpreter function, and we've got the soundness of the interpreter with respect to the operational semantics. So that's the sort of old way of doing things. It's a very normal way of doing things. But we were asking our question, oh my goodness, we've got to go to WASM 2.0. How on earth do we do it, and can we do it in a way that we get more efficient? And we can. And there's different versions of answers of what it means that we can do it. And the first way comes from Phil Wadler, and he's the only reason why we were going anywhere near this stuff, because he sent us an email asking us if we could do what he'd done. So basically, here's preservation, and I think it's folklore, but Phil's grabbed it. which is that one can oscillate between the two and end up getting an interpreter. If we've got a configuration that's well typed, we can either do a step or we terminate. And if we do a step from a well-typed place, we get another well-typed thing. So we can go round again and keep on going and getting that interpreter. And so in particular, Phil Wadler says, progress and preservation gives a sound interpreter for free, because that's how Phil is, and I am trying to channel a little bit. You see, I'm even a bit embarrassed having done that. It's not and in particular, so there's a quote, and he says, does this work for our WASM proofs? So that's how we got started, and how we got started with an absolutely awesome MSc student who is here. This guy, Stefan, who alas has gone. So before we worked with mechanizing these 4 separate things and channeling Phil, we just mechanized 2 things, which is preservation and progress. And then for free, we get both the interpreter and the soundness of the interpreter with respect to the operational semantics. And just to do the flip side of that, there's also Adam Chapala going, oh yeah, is this the right way of doing things? But Phil's take would be, absolutely, yes it is. These proofs are beautiful and it is the right way of doing it. And let's see. So absolutely, I mean, Phil's right. You know, it is great what he's done. And in particular, you have less line count. And the point, it's much easier to maintain and add new features. And this is sort of where we're trying to think. But question mark, because I'm sure Phil has some opinions, that the existing proofs make it slow. I think you can get better and better with that, and I think Phil's been part of getting better with that. But in particular, we are in this extrinsic types world, and we do have to carry around the typing, the proof of the types. So we are having complicated stuff happening in the proofs that maybe Phil doesn't need so much. And in particular, we want real control of this interpreter because we want to make it fast like Conrad. Yeah? So we want to change the evaluation context. We want to change the data structure. How do we go? So in particular, the question is, can we control the interpreter definition more directly whilst keeping these proof maintenance properties? And then here's the Phil approach, which we just described like this. Preservation progress gives sound interpreter for free. And instead, we are doing something different. And in particular, we've got fancy interpreter. And fancy interpreter implies progress. Preservation is off to the side because of non-determinism. It's a different thing. One can start arguing about what it does it mean to actually combine them and all that, but that's a sort of different story, not for today. But so fancy interpreter, what does it mean? It's you've got a dependently typed interpreter and its sound, and then the implication is saying it gives progress for free. Fancy can mean complicated too. So, you know, it's one has the caveats of all that. So here's the old way of doing things that I ran through with you. And here's the new way where you integrate soundness as you go with respect to the interpreter, and then the progress comes for free. So here is the first thing to think of, that basically, we're in this world of doing one step, and for example, if you do the one step and haven't continued, you end up in a place where you've doing a step in the operational semantics, and this is this certification is rolling along with the definition. And in particular, it's rolling along with the definition, and we're using dependent types, because here we have this ES, and we have to know that we've got a proof that it's making sense with respect to the operational semantics. Similarly, for values. Now, can anyone think of the most simplest interpreter you could define? Simplest, easiest sort of. Sorry?
That satisfies this.
That satisfies that. Yes, got it. So you can have an interpreter that does absolutely nothing except for crash. And so we have to understand what's happening in the crash case to make sure that we've got this nice interpreter. So when it crashes, you're not going to get the configuration typed. We're in this extrinsic world. If it crashes, the types have gone wrong. And so this is sort of another way of saying, actually, we've got that progress proof if we've got this. Yes, because when you've got a type, it's either in that case or in that case. So here we're in the case where we've capturing that in the crash way. And actually, the MSc student, Stefan, we hadn't got it quite right with the old interpreter, and we'd over-crashed. And we got it right by even doing this. Oh, and by the way, Conrad hasn't done any crashes. Yeah, he said that I could say that. Yeah, no, he does too many because he hasn't done it. This bit he's not done. he let me say that. Yes.
So I'm really glad you got some way of classifying when crashes can occur. That's very important. I'm surprised at that one because shouldn't preservation guarantee that you never crash? Should things always remain well typed?
The interpreter accepts an untyped program as input. So the point is the crash case is only hit.
Oh, I see.
We're extrinsic, you're intrinsic. Yeah?
Okay.
Yeah.
Very important point.
Yeah. So given these, what we had before, now we put up our hands, we've got preservation separately because of non-determinism, but with our fancy interpreter, if it's well typed, then this stuff comes for free. And it is the case that this is complicated, yeah? I mean, Ralph would say it's beautiful, yeah? So it depends a little bit on what head you have on, but it's no doubt it's more. But we get a lot because we have a direct way of having the runtime performance, and moving to WASM 2.0, we're going to be able to. And we're going to, just like with the fill approach, you've just got more structures, more expressions, so you have to handle those cases. It's not all intertwined with the proof derivations. But here's where I brought up the intrinsic versus extrinsic. So this is a good way of doing it because we've got the extrinsic WASM semantics. And I think there's quite a bit of discussion that's been happening of whether one should be intrinsic or extrinsic. No, WASM is extrinsic, but one can argue that there's some beautiful stuff going on with intrinsic. And this guy is saying, oh yeah, really, dependent types, not very nice in Coq. And the point is, I think one can accept some of that, but in another way, with that struggle, thank you, Rao, we have still managed to win in the sense that I will show you. So we've got some lemmas shared between all the different ways of doing it. So the infrastructure's all shared. And then we've got the old interpreter way of doing it. And it's this many lines of code of the Coq stuff. And then we've got porting the fill way to us, which is fill wins. This is the smallest number of lines, and there's something beautiful about that. Phil wins on this slide. But then there's now, what about can we do fancy things? And in particular, the awesome MSc student, Stefan, did this one. And look, the lines are about the same. But actually, don't forget, we've got this stronger interpreter where we've also proved about the crashes. So that's not quite fair to say that. And now, in Rao's optimized representation, we're doing quite well, and the interpreter is quite optimized. Now, what do I mean by that? He's done the Conrad trick of getting better evaluation contexts, hasn't yet gone to the better data structure, and which is the better data structure and the appropriate thing for the cock world, we'll find out. You know, it's not so clear. And that's, Isabel has a good monads library. You know, so we're only beginning to do benchmarks and thinking about this side of it, but, and in particular, we're not on the memory side, so we're really just on the basics. And for this one, we're on Fibonacci. And in particular, in the recursive case, in terms of execution time, this is Phil. Hello. This is Phil. And this is Conrad and us. So Isabel and Koch, with tiny improvement on the Isabel, but hardly. And now we go to the iterative Fibonacci. This is Phil, and this is us. And in particular, this is Isabel. This is where we are at the optimized place. I think Rao is contented, and that's actually a very good thing. That's a standard. And anyway, just to drill down into this a little bit, it's just to say, so this lot is there. This is Phil. And in particular, Phil is at least quadratic. And so where is that going, and why and what's happening? And especially if one's in an intrinsic world, then you know, some of the stuff is done beforehand because everything is typed. So then in that place, what does this turn linear? We don't know. We would love to unscramble this by the end of the week with Phil. I think that's the plan. So this has been just this tiny thing of here's WASM mechanization. We know that you know, getting the definitions is one thing, but then actually doing these proofs, it's sort of at the MSc PhD level, but it is you know, there's quite a lot of manpower going on. And so what does it mean to hook this up to the standard? How does one keep able to engage with the standard and get mechanization embedded there? We're already doing very well because the standard is acknowledging our efforts and saying, well done, tick. But you know, how do we do it in such a way that WASM 2.0 comes quite straightforwardly, and we get this efficient reference interpreter, etc. So this is the normal way of doing things. We've got the WASM community basically creating the implementations, creating the pros, etc. It feeds into what the specification is going to be and with the formalism, etc. And then all that lot's done, and now we come along and have a play with our particular mechanizations and then start doing the PLE things in terms of analysis. And in particular, Conrad lucked out, but lucked out because he was good, which is that you can do a feedback loop and actually really, really affect the specification if you were lucky. So, and that's what happened. But that's only, you know, the sort of start of the story. The real challenge is, what does it mean for that lot to continue? And even without Conrad falling down with exhaustion, or whatever it might be. So I think many of us in this room have been trying to understand what's it mean to make this lot better. And in particular, what it means is sort of really evolve getting, because we're in a PL conference, getting formal methods embedded in this standardization process in such a way that it's easy. I think that's the point. Of course, it's embedded already. So let's just take a little bit of look at what's going on with the standard. You've got formal specification. Well, there's a couple of two experts here. How many others do it? I don't know enough about the ecosystem, but there's not going to be many. And there's prose descriptions. Well, you have to understand that. So then you have to do some boring prose. And test suite, I guess, you know, that's many people can start thinking about that. And the OCaml reference interpreter. I have a feeling some obvious suspects are doing quite a lot of work. And it would be very nice if some of this could be done better. And it can. First, and we're off to the side. You know, never mind, we've got a bit of a loop. But this, you know, the mechanization is off to the side. It's either there or it's not. Doesn't matter. We would like to try to see, understand better. And what's happened is that there's a new game in town, and I'm going on to the next slide because I think it's easy. There's a new game in town, which is these guys. And it started because of a Dagstuhl. Was it last year? Last year's Dagstuhl, huh? And we ended up on the last evening having wine in a tiny little room and thrashing some of this stuff out. And basically what happened was Suk Young was at the beginning of the Dagstuhl saying, I've done JavaScript standard. I know how to take JavaScript prose and push it to have an interpreter and work with automatically with the standard. And then she said right at the end, I wonder whether we could do something for WASM, but it has to be the other way. Or, you know, with a bit of a chat, it was, yeah, but it's the other way. But basically what was extremely amazing was that Suk Young at the beginning of the week went, I have a gang of people. And it was, whoa, how does this gang of people get used? And nicely used. And that's turned into this lot. And basically what we've done, starting with Andreas, is create this WASM domain-specific language. And so basically, Andreas, what he's doing is you've got code, but you've got code with annotations. And the idea is that the annotations give enough information that for free, we have the formalism, the prose, the testing, the interpreter, and the mechanization definitions. And in particular, do it in such a way that coders who like standards, and especially the WASM standard, can be part of helping here and not too irritated by annotations. Yeah, so there's actually sort of quite a fine line as to what that design space should be. And I think it's fair to say we're on the way that rather than really, really know. But we do know in the sense that there's a whole story to tell here that is Suk Young's story that's going to happen, Suk Young and others' story that's going to happen any minute. Yeah. So before then, let me just put this bit in just to finish my part of the story. So this is the old way of doing it, and now we've got a new way of doing it. And with the new way of doing it, we've got this WASM DSL with now the automatic generation of the things needed by the specification. And we've got the automatic generation of the definitions. For Coq, Isabel, Lean, Agda. So there's lots of people very interested, and there was some photos a while back. I'm not going to pinpoint everybody. And the point is, so I should actually put those other icons there now. Sorry, Sam, who is actor. The idea is we've got this sort of actually really embedded in the standard. You know, that would be really a cool thing, because developing these mechanized definitions is actually quite, it's labor intensive. And then kapow, what about doing the proofs and the analysis, etc.? This is really in research land. But in particular, one obvious question is we can automatically generate the mechanized definitions. Can we automatically also generate the proofs? That turns into real research now rather than the engineering thing of whether something like that is possible. And we have to do it in such a way that we don't kill the annotations here. Yeah? So this I think is a lovely research style question, not just what does it mean to embed language, to do language specification well, and in particular embed mechanization into that language specification. And of course, in the Cockland at least, we want to do it in such a way that the previous part, most of my talk, gets embedded in here so that we can do the expansion to WASM 2.0 easier, etc. Are we going to find that the dependent types are getting too much? Are we not? We don't know the answer to this. We're just going to explore. Thank you very much.
Yeah, thank you very much, Philippa. Other questions? Phil, obviously.
Do I get to rebut?
Uh-oh.
I think this is not a rebuttal so much as a clarification. So I don't think I ever said, this is the way to do it. I think what I said was, could you do it this way?
Yeah.
And how much would it cost?
Yes.
Right? And you said, it costs quite a lot because it becomes quadratic rather than linear. And in fact, we can explain very simply why that happens, right? If you think of a normal proof of
One thing I can remark on, by the way, is you keep talking about WebAssembly 2.0 and how do we get there. WebAssembly 2.0 is in the past, right? That's 2 years old at this point.
Okay, so just to say, we have got the types on this stuff, and now we're on the interpreter. So we are there, and he isn't.
Yeah, so if Philip is behind, I'm super behind. But I'd also say if we want to say WASM 2.0 is current, we need to finish actually publishing it as a W3C standard.
That's not our fault, and that's not. Right, but what I wanted to say really is that the step from 1.0 to 2.0 is actually relatively minor. What we have done in the meantime is a much, much bigger change and extension, and that is where we really have the litmus test of this scaling up. Anyway, okay, let's move on with Sukyoung telling her part of the story. The other half of the story. Where are we going?
Yeah. Hi, everyone. I'm Seokyoung Ryu from KAIST, and the title of this talk is Generating Executable Specification from Formal Semantics of WebAssembly. And Philip already gave you a high-level idea about our SpecTech project, and I'm going to touch on some about it, and then talk about this executable semantics. And this work is with my students and all awesome people. You're going to see some pictures you've already seen again. Okay, so everything started last March at Actual. So someone here know me from JavaScript. And actually, Christian was looking at me this morning, and he was like, why are you here? This is not about JavaScript. Our group has been working on JavaScript for like 15 years, and we are sick of it. And I'm going to talk about that in a minute. And Sam one day told me, like, have you heard of WASM, WebAssembly? That's really cool. You may want to apply your technique to WASM. And I was looking, and he talked about this in a talk show, I think. And I looked at it, and I just sent an email to Andres. Oh, I'm interested in this talk show, and I've never worked on WASM, but can I attend it? And he was like, yeah, bring your student as well. Oh, that's nice. And in the morning of the very first day, Andreas gave this timeline. And I was like, oh, very good. Because on that day, this afternoon, I showed this slide. This is about the history of JavaScript. Until 2015, there was just one pretty big, let's say 879 pages of the specification. And since 2015, the spec is released annually, every year. So like Philippa and the other people who, including us, working on JavaScript, we need to read these 800 pages every year. Doesn't make any sense. So we were, and this is the Thursday of the talk show, and Conrad was taking a picture, so he's not here. But you can see Andreas, Philippa, Mattia, Pierre, Joachim, Luke, who gave the first talk today, and my student Dongdun, and Sam. So we discussed this idea, and when I gave the presentation of this, Andreas started writing DSL, DSL for WASM. It was amazing. So I was so happy to see. I have to really enlightened and happy to see this awesome language called WASM and awesome people who are working on this. So we were happy. And Andreas gave this keynote last year in September at ICFP. The title was As Low Level as Possible, but No Lower. And he showed this picture, right? Everyone in the previous picture with 2 more students of mine. And it's okay. And we've been happy with applying this. And as many of you already know, when you want to add something to this WASM standard, you need to provide 4 artifacts. The first one is formal specification written in LaTeX. And the second is, Andreas thinks this is the best. But developers may not think that way, and they prefer some prose. So this is prose pseudocode description, and Andreas usually called that like COBOL style, or translation from this beautiful LaTeX to some prose specification. And not only these two descriptions, but also you need to provide reference interpreter in OCaml and unit tests for the feature. So these all 4 artifacts should be provided. Then my students, our team has been working on everything for JavaScript in Scala. And now we need to implement things in OCaml. And there are some new bits, but they were happy to learn those things. And another thing is that the current status is that developers, they need to write and read and review differences of the versions or new features in LaTeX. And you know how LaTeX works, especially with errors. And it doesn't check anything for you, right? So Andres wrote this beautiful picture. And the beginning is this DSL, domain-specific language. That's going to be the single source of truth. That's going to describe the semantics of WASM, only once. Then, out of that, we can generate LaTeX description. We can generate prose specification. We can even kind of generate interpreters. It's a meta-level interpreter. I'm going to talk about that later. So you can run WASM code in the interpreter that's correct by definition, correct from construction. And then there are lots of mechanizations that Philippa already talked about, right? So this is the big picture. And we have yes?
You had 2 check marks there, a line between them. Oh, 4 with 2 lines. Can you explain what those are?
Yes, thank you. So usually when you say semantics in prose, then we check that whether our interpreters or whatever implementations or runtime implementations correspond to whatever said in the in the specification. So that's kind of the correspondence check. Usually, let's say when you have a JavaScript specification and when you have JavaScript interpreter, then usually you check the correctness of your implementation by running test code. Lots of test code. So this is like when those 2 things, like implementations and prose specification says the same thing, then we say, okay, they're good. They are talking about the same thing. When you have LaTeX, then you usually check that with proofs, with mechanization. That's what we call by this. And when we just describe the semantics using DSL once, and you generate those mechanization automatically, then that's going to be correct by construction.
Thank you. The one thing I don't understand is why you're comparing the tests with the prose backend when you compare the tests with the interpreter.
Oh.
Since I made the slide originally, maybe I can answer that. So the idea there was like, usually when you have a language definition, right, that's just some text, maybe some LaTeX. How do you know that if you mechanize it or if you implement it, that is in any relation to what was there in textual form? Here, that is by construction because it all gets generated from the single source of truth. So whenever you prove something about your implementation, run the test suite, or do proofs about the mechanization, doing real proofs in Coq, then this actually gives you some assurance about what actually appears in the printed spec, right, as well, because it all comes from the same thing, and they really correspond to each other, and you know that because it's a mechanized construction, not something you kind of translated by hand and just have eyeball correspondence on. That was kind of what this tried to convey.
That the Coq theory there and the LaTeX will be the same thing.
Yes.
But why would we know that the test suite is distinct?
It's more
so basically what is called AR there is some internal representation in this tool. So it's kind of like a compiler-like tool pipeline. And that's called algorithmic representation. And that's what we generate the prose from, right? So it's basically an abstract syntax tree for the prose. And that's also what the interpreter interprets. So the interpreter, this meta-level interpreter, interprets the same thing that is then kind of pretty printed in the actual spec. So when that succeeds against the test suite, then basically it means that what is written in the spec succeeds against the test suite.
I see. Okay, thanks for the clarification.
Future reference, we can pass the next one.
Oh, yeah, sorry. Yeah. No. So again, this blue background is done by Andres. Yeah, that's from his keynote talk of ICF P9. Yes?
Explain that AR is
So the question is, AR is not Andreas Rosberg, it's algorithmic representation. Thank you, Ben. Okay, so we wrote a very brief 4-page description of this big vision, WASM spec tag, engineering a formal language standard. It's available as archive. And our team has been working on this algorithmic part, as Philippa already said. I'm going to show you the picture later again. So this is all based on our experience with JavaScript. So this was published at ASE 2020. And again, we started with this ECMAScript, the prose specification of JavaScript. It's written COBOL style, the semantics of JavaScript. One, do this. When you have E1 plus E2, number one, evaluate E1, get the value, call it N1. Number two, evaluate E2, get the value, call it N2. Three, evaluate N1 plus N2 and return it. It's more like pseudocode, but one difference, maybe one of the many differences from WASM spec is it's big step. Big step semantics using the values and more high level. But we can discuss the difference later. So from this specification, we extract the semantics automatically. So actually, we generate the parser and the interpreter from the mechanized specification and generate the whole tool set. So this is an excerpt from the reviewer number 3. Reviewer C from this in the paper, he said, can you possibly go backwards and generate the documentation from your derived model, right? That way, the documentation can be more precise, and the standards committee can use your model to design new versions of the language. I believe that this is the right order to design and document languages. First, the semantics, then the implementation and documentation, ideally generated from the semantics. So this reviewer, saw the future. And we wanted to do this from 2020, but there were so many JavaScript bugs not even going to this direction. So we had all lines of toolset from GSAT. So as soon as we have mechanized spec of the JavaScript semantics, we could generate test data, a lot of test data to find real-world bugs in JavaScript engines from major browsers. And because the usual coverage metric is not enough to generate lots of test data for language semantics, we had more specific test coverage for language semantics. And we also generated a static analyzer from the spec, and and type analysis of the specification, and things like that. So we've been happy with this JavaScript work, and even our work has been officially integrated into TC39. So now every feature of JavaScript is now running our tool, the spec checking and test generation. So that's all good. But the thing is, as Philippa said before, students graduate, right? The main student, Ji-hyuk Park, is now an assistant professor at Korea University. And now that he's an independent researcher running a team, we are like, OK, you can take the JavaScript work. And anyway, we are sick of JavaScript, and we are looking for a new target. And then again, Sam introduced WASM to us, and we moved to WebAssembly. And now JavaScript is with Ji-hyuk's team. Then WASM semantics in the specification. As you know, it also has formal semantics and prose specification. Again, this one is binary operator again. Then let's look at it. Number one, assertion. WASM has validation, static semantics, unlike JavaScript. Number two, pop the value from the stack. And we were like, my students were like, what is stack? Pop. Number three, pop the value from the stack and do this binary operation. If that's defined, then do this, otherwise trap. What? So WASM was really different from JavaScript. So we had to understand the semantics. And the formal specification is the usual Greek letters, right? So OK, we are happy with this. So let's compare this JavaScript and WASM. As Philippa said, it's the inverse order. With JavaScript, we started with this prose specification and generated some mechanized specification. And as Andreas explained really well, the semantics is represented in some DSL. For JavaScript, we call that IR, Intermediate Representation for ECMAScript, IRES. So the semantics in the ECMAScript spec, like evaluate E1, get the value N1, call it N1, all those things are now described in IRES. And when we interpret the semantics, that's going to be an interpreter. So when we get the JavaScript program, and that the interpreter, the meta-level interpreter, is automatically generated from, we wrote the interpreter of the IL, then that's going to be an interpreter for JavaScript, right? Then we also generate parser automatically. So those things are all automatically generated. We get the result. But with WASM, that's the other way around. Now, Andreas wrote the DSL. That's going to be the single source of the truth again. And the WASM semantics is going to be written in DSL. And so with this WASM 1.0 and 2.0 and now 3.0, so Andreas rewrote the semantics previously written in LaTeX to DSL, right? Then we can generate a parser as well, but we didn't. Why should we do? Because it's already there in the reference OCaml interpreter. So we reuse that. But we generate this AL interpreter. We extract the semantics from DSL to our algorithmic representation. That's going to be DSL to algorithmic representation compilation. I'm going to talk about that in a minute. Then we have this AL interpreter, and that's going to be the whole thing about algorithmic part. So now we are finally kind of achieving the goal that reviewer number 3 envisioned in like 4 years ago. First, the semantics of WASM in the DSL, and then generate the implementation and documentation from the DSL specification. So our dream now came true. So again, here is I'm going to show that white small box later in a bigger font. So that's the semantics of binary operation in DSL. And Andreas also wrote parser and checker for DSL. Remember, if you write the semantics in LaTeX, if you missed some argument, if you have some typos, LaTeX doesn't find or doesn't check it, just make some errors, right? Or just generate some PDF with the errors. But now that we can have the semantics as a data, right? We can check it and we can do some more analysis on that. That's all IR. So if our repository is available, so you can see that in the actual implementation, there's EL and IL and various levels, but you don't need to know about it. We call it just DSL and algorithmic representation AR, right? Then Andreas also wrote this LaTeX backend. So we call these backends because the semantics is written once, and all the others are automatically generated. So LaTeX backend, prose backend, interpreter backend, and mechanization backend. So here, because the designer of DSL made that way, the translation from DSL to LaTeX is very close, one-to-one correspondence almost, right? So you can have this DSL in this operation semantics way. And this is our AR, algorithmic representation. I'm going to talk about that in a minute. From this, we can generate this prose specification, and we can also make some tests. So again, this is that small, the top small white box. That's this. This is DSL, describing the semantics of binary operation. Here we say, so it's a binary operator. When you have C1 and C2 and binary operator, then if binary operation has some value, then you have this semantics. If not, there's a trap. So there are two versions of the semantics. And this one is going to compile to LaTeX. Then you're going to have this LaTeX backend showing this. Right? So this one is automatically generated from this DSL. Now, one thing to note is that if you look at this, these are just if conditions. When you write some operation semantics, you have some conditions or premises in inference rules, right? So this one says if binary operation of C1 and C2 and its result is C, it evaluates this operation, get the result, and compares the result with this C. It's equality checking, right? And then this one just says binary operation doesn't have a value. So I'm going to show that more clearly here. This is our algorithmic language. This is just the same with these 4 lines in more complex to human eyes, but simpler to the interpreter or spec generator. It says, hey, this is the semantics of binary operator, and assert, pop. Now you can see why we made this way. As Andreas designed DSL close to operation semantics, we designed AL close to the prose specification of WASM. So this is different from IRES, because with ECMAScript, again, there are big step semantics. They're more high level. They use lots of auxiliary functions. If you ever looked at JavaScript semantics, just one simple evaluation of an expression requires like 10 auxiliary function calls, right? But WASM is different. So we had to, design this AL nicely capturing the way of WASM spec style. But at the same time, we should be able to generate interpreter and prose specification. So, let's look at these 2 if expressions. The first one is now, hey, evaluate this one, and then let's give the value C, right? One more time. So when you have this application of binary operator, you have this C1 and C2, and this is binary operator, get the value, and call that C. And here, when you have this binary operation of C1 and C2, and that does not have any value. So they are differently compiled. Previously, they looked just the same with if expressions, but now one is using left binding, and the other is using comparison. So there are those details. And this is generated prose specification from this AL. So from this, you can compile one by one. The assert pop now goes to assert pop, an if expression with 2 different compilation of if expression in operation semantics. One with left binding and using that, and 2 with just the comparison. So based on how that's going to be used, they are compiled differently from DSL. One single DSL instruction is compiled differently in AL. OK? So far, so good. So I'm not going to go into the details of how to compile them. But really high level, when you have these kind of inference rules, DSL describes the inference rules really closely. So it says there's a left-hand side to right-hand side. That's the inference, rules from left to right. And there may be some optional premises. Then how do we compile them to AL? LHS usually pop from the stack and give them names. And right-hand side is usually do the computation and push the value onto the stack. And in the middle is going to be the premises. It's really high level. And when you get to the compilation, then there are more details. So when we are done with this compilation, we wanted to check whether the generated meta-level interpreter works correctly, corresponding to the specification, right? The semantics written in DSL. So we checked the official test suite. We tested the extracted semantics against the official WASM unit test suite with this, on this machine. And the extracted semantics passed all the tests, SIMD excluded, in the test suite in 21 seconds. So SIMD, we think it's not that difficult, but a lot, right? A lot. So we excluded SIMD instructions, and just to have some high-level idea about whether this idea works, we tried it, and it worked beautifully. So wow, that's good. So we recruited 3 more undergrads. So Suhyun and Ho-sung, 2 undergrads, they were busy implementing SIMD instructions. And as you know, it all started last March, less than a year. Then you can see the code is not going to be pretty, right? And you may know that Andreas has high criteria for code quality, I think. So when he does some code review, my students are like, and very grateful. And they are learning a lot, but it takes time, right? So what we wanted is that, again, Dongjun he's one of my PhD students. He's really quick. And as Andreas wrote the DSL during the doctoral week, Dongjun just started writing the interpreter and AL definition from that week. But his code is quick and dirty. So Hyun-hee, the 3rd undergrad, she's now joining us for code reviewing and refactoring. She's impressive. 1 minute for something really different. She studied drawing when she was a high school student, and she wanted to do something cool using arts. And she realized that art school doesn't teach her how to make that more scalable. So she started to go to a college in the 2nd year of high school, and she studied hard. And KAIST is one of the best school in Korea, but she entered KAIST. Even with less than 2 years of studying. And she studied industrial design at KAIST, and she quickly realized that computer skill is needed. And she studied computer science in the 3rd year of her undergrad. And she went to an intern, and she realized that code quality of the real-world developers is really low. So without any guidance, she looked up clean code textbook, and she read it while she was an intern. So when I heard the story, you should work with us. So now Hyunhee just joined, and she's cleaning up the code of Dongjun, Wonho, and Jaehyun. I am so happy. So they are working hard. And now the current status is that they are done with writing the semantics of SIMD instructions, syntax, validation, and execution, everything. So that's all done. And they are reporting minor spec errors and getting some approval. And they also automatically generated LaTeX and prose specifications for SIMD. And with the official WASM unit test, 86% passes. The remaining 14% may due to our way of describing the semantics. We may need to change the DSL, but I don't think so. We'll see. And IL to AL translation and interpreter. As you can see, whenever we have some decision making, we looked at the current WASM specification and its way of describing the semantics and just followed it. But maybe that's not the best way to describe the semantics. That's a way that we chose, not we, WASM people chose in the beginning. So that's the thing that we are currently working on. And when we worked on this methodology, like in a SpecTech, the nice picture, why SpecTech? There are many language frameworks like K and PLT-Redux, OTT, and many others, right? So we did not want to, invent a new wheel. And we looked at K, and there were one repository for WASM semantics in K, and 2 repositories for WASM semantics in PLT-Redux. And all of them didn't really work. They were incomplete. And we have some discussion with internal people in K and PLT-REDEX and realized that they are not well suited for this, this style of semantics. I mean, K and PLT-REDEX, they have their own pros and cons. And SpecTech also has its own pros and cons. So it's not like one is the best and the other is wrong. It's more like they have different application domains, I think. So K and PLT-REDEX, they are rewriting engines, and they do not have algorithmic way of describing the semantics. They may, yeah, they don't, just don't, they don't. And our SpecTech, we want to have this prose specification with algorithmic, stepwise semantics. That's one thing. And now that we have this mechanized specification, we can generate test data. Wow. When we gave this presentation at WASM CG meeting, developers came to us like, when can we run your code, run your tool so that we can test our implementation? We had these errors that we wanted to catch earlier. And most of them were about SIMD. So at that time, you were like, oh, sorry, SIMD excluded. And now we have SIMD, like 14% left, but I'm pretty sure it's going to be done by the end of January. So then we can finally help them work on that. So back to this JavaScript word, because again, not the others. Mechanization, that's all Philippa and Stem and Conrad and other smart people. We are about this algorithmic part because we've been working on JavaScript in that way. So now that we have this kind of thing, we have WASM DSL designed by the king of WASM, and we can just trust that. If not, we can blame him. That's not us. And based on that single source of truth, now we can generate all these tools. So the first target is test generation, just like we did with JavaScript. So and the technical detail about Jest is what? From this mechanized specification in WASM, that's going to be the WASM semantics in DSL, we can generate WASM programs, right? And not like randomly. We know the syntax, we know the structure, we know the semantics, and we know which part of the semantics is well tested by the official test suite. We know weak points. We have everything. Right? So that's going to be the usual thing. We can generate programs from seed, and we can inject assertions because we know the semantics. And then we can have some mutator of the programs that's going to be guided by coverage metrics. Then we can find some errors in existing implementations. So that's West. So Jest is JavaScript engines and specification tester. West is WASM test generation. So this is what we are working on right now. Dongjun is working on this. Now the undergrads are cleaning up his code. So we built a WASM fuzzer framework. And for WASM 1.0 to 3.0, we can generate this .wast WASM test files automatically from the semantics written in DSL. And now for 2.0, we check that generated WASM modules are all valid. So in the beginning, only 0.1% was valid. So we had to add more stuff to filter out invalid modules, but now it's pretty high. And we can generate 10,000 tests in several minutes. And we found 2 minor bugs in some implementations already. And we measured the spec coverage of these 10,000 tests. It covered 100% excluding memory.copy and table copy. There are some issues, I think, in our implementation. Don't worry. We're going to look at it. And we are looking at it. Another thing is that even with JavaScript as well, the Jest paper was published in ICSI because it found really many errors. But we knew that there are more, but our Jest didn't find them. So we had to invent new kind of coverage metric for language implementation. Language semantics checking, testing is different from program testing. Let's say that. If you're interested, you can look at PLDI paper. So here we already see that, oh, the current metric is not enough to check WASM semantics. We have some bug reports from WASM runtime implementations, and we are pretty sure that our naive current West implementation cannot catch them. So we are looking at advanced coverage or guided test mutation in that word. And then we are going to find some bugs in WASM runtimes. So this is the current AL. If you look at this AL description, there's one-to-one correspondence in sentences in WASM spec. So we started from, actually, what Dongjun did in that doctoral week is to collect all the sentences in the WASM specification and translate them to IR, and then compile them, and then simplify that. That was the first dirty hack. Then he covered 100% like in a week. But that's not pretty, and that's not like actual core semantics of WASM semantics. So we had to revamp that. And this is the current version. But is this AL general purpose enough? Not really, because it's different from ECMAScript. And another question is, this is the interpretation, DSL for ECMAScript. Very tiny. And it's really high level. It uses lots of function calls. It's just like ML-like functions to describe the semantics of JavaScript. So JavaScript language itself is really weird and not good. But the semantic specification of JavaScript is pretty nice, right? So I think this is the final big picture of our group. When you write a grant proposal in Korea, we usually write this kind of picture. Draw this kind of picture. Maybe same here, I don't know. So my grant proposal says that, there's natural language specification for various languages. And we'd like to have this general purpose mechanized spec. In the proposal, I said that there's going to be one general language specification, but not really. Now that we think about it, again, this JavaScript and other languages are big step. WASM and other language semantics are small step. And some languages are more low level, like manipulating stack. And some languages do not know about stack, but it needs to take care of some other high level bits, concurrency, all that. So I don't believe that there's one single language, but we'd like to understand this better. Currently, we have only 2 instances, JavaScript and WebAssembly. And our grand vision is to have many languages. And another target is P4. As you know, P4 is this language for network switching. And so last year at PLDI, Nate Foster came to me and someone told me I should talk to you. And because P4 also has a specification written really nearly natural language. It does describe some semantics, but not really precisely, or I don't know. So we looked at that, and it's a whole new word. So we were not committed. We have not yet committed to it. But when you write a proposal, you can say whatever you want, right? So P4 is just one of the latest language. So Java, we only did JavaScript, and we are working on WASM, right? And we'll see. And the whole this tool generation is not like unique to us. Again, K does that. Other cool language framework manipulation frameworks do that. So what we are trying to do is that language semantics. That's going to be again, I'm speaking this too often, but the single source of the truth. And as a language designer, we do like to describe the semantics in a crisp way, in a precise way, so that interpreter implementations and those developers, in what sense of developers, they need to read only one thing and understand it and do other things. And JavaScript spec is released every year. WASM is growing. And whenever you grow your language, you need to do this manually again. So all we say is that it's not really technically complex. We do not use lots of Greek letters. All we say is that if each language language has its own DSL, right? Write for its own semantics and describe that, and the other artifacts can be automatically generated, then the lives of developers are going to get much easier. That's our hope and belief. And WASM is our second instance, and this was a very happy and lucky experience to us, because working on JavaScript for the last 15 years was not that pleasant. But working with this WASM community and people is really impressive. And the high-level standard of the way the specification was written and the implementation is manipulated, and that's all really high-level and well-organized. And we are happy to work on this thing, and this is all possible by all the WASM community. So our bit is, I think this is the last slide. Yeah, our bit is that algorithmic part, and everything is possible by the semantics in DSL, because they all started from the semantics. Okay, this is what we've been doing, and thanks for listening.
So there's lots of great work on generating interpreters, talking about how to generate interpreters. So the step beyond that, how are we going to think about generating compilers?
We cannot generate type checkers yet. And actually, after this talk, John Hughes, after Andreas' keynote talk at ISFP, there were so many people asking questions to Andreas. And during the talk, Andreas was like, "Oh, Seogyeong's team is working on this implementation. Seogyeong, how much percent?" And I said, 100%. And after that, his talk, everyone was asking the questions to him. And John came to me and asked, like, "Can you generate type checker?" And I was like, "No." We are only, I mean, the spec implementation, the interpreter is really nicely specified in prose. And we were just compiling that to AL. And type semantics is also written in prose, but in a very different way.
Well,
yeah.
Yeah, so the operational semantics, the prose of the operational semantics, kind of like algorithmic, like you showed. It's this step this, step this. The typing rules, the prose of that is really declarative. It's just like a bullet list of constraints. That doesn't give you immediately an algorithm, right? For WASM 1.0, it wouldn't probably be too hard to derive an algorithm from that, but at least with WASM, like what we have now, we have subtyping. Right, so you have transitivity and all that, and it's a well-known problem that generating an algorithmic formulation of subtyping from a declarative one is not trivial, and you usually have to prove cut elimination and all that. So automating that is currently way out of scope. So what we do, though, is we generate the prose for the validation as well, for the type checking, but there is no execution of that, right? We don't have any interpreter for that. So that's kind of, if you want, that's a bit of a missing piece there. Likewise, I think what we don't do yet, but could do, I guess, is generating the parser.
Yeah, parser is, yeah, that should be doable.
Yeah.
Hello. I don't know much about WASM, but just I was thinking about two sort of related approaches. I mean, in the instruction set architecture area and processor definition area, sort of Adam Chipala had a sort of similar plan about 6 or 7 years ago, so it might be worth talking to him about that. And I was also thinking sort of for specifying execution models and properties about that. 30 years ago, there were these approaches of particular SOS formats, GSOS, generalized SOS, probably Philippa, you know much more about that. But I was wondering whether this DSL format at the very top sort of has relationships to that, or whether that such structuring would help you sort of to derive additional reasoning principles.
DSL.
Well, yeah, so one thing I should perhaps explain is that the DSL itself really, it's very general in some way, right? It really gives you only a way to define syntax or data type, if you want, an inductive type, and relations. And then reduction relation is just one particular form of that we use for that. The typing relation would be another one. So on the DSL level itself, on the SpecTech DSL level, you don't really have a notion of reduction at all, or SOS. But then the later phases, in particular, that's where the animation comes in, and that backend makes a lot of assumptions about how to interpret these relations. And that is kind of like what we get out of this approach, right? So, I mean, the other question you could ask is, why don't we use something like ODD, which also is this form of DSL, which you can generate stuff from? Well, this is like doing our own thing, allows us to specialize the hell out of it, right? We can just cut corners wherever we want. We just need to be able to handle the cases we care about. And that means, especially in the back end, it doesn't have to really be able to handle the general case. And I mean, you showed the AL abstract syntax, right? That's totally specialized to what we use. Right, and which is not in the front end, actually. So there's at some stage in the pipeline we make assumptions about the structure of things and don't bother dealing with other things.
So two things to add is that one is to really understand the current status of the DSL and everything, we need to actually write that in other forms. So one of my students tried to rewrite the semantics in DSL in K and in PL2REDX. That's how we understood the differences between them, like the lack of some features in K and PL2REDX. And now he's defining the semantics of P4 written in Kwok and Isabelle in DSL, so that we can try to see whether DSL is enough to describe the even lower level of the semantics. And another thing is that Lucy and Amal and Luke and Andreas are working with this component model, and Lucy now has the formal specification of the semantics of component model, and one of my students is trying to describe that semantics in DSL again. Then now we are like giving hard time to DSL. And it's designed to be general purpose and really high level. And we believe that's going to be doable, but we will see how far it can go.
I mean, yeah, the DSL is in a way general, but also in terms of its feature set, it's just about what we need, right?
Exactly.
It doesn't hardwire any of WASM specifics, but in terms of the feature set chosen, it's just what we need for WASM. In particular, right now, there is no such thing as binders in the abstract syntax because WASM right now doesn't need it. So any language kind of semantics that has to do with binders will be a challenge, which is the case for the component model. But yeah, I think.
So thank you for a really inspiring talk.
Thank you.
Following up on what Andreas just said, so I don't know which of you to ask, but we were shown this exception handling thing this morning, which requires capturing the evaluation context. Does the DSL cover that, or will it be extended to cover that?
That's an excellent question. So that's one of the things we still keep discussing, like what to do about evaluation context. So right now, without continuations, we can get away with just having like this bubbling up semantics for branches, which are just breaks, and also exceptions and return, which are the three things. But with continuations, you can also formulate it that way, but it's kind of very tedious. You have to incrementally construct the evaluation context that represents your continuation. So basically, that's an open question right now, how we want to deal with that. And it might be that we want to build in special support for evaluation context, or we just say, like, okay, we just do this more cumbersome thing and be happy with that. I don't know. That's not.
So a different question. If you could go back to the slide where you had the DSL and then the expansion into English prose.
Not this one. Here?
Right, so there's the expansion into prose. So that will now be part of the spec, right?
Yes.
The generated spec. And then can you go back to the DSL that generates that?
Conrad, I'm not familiar with that Windows.
Let's just turn it back into presentation.
Thank you. And
that's somewhere there.
Here? Is that, this is AL, algorithm representation.
Right, but you don't write the AL, right? The AL is...
DSL, sorry.
Right.
DSL.
Right. So that is so much more compact than the prose or
Exactly.
the. So this is sort of a question about pragmatics. It seems like if I wanted to review the thing, I'd be much better off reviewing that than the generated prose. Is the expectation that eventually nobody's going to read the prose? Or why is the prose there when this is so much better?
So we have.
Yeah, I mean, I can say a lot about that, but maybe Thomas wants to say.
Yeah, he first.
Hi, I'm a software engineer. I work with a bunch of software engineers. They only want to read the prose.
Exactly.
They don't want to look at this.
I believe that. I understand that. But why?
It's got a big horizontal line, and it's got some squiggly arrows, and like, what is that? You know?
Could we do something that they read that's this compact?
Compact
Maybe,
doesn't
but they're
mean
also
the
happy
best.
reading the prose.
So Andreas wants to have only this version, and usually developers do not want to look at it and have only prose version. Everyone is different.
And I think I can say concretely, very confidently, WASM would never have got industry support if we didn't promise to write the prose. So there's a pragmatic thing of needing to give the people what they want, even if they're wrong.
No, I understand this is huge pragmatic thing.
I was just going to say, so yeah, I'm also a software engineer, and there's way more of us than there are people who speak this language. I tried my hand at teaching students this kind of thing with Jonathan co-teaching, and yeah, being able to speak the language in which the thing is written, would be English, and the generated prose is very handy. So people can actually, they can read it and they can step through it. It's only when they get to the level of maturity where they understand the beautiful notation, will this make sense to them, but they don't initially.
So I'm just going back to an earlier discussion. The thing about having a generalized specification like OT. I always make this point in these venues. We're not the only ones who have observed that actually specializing is pragmatically, essential at the moment. So Peter Sewell, who is somewhere at this meeting, he did OT, but he was also involved in SAIL, which is essentially doing the same thing that we're doing with SpecTech, but for specifying processor architectures. So.
And ASL, where it is even more specialized to just on.
Does SAIL have this bit of generating
Mike?
ASL, I think, that's just on off. So I guess again, that's about if you specialize, you can do more.
Philippa, you had your hand.
It was going to be this ASL comment.
Okay.
So coming from the mechanization hat on, often with these general purpose frameworks, you can automatically generate COC code or equivalent, but it's not what the people want, and it's not what those COC specialists want. So in particular, for what's going on with WASM DSL, it's absolutely to get to the place where it is what we want. We actually sort of know the target because we've done the work already. And now it's, can we back design to get what we need to then do the proof? And I imagine there's going to be similar stories in Seok-Young's world. I just can't pinpoint it, of if one went general, you could do this with respect to prose, but that's not the same as being specific to the particular target in hand. And actually, it will be quite good to pull out some of these ideas and sort of really grab at why staying absolutely in the WASM world for this DSL is really helping us. That's the thing.
On that theme, one difference here in the generated text versus like what we have today, for this binary operator example, is I think what we have today is like if binop of C1 and C2 exists, and then the generated text here, it says if length of binop of C1 and C2 is 1, right? So there's just like that tiny difference. Obviously, it doesn't make much of a difference. Is that So that is something you plan to change, make it more similar to what we have today.
Right,
Okay,
yeah.
cool. Yeah, I was wondering like how far are you going to go to make it exactly what we have today versus something that's
very close.
I mean, I would say the main balance is between trying to get as close as to what we have today, but also making sure the code base is maintainable. It should be the case that because we're specializing for WASM right from the start and always having that in mind, we should be able to get very close to what we have today. But not at the cost, I think, of building in 100 hacks that we then have to maintain in future. So I think it's not going to be the case that we throw the baby out with the bathwater to get exactly the same. But at the very least, things like that, we should be able to get the same without compromising on the rigor of our coding.
Right. So currently, there's almost no hack in generating prose, and we are willing to add some tweaks about these things.
I can imagine we'd even start out with a couple hacks so that's more similar, and then improve them over time.
Yeah, right. I mean, there are not that many differences.
Well, I mean,
yeah.
So, some of these things are kind of like syntactic patterns that are used in the spec right now, right? And they are so that you minimize the number of special constructs that the spec formalism needs, but there are certain patterns, and I think in the prose you spell these patterns differently because it makes sense, right? And I think the prose generator can, like, there aren't that many of those, I think, so it makes total sense to. Okay, I think we need to move on because we are already well into the break. But we have a very quick question, Phil.
It's not a question.
Oh, okay.
Historical observation. Just a quick historical observation. So I make this as an old guy, and it's somebody who comes from Edinburgh, so I have to point out the historical role of Robin Milner. So everybody will know Robin Milner's contribution to functional languages. They'll know his contribution to proof assistance. But maybe one thing that's relevant here that people might not know is if you go back and look, I think it's ICFP 1984, Robin gave a specification of standard ML. But it was written very much in this kind of prose style. And then later it was done as proof rules. But the first one was done this prose style, which the proof rules then compress. So that
That's old. That's like outdated. That's like my screen from before. I don't even have those tabs open anymore.
Nope. Wow.
Try plugging it back in. JP, let's try unplugging it back in. Are you seeing a second monitor? Yes. On this side? You are seeing a second monitor. But, okay, so it's on our
Is there any kind of timer on the laptop? Or should I use my phone?
Laptop, people have just been putting their phones.
Okay. Cool, cool. Yeah, no worries.
Yay, okay. All right, hello everyone. Welcome to the final session of the WebAssembly workshop. Thank you for sticking with us. Before I get to our final speaker, I just want to make sure that we have all of the Lightning Talk participants present in the room. So do we have Marco Vicenna, if you just stick up your hand, great. Do we have Aria Shrimpton? Great. And do we have Maxime Legapou? Great. Oh, and a late entry, not on the card, is going to be Andreas, who I believe is going to be talking about on the industrial side advances in the WebAssembly specification over the last year. Is that correct? Feature set. Okay.
So people are aware that we're way past 1.0.
For our purposes, 2.0 exists when it's published by the W3C. Just like to put that out there. So yes, again, welcome everyone. Our first and only timetabled invited speaker is going to be Thomas Lively, who's going to be talking about a brief tour of Binarian. Thomas is, are you senior engineer or super senior engineer at Google?
Staff now.
Staff engineer at Google. You heard it here first. So let's take it away, Thomas.
All right. Thank you, Conrad. Let's make sure this works. Nope. All right. It's okay. I'll hit the space bar. Oh, it's supposed to be plugged in? Okay. Well, hi, everyone. I'm Thomas Lively. I am, as you heard, a software engineer at Google. I'm on the WebAssembly tools team. Thank you. Great. OK. Where I work full-time on WebAssembly, which is like a dream job for me. So I'm super excited to have it. So this talk is going to be about Binarian, which is one of the open source code bases that I work in quite a lot. But I do a whole bunch of different WebAssembly things. So I also work a bit on Emscripten, which is the C++ to WebAssembly toolchain that actually predates WebAssembly by quite a bit. Used to compile to ASM.js and just normal JavaScript before that. And I'm also very active on on the spec side of things. So I chair the GC subgroup and the new Threads subgroup in the W3C community group. So I love WebAssembly, and I love being on the industrial side of WebAssembly. I love writing code. I love, having users tell us that their stuff goes fast. But I also love being here on the academic side, because I think all of the formal specification, all of the proofs and everything, all those Greek letters, I love that stuff. And I'm super glad that I still get to see it, even though I'm now in industry. So let's kick off a brief tour of Binarian. So what is Binarian? Binarian is first and foremost a WebAssembly optimization framework. All right, so it's an open source repository, C++ code. It's in the WebAssembly org on GitHub, so you can go check it out. It's sort of like existed as long as WebAssembly has. So it's an optimizer. It's a compiler infrastructure. It has sort of like a pass runner mechanism. You can write new Binarian passes and run them. It's a suite of other tools in addition to the optimizer, and we'll see those. It's also a C library, so you can embed it in other programs and call it as a library. And using Emscripten, which I mentioned earlier, we compile the code base to WebAssembly and wrap it up as a nice JavaScript library that's on NPM. So lots of different ways to use Binarian and get access to all the optimization goodness. So what do I want to talk about? First of all, I would like to convince you all that you should care about Binarian and maybe use it, and maybe, if I'm lucky, even contribute a bit to it. Now, Daniel Hillerstrom's group for WASMFX has been contributing to Binarian, implementing support for their new instructions, and that's been awesome. And I would love for more people to help experiment with new things for WebAssembly in Binarian. So then, presupposing that you care about Binarian, I'd like to go into a little bit about what you would want to know about it. All right, so what are sort of like the headline items in Binarian that you would want to know before taking a look at the code base? And then what are the opportunities in Binarian? Because it's a really exciting space, writing all these optimizations. And honestly, we're just scratching the surface. And I think that it could be a pretty cool academic project in addition to industrial projects to take these WebAssembly optimizations even further. So the Binarian tools are WASMOpt, that's the optimizer. We have an assembler, we have an interpreter, a disassembler. We have a linker, so you can take two WebAssembly modules and just smash them together into one bigger WebAssembly module, which is pretty nice. We have WASM split, which does the opposite. You can take one WebAssembly module and you can split it up into multiple WebAssembly modules. And that's pretty cool because we can use that for lazy code loading. So if I have a giant multi-megabyte WASM binary, maybe it's Photoshop or it's Sheets or it's some giant application, I can split it up into multiple modules using that tool and have them dynamically loaded at runtime as the functions are needed. So that's neat. We also have special purpose tools. So here's one called WASM CTOR eval. This is to pre-evaluate WebAssembly constructors. All right. So if you have like a C++ application, for instance, it might have a bunch of global constructors. We can pre-compute those and serialize the result as an output WebAssembly module. And then when you run it, you don't need to run those constructors anymore. They've already been run. And I know the Bytecode Alliance also has a tool called Wiser that does pretty much the exact same thing. We even have a compiler, WASM2JS, that does what it says. It compiles your WebAssembly to JavaScript. And we have WASM Reduce, which is a test case reducer. So if you find a WebAssembly module that triggers some bug in a tool you've written or your interpreter or your engine, you can throw it into WASM Reduce, and it will automatically use all of Binarian's optimization passes and other modifications to reduce that binary to something much smaller that still triggers your bug. So this is great for filing bug reports on things. So as you can see, it's pretty eclectic, and we're kind of happy to throw whatever tools we want in there. So if you think that there should be some tool for WebAssembly that doesn't exist, and you want to reuse all of the code we have in Binarian, come let us know. We're happy to throw your tool in here too. So yes, very large toolkit. And Binarian is also sort of a narrow waist in the WebAssembly ecosystem. So I have some languages here. You've got your C's, your C++s. You have things like Python and PHP and Ruby that go via C and C++, via Emscripten to get to WebAssembly. You have purpose-built languages like AssemblyScript and Grain that compile to WebAssembly. You have your Javas, your OCamls, your Haskells that go to WebAssembly. And every one of these languages, in some way, uses Binarian, all right, in their tool chain. For a lot of them, it's optional, right? Binarian is a WebAssembly to WebAssembly optimizer, so you can always just not run it, right? You start with WebAssembly. You want to end up with WebAssembly. You can just not run Binarian. But when you're compiling with optimizations enabled, if you run Binarian, you just get all that optimization goodness that we've developed basically for free. So some of these languages, like C and C++, using Binarian is optional. We only do it in the optimizing tiers, or optimizing compilations. For other languages, like AssemblyScript, Binarian is actually their entire compiler backend. So they're using Binarian.js, and their front end calls directly into it to emit WebAssembly in the first place. So for them, it's mandatory. But either way, we're happy if you use Binarian. So what do you get when you optimize with Binarian? Your performance of your WebAssembly modules can increase by around 2x. And this is the number specifically for the J to WASM, so Java to WebAssembly benchmarks. And your code size will go even more down, 4x. And this is after we do an initial dead code elimination. Then all our other optimizations will reduce code size by 4x. If you include that initial dead code elimination, then it's actually 9x. So this can make a huge difference for your code size. So there's a huge toolkit. It's really good for your binary size and performance. Everyone uses it. And it's very well maintained. All right. So this is the sort of GitHub contribution stats over time. You can see it starts way back in 2015, and it's basically just been going steady ever since. I think the huge spikes at the beginning are because we were not squashing the commits. So there's like a lot of commits back then. But you can see basically every week since then, we're averaging between 10 and 20 PRs or commits every week. So it's a very active project, and it's very up to date, right? So all the latest features that are standards track have been implemented. We have GC, we have threads. We're going to have shared everything threads. We have exception handling. We have the old one. We're working on the new one. And as I mentioned, Daniel's group working on WASM-FX, the effect handlers. So it's very up to date. So you can take advantage of that too if you work with it. So OK, that was kind of the end of my this is why you should care spiel. So hopefully you're hooked. So what are some interesting things about Binarian? First of all, its intermediate representation might not be what you expect for an optimizer. Binarian's IR is an AST. All right, we're not using SSA, and we're not using anything else. It's not even a stack machine. It's an AST. So this WebAssembly fragment here, i32.const1, i32.const2, i32.add. Even though in WebAssembly that's a linear sequence of instructions, in binary and IR that would be a tree. So we would have an expression for the i32.add, and it would have two expression children, the i32.const1 and the i32.const2. So why is that? Well, it's a historical accident. You see, way back before WebAssembly 1.0, there was a period of time when WebAssembly was going to be an AST. And binarians from way back then, and we just never changed it. So you can see there's this nice issue from August 4th, 2016, Future of Binarian in a Stack Machine World, where such various options such as deprecate binarian were considered. So yes, there was a lot of hand-wringing back in 2016 about what we were going to do. And it turns out the answer was just keep on trucking. So we didn't really change anything in binarian. And it's worked out pretty well for us so far. Yeah. Well, so with a few caveats that I'll go through now. So for example, multi-value. All right, multi-value was not in the MVP WebAssembly. It was added later. We mostly support it. But we got to fit it into an AST. So if you have a block that returns not one but two i32s, how are we going to represent that as an AST? With these tuple things. So this WebAssembly turns into this binary in IR with a block whose child is a tuple.make instruction, which does not exist in WebAssembly. This is only in binarian. And that tuple.make is the parent of i32.const1 and i32.const2. And of course, when we emit a binary, we just skip the tuple.make. It doesn't exist, and everything works out. But now all of our optimizations kind of need to worry about tuples and the fact that they can exist. So it is a complication. Second, sometimes we need scratch locals. So here's some perfectly valid and very short WebAssembly. It pushes const1 onto the stack, calls some function that doesn't return anything or take anything, and then it executes i32.eqz, which, because our call didn't modify the stack at all, pops the i32.const1 off. No problem. Well, when we parse that into binary and IR, it needs to be an AST. So that i32.eqz needs to have a child that produces that i32.const1 as a value. But we can't reorder things in general because this call might have side effects. So we have no choice but to introduce a scratch local. And so binarian's parser will produce this IR. The EQZ is the parent of a block that we've synthesized, where the block contains a local.set to a scratch variable that we've synthesized of the i32.const1. Then it executes, that shouldn't be a NOP, that should be that call. And then it does a local.get of the scratch local to then produce that i32.const1 value that can feed into the i32.eqz. So between turning stacky code into this monstrosity in the tuples, sometimes the IR can be seriously bloated compared to your input WebAssembly. So that is definitely a downside of using the AST intermediate representation. On the other hand, we don't need to redo years of work by keeping it, so it's a trade-off. Another fact about binary and IR is that it keeps the types around. Okay, so this is unlike WebAssembly itself, where the instructions aren't all annotated with the types. In binary and IR, every expression has a type. So here, they would all be i32. Pretty simple. But if we change this to be the unreachable instruction, which traps, then in binary and IR, we assign that a type called unreachable, which does not exist in WebAssembly. So in WebAssembly, if I have an unreachable instruction or an unconditional branch, the types it leaves on the stack are polymorphic. You can pretend they're whatever you want. T star, for any T star, which means after an unreachable or an unconditional branch or any other instruction that never really returns, in normal WebAssembly, we're allowed to have any instruction we want. And we want to sort of emulate that behavior of allowing any instruction we want in binary and IR. So we introduce this unreachable type, which infects all the parents. All right. So because this expression is unreachable, that makes its parent unreachable, et cetera, et cetera, et cetera. So this one's still I32, but this add is now unreachable. And that tells us that the add will never return. In fact, it'll never be reached, but it also won't return. So yeah, our type system, we have tuples, and we have unreachable, and we also have a none type. So this call that doesn't return anything would have none type in binarian, which also doesn't exist in WebAssembly. So our choice to have this tree structure does introduce a few oddities and things that don't exist in the underlying WebAssembly.
The question was, how is none different from unreachable as a type?
Yeah. So none isn't infected. Like, it doesn't infect the parent. And it's also not allowed to appear anywhere except inside a block. So like a drop instruction, right? Drops its child and has type none. It doesn't return anything. The only place in binary and IR that you're allowed to have a drop is either like at the top level, like your whole thing's a drop, or it's inside a block where blocks are allowed to have a sequence of none-typed expressions, potentially followed by a concretely typed expression.
So it's more like a unit type, not a bottom type then?
Correct, yes.
So
yes, and again, we're software engineers, so we would never be confused by that, because we don't know what bottom types are. Yes. Although, yeah, so obviously now that we've implemented WASM-GC, we do have heap type none, which is the bottom type, and then we also have type none, which is this other completely unrelated thing. So, yeah. So, all right, that's all I had to say on binary and IR. It's a little weird, but it gets the job done. So let's talk about sort of like, what does binarian do with the IR? All right, so at its core, binarian is just like a dumb pass runner. All right, you register a bunch of passes, and then it runs them one at a time. And each pass has the IR, and it can do whatever it wants with it, and then it ends, and then the next pass runs. And really, the only constraints on what happens in a pass is that it must leave the IR valid. So we have a validator that runs in between passes if you're in debug mode. And as long as that passes, as long as the validator passes, the passes can do whatever they want. So usually what they want to do is walk the IR. All right, so they want to walk this tree and perform some analysis or make some modifications. And so we have all kinds of utilities. We're very into our shareable utilities in binarian because we've got dozens and dozens of passes, and they all basically want to do the same thing, which is walk the IR. So if you'll excuse the C++, this is an example utility that's going to collect a list of all of the expressions of a particular type. So it's called finder, and it's generic over some expression type t, and it's going to collect a std vector of pointers to t. So t might be binary. Okay, binary is the class representing all binary operations in the IR, or it might be unary, or it might be some crazy SIMD class that represents some niche SIMD instruction, right? We have a few dozen of those. So, or it might be a local get, or a struct get, or whatever. Finder is a subclass of this postwalker utility. All right, this is the reusable part. And so postwalker is going to be this generic thing that knows how to walk the IR in post order. Notice that as a template parameter, postwalker takes Finder itself. So the superclass has the subclass as part of its bound. So in C++, we call this the curiously recursive template pattern, but you all might like to refer to it as F-bounded polymorphism instead. I don't know what that is, but you might. So yeah. And then we also tell the walker how it's going to visit each expression. And notice that also takes Finder. So there's more F-bounded polymorphism there. And because this is a unified expression visitor, we're going to visit every single expression with just this visit expression method. All right, so what you don't see in this example are the implementations of postwalker and unified expression visitor with like hundreds of lines of just like very repetitive, like if it's this kind of expression, call this visitor method. If it's that kind of expression, call that visitor method, right? We get to share all that code and we don't need to write it every time. And then what's this visit expression going to do? It's going to be called for every node in the IR. And it's going to be generically typed as expression, which is a superclass of all the different expression nodes. And then what we can do is we can do a dynamic cast on it to T, right, which is the expression type we're actually looking for. And if that succeeds, we can add it to our list. So relatively small amount of code to implement this basic utility that's just going to go find all the particular expression type. And we do this all over the place. Like we have dozens and dozens and dozens of subclasses of postwalker and visitors and all sorts of things. So if you do anything in binarian, you'll definitely see this. So building on those walkers, we can build entire passes. So here is a real example from our code base. We have a pass called optimize instructions. This is our peephole optimizer that just looks at each instruction, looks at its children, and tries to simplify it if it can. So this is a walker pass, which is parameterized with a post walker of optimize instructions. Right? So there's that CRTP, F-bounded polymorphism again. And the interesting thing here is that we have this method. This is a virtual method, is function parallel, and we just say return true. So that's all I need to do to make my pass massively parallel. So my workstation like exists up in the cloud somewhere, and I'm working on it every day. And it has something like 128 cores, right? So whenever I'm running a binarian pass, if it's function parallel, it's just going to use all 128 cores automatically. It's just going to split up all the functions between them. So this is great. And then all I need to do to make that work is tell it how to create an instance of the pass for each thread, and the sort of like part where it splits up the functions and runs it on each thread, totally taken care of for me. So it's pretty easy to write passes that are walkers that do whatever you want in binarian IR. So I want to talk about what's like the latest and greatest in binarian. What's the cutting edge? So we have this project to add a monotone framework to binarian for static program analysis. So if you're not familiar, this is static program analysis sort of like theory in terms of lattices, which I've beautifully illustrated here, where the lattice represents what you know about your program. So the top of the lattice is like anything's possible, I don't know anything, I give up, this isn't useful. And the bottom of the lattice is the most specific possible thing you can know, which is that like nothing is possible, right? They're like, that's it. So I can just optimize the whole thing out. And then the cool thing is individual facts about the program are different points on the lattice, And so the combination of individual facts about your program is the join of those 2 points on the lattice. And there's like nice theorems and stuff about how if you start at the bottom and then find new facts about your program, you'll reach a fixed point as long as it's like a finite lattice, and that's too strong. But anyway, yes, you can reach a fixed point, it'll terminate, and you'll have a sound analysis. So we take our lattice, we take our control flow graph, and we can actually give each block in our control flow graph its own little lattice. That is going to be a component of this single huge lattice that we're doing the analysis on. And then so here's an example that I'll run through. This is actually, I chose this example because it's the only one in the code base so far. So, it's a work in progress. As I said, this is the cutting edge. But we're going to try to find the most general type required at each program location, with the goal of generalizing the output type of casts far enough that it is a super type of the input type and we can get rid of the cast. All right. So that's what we're working on.
Is it okay if I add a clarification?
Yes.
This is for the garbage collected types feature, which actually adds object types to WebAssembly. So we're not just casting from I32 to whatever.
Yeah, right. This is for WASM-GC, which actually has subtyping. It has casts. Like, this is a real thing I want to do. My users have asked me to eliminate their casts, so I'm going to try. So I want the most general type, and I want to know the type that's required at each location. So this is going to be a backward analysis because requirements come from the future, and I need to track the type for each location. All right. So first, I would design a lattice for this. So here's the lattice for val type. You can see it has our fancy type none, which is not a bottom type. It means literally no type. That's up here at the top. And our type unreachable here at the bottom, below the actual sort of like bottom types for each individual hierarchy of types from WASM-GC. So here's our type lattice. We're clearly going to use this, but we're going to invert it because we want the most general required type. So as I discover more program facts and sort of go up my lattice, I actually want my type to become less general. All right. So I've inverted the lattice. And right over here, this is literally the C++ type that I write to represent this. So we have a library of general purpose lattices like val type and inverted, and we can compose them arbitrarily to build up these bigger lattices. So then I need to track the type for each local in a function. All right. So I'm going to add the vector lattice to wrap my inverted val type lattice. And this creates a new lattice where each element is a vector of a particular size. That particular size will be determined by the number of locals in the function. And it's like sort of the lattice you would expect from vectors where elements are compared element-wise. And then similarly, for the stack values that aren't in locals, I can have a stack lattice where the bottom is the empty stack, which is secretly an infinite stack of bottom elements. And the top is, for example, this one in this picture, where the stack has nullref, and I32 at the top, and then an infinite sequence of bottom elements. And again, we can compare it element-wise without actually, rectifying the infinite sequence of bottom elements at the bottom of the stack. And this all works out, and it's a proper lattice, and it's exactly what we need for our analysis. And then I can stick it all together with the tuple. So I keep track of the locals. I keep track of the stack values. And that's like literally all the code I had to write for that. And then the rest of it is defining the transfer function, which takes a basic block and one of these lattice elements and just traverses the basic block, updates the lattice element, and then returns a set of basic blocks that may be affected, may need to be reanalyzed. And that's it. So this sort of framework where I can compose these lattices and then write transfer functions is, I would say, the cutting edge of where we're at in binarian. So it's not like we invented this stuff, but it's awfully fun to implement. And I think there's a lot of room for us to take it further. So in particular, we haven't done all the lattices we need for interprocedural analysis. So that's next. We could use a smarter pass manager that shares these analyses between different passes. Right now, every pass just also performs whatever analysis it needs. It's kind of slow. I'm currently working on a new text format parser. Right now, just like binarian's IR is a little different from WebAssembly, the text format it accepts is a little different from WebAssembly too. It only accepts the nested form that matches the IR exactly. So I'm fixing that, which will let us upstream all of our binarian tests as spec tests in the future. Yeah, so that'll be nice. C++20 added generators so we could, or coroutines that we can use to build generators, so we could use those instead of the crazy CRTP stuff for our walkers, which would be very nice. And of course, we want to implement more proposals as they come down the line. So all the proposals that we're working on will definitely get implemented in binarian. But if there are also proposals that you're working on, like effect handlers, then we'd love to get those implemented in binarian as well. So this, as I said, open source, contributions very welcome. That's it.
Thanks, Thomas, for that talk. So questions. I'm going to bias against the other organizer.
Thanks. I think this is a kind of obvious question. You mentioned
we've definitely thought in the past, like, oh, should we add a second IR? Should we, change the IR? Should we make changes? And the conclusion we've always come to is no, because despite the annoyances, there are benefits, right? It's really nice to be able to just look at an expression and then look at its children and say, okay, those are the values it consumes, and that's where they come from. And like, that's it. You just followed one pointer, end of story. So that's pretty nice. The fact that the post-order traversal of this tree just corresponds to the exact code that's going to get output is also pretty nice. And the way types propagate up the tree, like that unreachable stuff, right? It just propagates up. Very simple, pretty easy to understand. So I think there are benefits in how simple it is and how easy it is to do some kind of analyses on it.
Andreas.
Now I'm curious again. So how do you represent the cases that don't fall into this like more structured AST form?
Okay, for one example is multi-value input to blocks, and we don't support that at all.
Okay.
Which is unfortunate.
I mean, another example is you have multi-value output, and then you consume it kind of in a non-structured fashion, right?
Right. So we had those tuples that I showed. So tuple.make.
Yeah.
So your output from the block would be like tuple.make. I package up a tuple. I return it. On the outside, if I consume it in a non-structured fashion, then I'm going to assign that tuple to a scratch tuple-typed local, and then use tuple.extract on the local everywhere I need it, and blow up my output code.
One other quick question. So you mentioned upstreaming your tests.
Yeah.
Like how many tests are we talking about here? Like
Well, so you're not going to be inundated with tests. I'd say the new parser will let us start writing spec tests that are upstreamable. Right now, in binarian, we have very robust testing, and only one of our testing directories is called spec, and it has sort of like modified versions of the upstream spec tests that are like n years old, right, and have been like munged so binarian can understand them. So it's going to be new tests we put in there that are now going to be upstreamable. We also have a ton of other tests that use the LLVM lit testing framework, where you sort of just like have an input file and the output that you expect is in comments in that file. So that's like completely unrelated to the spec tests. That's the majority of our tests. Those won't be upstreamed.
Can you tell me a little bit more about how your test case reducer works? Like, do you have like a user-defined function that can say it still fails or passes?
Yeah, exactly. It's pretty dumb. You pass it a like arbitrary command as a command line argument, and it just like calls system and like runs that command and sees if the return code has changed. I think it looks at the return code and standard out and standard error and sees if they've changed. Yeah.
So do you try to go back to a more compact form after expanding into the AST form, which may require more nodes? Do you guarantee that you will always find back the compact form if nothing changed?
Yeah, so in the happy case where there was no multi-value and no stacky code in the input, then the IR actually has the same number of instructions really as the input. There are a few details, but then when you emit it, it'll be sort of one for one. In the unhappy case where there are multi-value things and stacky code and we need all these scratch locals, we do our best. And obviously it's an optimizer, so the whole thing is about trying to get the code size as small as possible. But we don't really have a great intermediate state between the IR and the emitted binary where we'd be able to do those fix-ups. So if we need to bloat the binary or the IR with like tuples because we simply can't represent it any other way in the IR, then right now we're pretty limited in the amount of cleanup we can do before we go to binary. We do a little bit, but no, there's no guarantee that it's going to be better.
So then could it happen that overall the code becomes slower because of this blow-up?
Yeah, you could easily construct a sort of terrible input binary specifically constructed to become slower, but sort of like for all practical cases, that's not going to be the case. Yeah.
Kind of follow up on that. Is it at least true that you can convert every program back? Because like this tuple binding you mentioned, it seems to be more expressive. You could use the same tuple component several times, right? Which you can't easily translate back unless you introduce more locals, I guess.
Right. So because it's an AST, everything only gets used by its parent, right? So everything's only used once. So if I wanted to reuse tuple components, that would involve storing the tuple to a local, and it would be a tuple type local, which then when I emit the binary would become a scratch local for each of its elements. Yeah.
So I sort of want to ask the dual of the previous question. So you've said you get this 2 times speed up typically.
Yeah.
What sort of things are done that are so, in the code that's given to you, that are so inefficient that you can speed them up by 2 times?
So that's
what typical optimizations end up happening?
Absolutely, yeah. That stat was specifically for J to WASM output. So J to WASM is a Java to WebAssembly compiler. The team that works on it actually calls it a transpiler. So we benefit there. Like we can look really good because their front end is not trying to do anything fancy at all. All right, they're not doing any optimizations. They're just taking the source code, like emitting WebAssembly in the most trivial way possible from that, and then we take care of the rest. So that 2x is like totally standard stuff that like any optimizing compiler would do. Even just like dead code elimination, and now there are fewer branches, right? Or, we do a lot of more sophisticated things as well. So we'll analyze the WASM GC types across the whole module, and if there are unused fields, we'll get rid of them, all right? So we're modifying the types. What we can do is we can pre-compute some things. So Java code has tons of vtable lookups where it's like taking the object, following a pointer to get the vtable, following that to get the function reference. If we can like look at the types and determined that, hey, this type always has this vtable in that field, and this vtable always has this function in that field, we can pre-compute the whole thing and just have that function reference. And then we can directize it and make it a direct function call, which is way faster than an indirect function call. And then we can inline it. So all those things. Inlining is a big one. And that one's interesting because the engine, right, V8 in the browser, will also inline. So it's a trade-off. How much do we inline versus how much do they inline? If we inline too much, the code size blows up, and that's no good. If we don't inline enough, then we're leaving performance on the table. So it's a constant back and forth.
So you mentioned it was implemented in C++, and you apologize for that. Thank you. But I'm wondering to what extent that was a good choice or a bad choice. Would a different language, in retrospect, have been a better choice, or is C++ a really good choice? And if so, what features of C++ make it that?
Yeah, I think C++ is it's a pretty decent choice. Of course, pragmatically, it's a great choice because my entire team knows C++, right? That's very pragmatic. I'm sure we could learn other stuff if we had to. We talk with every so often about like, hey, should we introduce some Rust to this project? Because we all want to write Rust instead. It's like C++, but way nicer. I don't know what you're hoping to hear. Yeah, we would not consider OCaml.
Just because nobody's trained in it?
Nobody's trained in it. I had like one OCaml class. I read the textbook. I mostly forgot it. I sometimes do stuff in the reference interpreter, but Andreas knows not even that much. Yeah, we just don't know anything that's not C++. Right, and yeah, so like we're at Google. Everything we do is open source. It's on GitHub, so there's like lots of rules that don't apply to us. But in terms of like having talent and being able to like hold a conversation with other people at Google, like we have to have some similarities, and part of that's the language we use. In some cases, yeah. The question was, is Google adopting Rust? And like for some things, very niche things, yeah.
So I have a provocative question.
Yeah.
Do you ever worry that Binarian is now too central to the WebAssembly ecosystem if everyone is expecting to feed through it?
I don't think so. Just because it's open source, right? It's not going to go away tomorrow. It's not going to become unmaintained tomorrow. I think the idea of WebAssembly, right? It's as low level as possible, but no lower. So that implies that the tool chains, before you get to the engine, are going to be doing a great deal of the optimization work. So if not Binarian, then everyone else would be having to do that work. So there would be some other optimizer tool, or each tool chain would independently have to write all the same optimizations. So I think we're actually in a much more sustainable world today where we can centralize and share all that work.
Great, thank you. I think that's a natural place to stop, so let's thank Thomas again. So now we get to the last part of the day, which is going to be lightning talks. So first, I think we have 3 people on the list, and I was thinking Arya could go first, if that's all right. Do you have your own laptop, or would you prefer to use mine? All right. Because we have 3 talks, we don't need to be so strict about time. These can be more like thunder talks. Could you hold this for a sec? I'll bring it back if it turns out that the laptop's not working. But don't feel hustled. I'm not going to drag you off if you go over 3 minutes.
Only the top right of my screen. Cool. Should I use this or does it matter? Just that pocket one right there. Hello? Oh, that's weird. Okay. Cool. So, hey everyone, I'm Arya. I'm from Edinburgh. This is, I think, the third formalization of WebAssembly that you've heard about today. So I'm going to skip over a lot of details, obviously. But there are two main differences to the existing ones in this version. The first is that it's intrinsically typed. So I think we touched on this a bit earlier. But rather than having a separate proof of each thing being well-typed, we just require that they are well-typed when we make the instructions. So it looks a lot like the spec. We're using different symbols, but in the context gamma, we can turn the stack delta into the stack delta plus a number on top, right? And rather than just storing indices into which label we want to break to, we need to provide a proof that the label exists and that the label has the type T, and then we constrain that if you want to use this instruction, you have to have type T at the top of your stack. And that works similarly for instruction sequences. We require that you line them up between each instruction so that you can actually execute the next instruction. The second difference, which is maybe more noticeable, is that we represent our configuration differently. So in the WebAssembly spec, you have the same stack, which is an abstract machine, I think it's called, and that contains your constants and your instructions and these special fake instructions that represent control flow. Here, we have a separate operand stack, and we have the instructions that we're executing currently. And this lets us more easily write restrictions. So here, because we have delta in the same places, this requires that for a configuration to even be constructed, to be valid, it has to have an operand stack that's ready to execute the next instruction. So our configuration will always have the stack in the right shape. And then whenever we have control flow, where the stack is going to empty out and then change, if we enter a control flow block, we add it to this frames data structure, and we save the current operand stack and the rest of the instruction sequence, the continuation, and then we constrain the next version of the configuration. Whatever new instruction sequence we're starting to execute, we have to finish with what we're continuing with, right? So again, I'm skipping over a lot of details. The rest of the the rest of the proofs are basically straightforward, defining your reduction rows, doing progress, which is especially straightforward because it's just what instruction comes next, right? The main thing to note is that obviously our reduction rows have to be different because this is not how they are written in the specification. They're a little bit uglier just because there are more fields that you have to deal with rather than just having everything in one place. Yeah, and because we're using a proof of progress, we get our evaluator for free. So this all gets figured out. It's not currently at the stage where we can instantiate modules, but it can evaluate things. So yeah, that's about all I had planned. I don't know how close I am to time, but if you want to talk to me about this, I'll be around after, or here's my email or my Fediverse, and yeah, thanks.
Great. And for our second speaker, let's have Marco. Oh, sorry. Actually, yes, questions first. Let's do just like 1 or 2 minutes for questions, so we'll try and be brief.
This isn't a question, this is a brag. People looking at this might think that Arya is a student and had a project where you put in hundreds of hours and so on, and this is the result of that project. What actually happened was Arya was a student in my class taught from my textbook, Programming Language Foundations in Agda, and there's a final project that's optional, which is there for students to show off if they can do something really good. And she went off and did this all on her own. I didn't say do WASM or anything. She just did it. and in a normal 10-unit course. So this is an amazing amount of work for an optional project in a 10-unit course, and I just want to point out what an amazing thing Ari achieved. And
a very quick question here. How long did it take?
No idea. If you count loading Agda, if you count loading Agda, it took a semester. So.
I think that's a natural place for us to rotate speakers. So thank you very much for speaking. Let's have Marco next. And I promise I did not deliberately do this. You'll see what I mean in a second.
Thanks. Yeah. Okay. So this is gonna be interesting. So so this project is mainly driven by two students that are working with me at Utrecht University. By the way, I'm Marco. I'm faculty at Utrecht University. So it's also about a intrinsically typed WASM. Basically, we are building a verified intrinsically typed WASM interpreter. So what is that? So that's an interpreter that operates on a well-typed intermediate representation. So that means that our syntax keeps track of all the invariants that all the types of the types of the things on the stack or the type of the function in scope of a module and whatnot. And why are we doing that? Well, like the question that we're asking ourselves is whether types can lead to shorter proofs. And Philippa, thankfully, I already answered that question today, I think. You found that the intrinsically typed interpreter, the intrinsically typed, verified interpreter was at a fewer lines of code than the extrinsically typed one. The other side is about execution. So Conrad's interpreter showed that there are a bunch of tricks that you can use to make this interpreter faster. And we are continuing on that line. So we are doing this in Lean, which is nice. I think we have all been playing with proof assistant, and I'm not aware of any interpreter written in Lean. So Lean is a proof assistant that provides good support for dependent types and statics as well. We are using typed de Bruijn indices. So these are basically proofs that, things are in scope and have the type that you expect. And the other trick that we are using, or at least we're experimenting with in the interpreter, is to use continuations. So whenever our interpreter reaches some control flow instruction, is going to build a continuation that will do something, do what the instruction is supposed to do with the things that it finds on the stack. So Lean can, Lean code can be executed efficiently. So Lean is a virtual machine implemented in C++. So we hope that compared to the type of code that you can get from other proof assistants, that would be faster. But there are some challenges with this intrinsically typed approach. So the fact that our intermediate representation is typed means that our runtime representation could have some of this information there. And this could cause unnecessarily overheads. So we're really interested in figuring out if we can completely get rid of these types at runtime. One thing in Lean that might help us here is that Lean has a special type for things that you can prove things about, a prop type. And these are guaranteed to be erased. So if we can map our dependent types into a prop, then Lean tell us this will be erased. So the way I see this project moving forward is that we'll have to figure out how to refine this dependent type into a prop type that then will be erased. So also, the main driving force here is Alex. He's a master's student at Utrecht University. And he started actually, even before this project, working with intrinsically typed representation. He built a interpreter in Haskell that is using GADTs and all sorts of type hackery. And now we're just carrying on this in the with Lean. So that's all I have. Thank you.
So I have an immediate question. When you're talking about intrinsically typed WASM, I'm taking that to mean that the definition of the WASM AST is intrinsically typed.
Yeah.
Do you ever expect to be able to erase those types, or are there different types you're talking about erasing?
No, I mean, like, I expect that, like, these types will be erased, yes. Or at least that's like, I mean, so like the way I see is that, yeah, like, this typed AST is like really good to do for doing proofs. I mean, you can get, I don't know, like preservation for free. Like parts of the interpreter, I think, do benefit from yeah, like this type information. And I don't know yet if we're gonna manage to completely eliminate that, but yeah, like that's our hope.
Because I would, just to follow up, essentially the way we managed to erase all of our dependent types was because almost naturally in Coq, you pack all of your dependent types into a separate prop that's entirely off to the side, and it seems harder to play that erasure trick if it's interleaved with the AST. That's more of a comment than a question.
Yeah, no, I mean, yeah.
Like, two questions. One is, how do you generate these ASTs? You have a parser that validates as it goes, or?
So currently we have a parser that validates as it goes. We're also like thinking, yeah, like if we can start with the untyped AST, such as one, I think, from the, what's it called, the WASM specification generators that we heard today. Sorry, I forgot
the reference interpreter.
Yes. So, but currently we type as we go, yeah.
And the other question is, like, with this much more complicated type system we have now with GC types, so where you have subtyping, recursive types, and stuff like that, will that affect the strategy somehow? Will that make it harder for you?
We don't know yet. Currently, we are still at WASM 1.0. We're making good progress, so that would be like a nice test to see if this can be extended further. One thing that would be actually cool to do, actually looking at GC types and whatnot, is to see if some of these optimizations that Binarian performs could be, we could validate them and show that they're well typed with this type syntax.
So this is really for the whole audience, not just to you. But basically, okay, there's this bullet to bite, which is intrinsic versus extrinsic, beauty versus direct on the language. What are we just got? Have we just got this bifurcation? So the gang over there is not going to work with the gang over there, and vice versa. Or what do we do about this? Because I will be very bored if I have to start answering questions about this again in another talk.
My personal dream, and maybe Sam's as well, is that WASM DSL can produce both extrinsically and intrinsically typed definitions of WASM. And then we can all hug and live in harmony.
And then what should the Coq mechanization do? Which one? Do it back and forth?
Well, you saw the quote on the slides. You're meant to forget Coq has dependent types, right? Any other questions?
It's called research, Philippa. Right? We don't know what the answer is yet, and this is a step towards finding out what the answer is, which is very interesting. I can tell you my one very preliminary result, which is that when I wrote PLFA, Programming Language Foundations in AGDA, I did it twice, once extrinsically and once intrinsically, and I found that the intrinsic code was the golden ratio smaller. So my slogan is that intrinsic typing is golden. On the other hand, if you try to do type theory itself intrinsically typed, the answer is no one knows how to do it yet and make it actually run in a system like Cubicle AGDA or what have you. I'm working with Torsten Alkirch and some others trying to figure out how to do this. So that's too hard for us to do now. It's a research question. So we will just, remains to be seen. It's very interesting to work this out, right? What is the best way to do it? We don't know what are the trade-offs. We're just learning. So there's much further to go, and it'll be interesting to see where we get to.
And is the same question there in the actual WASM language, or is it completely clear there that you want to be extrinsic?
Well, WASM wants to define the type system stuff.
Yeah. Sorry.
So the question was, we can ask this question in abstract. For WASM specifically, is there a clear answer that one's better than the other? For now, WASM very practically wants to define its type system against an untyped AST. So that's the thing that naively led us towards extrinsic typing. We weren't thinking at the depth that the researchers here are, so maybe they have something to tell us. Sam.
I was more or less going to say what Conrad said. So, I mean, I think this is a particularly interesting case to do some research in, because it's not your typical situation where you have just a statically typed term language where you're intrinsic all the way through. We need to be able to manipulate untyped code and validate it. And yeah, we can maybe make use of an intrinsic representation some of the time, but we have no choice but to deal with the untyped terms as well. So yeah, I think it's interesting.
But I mean, also one doesn't rule out the other. I mean, there is a correspondence between untyped, extrinsically typed and intrinsically typed. So I guess ideally you would like to get these transformations for free so that you can do the best task with the best representation.
Yeah, so then I declare the goal of WASM DSL is not just the untyped representation, not just the intrinsically typed representation, but the automatic derivation of conversion between them. We will definitely do this.
So actually, this is a question to both of the presenters so far. Did I open the mic?
Yeah. Sorry, I was trying to get over the camera.
Yes. So basically, I had some experience on the coq mechanization, and I was about to ask, when using the intrinsically typed approach, how what method did you come up with the initial typing derivation that you must fit into the initial interpreter? Because that was what I tried as well, and I think it has to be done via a type checker and plus some module instantiation typing results if you are starting from the module, or are you starting from the AST directly instead of the binaries?
Yeah, so as I mentioned before, we are currently doing type checking on the fly, which I guess has also drawbacks. One thing that we are actually considering doing is reusing the untyped AST automatically generated from the spec and basically type check that with an extrinsic or with an explicit type object, and then convert that into our typed representation. That would also be possible.
Any other questions or comments? I think that's a good place to stop then. So thank you very much.
Thank you.
And Maxime, I believe you're our third and not final speaker, because we also have Andreas.
Thank you so much. Thank you. Can I just stick the microphone? Yes, very quick. I love that, by the way.
Thank you so much.
Really good. Can you please put this onto your pencil? possibly not into the pocket. Yeah, exactly. No, like you can stick it onto the pocket, but not into. Perfect. Thank you.
Surely I need to plug in something. This thingy?
Yes.
Yes. It is now plugged in. Great, that is my screensaver.
Do you have an extended desktop rather than a mirrored?
Maybe. Perfect. So, hi everyone, my name is Maxime Le Goupil. I'm a PhD student with Lars Bjerkedal at Aarhus Universitet. I've now been working 2 years over there in Denmark. The first year before my PhD, I was a part of a group of incredibly talented people, Rao, Philippa, Conrad, who are here today, as well as Lars, Jean, and Aina from my home university in Aarhus, where we developed Iris WASM, which builds on the mechanization of WebAssembly in Coq and adds a whole program logic using the Iris proof framework that allows you to write proofs about specific WASM programs. These proofs are phrased in a typical separation logic language. So if I have this precondition, which is phrased as a conjunction of different resources, then this is going to run safely, and I'll have this postcondition with different resources when I'm done. And then if I then take this as a precondition, I can keep running, and I'll end up with a different postcondition in here. If we have a look here at my example, you can see I'm calling functions like stack push and stack pop. So I'm imagining here that I have a library that implements stacks. And one of the important things that we wanted to have in Iris WASM is great modularity, and we wanted to show how we can reason modularly between different WebAssembly modules. And the way it would work here is that the person who's implementing the stack module is going to write proofs using Iris WASM of the way their functions work. And because we're using Iris, which is a higher order logic framework, they have a huge recursivity to write their proofs in the way they want. They can do things like completely hide the implementation of the stack behind predicates like this is stack predicate over there. Instead of my resources being, well, the stack is in memory at that place, I can just say, well, there exists a predicate is stack that relates WebAssembly values with mathematical stacks. And then me as a client where of the stack module, I can write a proof of my code where I am calling a function from the stack module using Iris WASM and that specification of the stack module. I can show that I'm going from having a stack that represents having a value that represents mathematical stack S to something where I've pushed the value 2 onto my stack. And so I can combine specifications of one module and another to then reason about different modules interacting with one another. If we look at the second part of my example, here I'm calling an adversary function that I've imported over there. And I'm imagining that I know nothing of this function. And what I'd love to prove is that after this call has returned without giving me any value, if I now try to pop from my stack, because I've never shared the stack X with my adversary module, I now get something that is 2 as in the value that I had pushed before. How am I going to prove that? That's the last feature of Iris WASM, is that we've written a whole logical relation. That means that we're now able to reason about unknown code. All we need to know is that the code for this adversary function types well in WebAssembly's normal type system, and then we get to know that the behavior of that code is not going to do things that are forbidden. Now, of course, in plain WebAssembly, if I want this to be able to work, I need to make the extra assumption that my adversary code does not have access to the function from my from the stack module, because obviously, if it was able to pop, it would be able to just guess arguments for the pop function and simply just interact with the memory in that way. Because like Amal mentioned earlier, in plain WebAssembly, if I have a memory, it's all or nothing. I either decide to share it or not. And if an adversary module has access to these functions, it's going to be able to interact via calling these functions. Even though I haven't shared explicitly this value x, in plain WebAssembly, the way memory accesses work is by a use of i32 addresses, i32 integers interpreted as addresses, and that's something that is forgeable even if I don't decide to share it. This is where MS-WASM comes in. That was a proposition at last year's POPL where you would modify the semantics of WebAssembly to, instead of using i32 integers as addresses to access a heap memory, you would use handles to access memory in what we'd call a segment memory. So you'd have this form of enriched pointer that has metadata about exactly what areas of memory you were supposed to access. And that means that you can now share at a much finer grain because these objects are unforgeable, meaning that if I'm not explicitly sharing my variable x, an adversary module would not be able to have access to that value. And I can now share at a much finer grain. So what I've been doing now for the first year of my PhD is adapting IRIS-WASM to MS-WASM, meaning I have the full mechanization in Coq together with all the theorems we had proved that had been proved for plain WebAssembly, things like type safety via progress and preservation, partial determinism, as in determinism unless I'm doing, I'm using the few features that might introduce non-determinism. I have the full program logic that's going to allow me to prove proofs or theorems about the behavior of programs written in memory safe WASM, and I also have a logical relation that allows me to make proofs of robust safety in the presence of unknown code. These both projects so also allow us to reason about interaction of different modules, as I mentioned, but also interaction with the host, also reinferent interaction, and yeah, the hope is that now that we've introduced this tool, it's going to make the proposition of MS-WASM that was advanced last year at POPL much more precise and to show exactly what kind of guarantees we get from using handles in WebAssembly. Thank you.
Questions, please.
Thank you. So my first question, immediate question is going to be, are you going to, as I imagine, implement a different unforgeable pointer type that cannot be used to do pointer arithmetic? So so that's when you share those kind of pointers, the adversarial functions cannot use them to kind of figure out where your actual other address is.
Absolutely, that's exactly what MS-WASM does. So you introduce a fifth type to WebAssembly instead of just having I32, I64, F32, F34, 64. You now also have a handle type, which is a completely distinct object that is what you use to access memory. And then you have separate operations to allocate, deallocate these handles, perform some handle arithmetic. There are some restrictions on exactly what you're allowed to do, or actually you can do whatever, but once you've done it, you might not be able to use that handle anymore because the handle contains metadata about what exact parts of memory you were meant to have access to. So if you try to do, perform pointer arithmetics to now have something that points outside of the area that is specified by the metadata, any attempt to read or write is going to fail. And yeah, we suppose these objects to be unforgeable. That is achieved by adding an ID. And yeah.
Yes. So my next immediate question is going to be is there any mechanism here that say prevents you from or prevent the adversarial function from storing a copy to its own global memory to be used later because it can kind of duplicate the access you have given to the function?
Yeah, absolutely. That's a very good question there. So if you're interested, feel free to read the MS WASM paper from last year. They have a couple of subtleties that go with storing handles. You have to be a little careful how you implement that. But some mechanisms that are put in place are things like if you decide to free a memory, then the memories, if you decide to free a handle, the handle's ID now does not appear in the allocator anymore. So that means if someone else tries to use that handle, even though it's been deallocated, that is going to fail no matter where they got it from. So you still have mechanisms to deallocate the handle once you're done using it. But yeah.
So to give another piece of colour to MS WASM as well, one way to think about it, and the way I thought about it when I was participating in the work, was it's a way of exposing cherry-like capabilities to a WASM level. So the point about ensuring you don't go outside the bounds of memory is exactly the agenda of a cherry capability. And the question Rao was just referring to there is about capability revocation. So you can also find literature at the cherry level on how to implement that and how feasible it is, just to give people pointers to some other work that might be relevant here.
So I guess, given that stack example, it's a great example to then extend your MS WASM work. Is that sort of your first? Because we were always having trouble finding examples. So is that your first port of call, or do you have other examples that you're thinking of? This will be the first thing to be looking at.
So we're still in the early stages of writing examples in Iris MS WASM, but we have implemented the exact same stack example we had in Iris WASM in Iris MS WASM, and we're currently exploring what can we prove in Iris MS WASM that we could not prove in Iris WASM, and this kind of example is exactly what we're looking at. Because if you're simply in plain WASM, there are some things that you can prove, some invariants about the way the memory of the stack module is laid out that are going to remain true because anyone can only interact via the calls to push, pop, or all the other functions that the stack module exports. But nothing about the data because anyone can just push or pop anything by guessing addresses or providing whatever input to those functions.
So I guess just a sort of more general comment that whether it will be in Iris WASM or the Iris MS WASM, I imagine it's the same. There's this, it's difficult to find examples. And in particular, you know, there's tiny things. And then because it's compilation target, there's huge things. But actually, for these sorts of program logics, what is right sort of WASM code to be exploring? And we don't know whether we're too early or whether it's never going to be that you get the standard libraries at the WASM level, or where is the place to start looking for this generic code? I think that's,
yes,
if anyone can say it better than I just have to, but I think that's the big important code that you want to verify. Yeah, right.
We feel like probably a logical next step or a natural next step to this would be to try to automate a lot of this, because a lot of this can be automated. And when we've started doing that, then we can start actually working on examples that are much more realistic. But we've implemented the whole of WebAssembly 1.0, the whole of the industrial definition of the language is included in the mechanization, the program logic, the logical relation, both in plain WASM and in memory safe WASM. So we're hoping that we're going to soon be able to do much more scalable, large, realistic examples.
Okay, one more question. Oh, sorry. Well, I'm going to let Marco go because he's on it last.
Maybe an idea could be like if you have some, let's say, memory allocator that you implement in C, and you could possibly like think about compiling it to MS WASM, and then you could prove that the allocator doesn't screw up and break memory safety, and that could give like, you could basically formalize what the secure allocator is in MS WASM and use some kind of robust memory safety guarantees. I guess that could be like a good application of this.
Certainly, yeah.
Okay, let's thank the speaker one last time. now for our final Thunder talk, it's Andreas, who's going to be...
Too many things.
Oh, do you have one of the cursed ones that needs net out?
Yes.
You find it doesn't work.
Thank you. So one of the previous speakers had a Mac, right? So I kind of hope it will.
With a direct HDMI connection, we can try.
Oh, okay.
You may need to email us.
That would be difficult, but let's see.
Wow. You have a really long
How is it? Why is it? Okay. What happens if I present? Oh, it works. Okay. Right. So last thing, I try to make it quick. This is actually something Conrad suggested, since this keeps coming up, like WASM 1.0, WASM 2.0. What do we actually mean by talking about it? And most people, I realize, in this community still are kind of behind the curve, right? And even being based on the PLDI paper, a lot of work seems to be based on the PLDI paper still, which is like 7 years old now. So WASM 1.0 is kind of what you know from that paper. It's roughly the same thing. Some minor syntax changes, some minor refactorings in the formalization, but that's the thing you all know. But that was like, 2018 when we standardized that, right? So that's a done thing in the past. Since then, we have not been lazy. We have done a lot of work, actually. So WASM 2.0 was actually a minor step. So the things that were added there were just a couple. Multiple return values, they actually were already in the PLDI paper, so that's probably not new. The big thing that was added there was vector type and instructions. So not particularly structurally complicated, but huge surface and a lot of irregularity. So as Sukyung pointed out, that makes it a bit painful. And then the kind of semantically more interesting thing was that we added reference types as a completely new kind of thing of value, like really opaque things that you cannot store in memory because you must not be able to observe bit patterns. So that might be pointers to functions or pointers to host objects. And that is kind of like a precursor for like what we now working on with garbage collection, stuff like that. And then there were various instructions that make like things like memory copy more efficient. They are not, again, not semantically interesting. They're just like a performance improvement. So that is also done. That was basically 2 years ago, we kind of merged all this. So we have this notion of, like, you may not be aware of a live spec document now, which technically we still haven't really. Like, there's something with the W3C process that makes that very slow, but essentially you should think of the document being on GitHub.io/spec as being the current spec. And that has had these features for a long time, since like 2 years. Some of them even longer. Okay, but what we have been working like really towards is, I just phrase it as WASM 3.0 here. There is no real version number yet, but it's kind of like a nice way to phrase it. And that is starting to add more interesting features in terms of support for high-level languages, right? So what do I mean by that? So the first one is tail calls. The next one is taking the story with reference types further. So we now have like actually typed reference, so structurally typed references. You know what you're pointing to, like some function or some other thing. And you have a rich notion of subtyping and type recursion on that. So that really makes the type system much more like involved than it's currently. Currently, it's almost like trivial, right? You just have these 4 or 5 or 7 atomic types. And now it's like there's a lot of structure going on there. And based on that, the probably biggest feature we have added is garbage collection. So primitives to allocate something on an opaque heap. So a heap that is completely separate from the linear memory. In the browser, it will basically be the JavaScript heap, but that, like, you can't really observe that. There's some heap, and the only thing you can do with it is allocate on it. And you can allocate tuples and arrays, essentially. And then you have reference to these, and that's where all these typed references come in. Multiple memories, Amal talked about that, or mentioned them. So that is really just kind of a hole we closed in the initial design, which we left there very intentionally. So now you can have multiple memories in a single module. And that's all these are, I put check marks there because they're basically done, right? All these features are done and just have to be merged, which is on me. The other thing that has been in the making for a lot is the threads proposal, which should more accurately be called atomics, because it doesn't really add the ability to create threads, but it adds instructions for atomic access to memory. And it comes with the whole weak relaxed memory model and all the complexity of that. So this is also like a big addition to the semantics, at least. Another thing is that SIMD is now extended even further. So there's this couple of new instructions called relaxed SIMD, and that have this somewhat unfortunate property that they have implementation-dependent behavior. And the reason for that being that CPU vendors simply can't agree, can't get their act together to agree on or converge on the semantics. And at the same time, people pushing SIMD really want to have cutting-edge features for their performance things. So we kind of were pressured to put that in. And then two more things which are not quite done yet, but will probably also end up, hopefully, in the next version we cut, which is exception handling. So you saw some of that on Daniel's slides. So it's kind of more or less like if you really squint ML-style exceptions. So you define exception tags, and you can throw and you can catch. And the other thing is with memories. So there are multiple memories, but we also are extending the address space by giving you the ability to declare a memory to have a 64-bit index. And that gives you full 64-bit address space. So yeah, all the things with the check marks are basically done features. You should consider them standardized at this point, more or less. They are at phase 4 of our elaborate process. And the other two are almost there. I think we will reach definitely this year. And there's more going on after that. I'm not going to talk through all of that, but stack switching, Daniel talked about, and there will be continuations in one form or the other, either our proposal or some other variation. The sort of things of having shared state. So with atomics, you can just share memory between threads, but we want to generalize that to being allowed to share arbitrary references and globals and tables and functions between threads. So that adds some stuff to the type system, but also to the memory model, of course. And type imports, exports. Memory control is a bit vaguer at this point. There's this is the idea of having something like mprotect, maybe mmap, or some equivalent of that in the instruction set, because that keeps coming up. And there are more things I didn't talk about, smaller proposals that are in the making, but these are the big ones you should be aware of. And right, so if you want to follow that, there's this web page where they're all listed, and you can see what stage they're at and how they progress. And so keep an eye on that. And this is the link to the live standard, if you want. The spec, you should consider the current standard. And that is usually more further ahead than what the W3C has put out as its document. Okay, so this just was, supposed to be an update on what's actually going on, so you're prepared for what's coming your way in the future. Okay, thank you very much.
What's your favorite feature, Andreas?
The best features are the ones we don't have to put in. Tail calls is probably, because it's so simple in terms of semantics, but has a lot of bang to it.
So this one that you say is the live standard, is that the very current version you've got, or the 2.0 version, or which version is that, or is it several and they're labeled in some way?
So currently none of the 3.0 features I mentioned are merged in yet. So it's 2.0 plus some fixes. But I will soon start merging things, and then it will be some part of 3.0, and incrementally we get there. And these versions are really just when we do an official kind of step of cutting the current thing as an official standard with a W3C. I don't know if that answers your question.
Is there somewhere else that you look to see the 3.0 stuff that's not in this yet?
Mm-hmm. So, well, none of that is in there yet. I have to merge it, but all the ones with a check mark could be merged anytime soon.
Yeah, I'm just saying, is there a public GitHub where you can see these, or?
So I showed you the proposals link. So that has basically this one.
It's under that. Okay.
There are links. So each proposal basically is a fork of the repo, which with the entire spec with the specification of these features like added. And now we
have to merge them to get spec.
Yes.
Okay. A very different question. You mentioned exceptions, and then we've got the continuation stuff. Does the continuation stuff subsume the exception stuff, or are they slightly different, or?
Like Daniel showed, the continuation stuff builds upon the exceptions proposal a little bit, so we use the tag mechanism they have for exceptions. But other than that, so our original design actually started out as a generalization of the exception instruction set. But for performance reasons, you actually want to know when you have a throw or suspend point, whether you need to create a continuation or not, right? That is a big difference in terms of performance. So you really want to at least annotate everything with, are you in the exception world or in the continuation world? So it ends up being two separate sets of instructions and types anyway. So
and they're mainly separate because one is much more performant than the other.
Right. So when you do a try for an exception, you don't want to create a new stack for that, right? It's just something you mark in the current stack. When you have a continuation, so with our cont new instruction, that is really under the hood allocating a new stack from the operating system, which is a much more expensive operation. And when you resume or suspend in both directions, you're switching between stacks, right? Which you don't do with exceptions at all. So that's why it really makes sense on this level to keep them separate.
Okay, thanks.
Two things real quick. Just want to mention. So the exception handling has suffered a little bit from almost shipping the wrong thing. So we're kind of recovering from that.
Yeah.
I'm responsible for fixing that. But you didn't mention profiles. Maybe you want to say something about that for this crowd.
Oh yeah. So right. So one thing which isn't really a feature in a way, but kind of like a way to annotate the spec is that we are adding or introducing this idea of profile. So there are lots of features here, and we have to support lots of different environments, ecosystems, platforms, some of which may not be able to implement some of these things, right? So for example, if you're running WebAssembly on a blockchain, you probably can't support threads. There's no way you can have non-determinism there. If you're running in an embedded system, you may not be able to support SIMD or GC because it's just like you really want a tiny runtime or tiny system, things like that. And the idea is that we potentially add this notion of profiles, which allows to define subsets of the language that exclude certain features. So there's the full language, but you can form slices in that language that exclude certain features, and that will be profiled. And one important one particularly is the deterministic profile. So that rules out all non-deterministic behavior, which we already currently have with NANDs, and with relaxed SIMD, we're going to get much more of that. But if you're interested in actually well-defined semantics, you can say, okay, my environment's only running is implementing the deterministic profile, which removes some behaviors from the specification, from the semantics, essentially.
Have there been any visible adverse effects due to the increase in the scope of the language from 1.0 to 3.0? Like, for instance, has it entrenched existing implementations or existing runtimes because it's harder to include all the new features in a new one?
Yeah, I mean, it's certainly the case that there have been a lot of kind of smallish toy implementations initially, which are not really maintained, and they're definitely falling behind, and they're not maintained. I mean, they would probably fall behind anyway. Yeah. But of course, it makes it harder for like developing a new implementation of WebAssembly. And there are currently like a dozen different ones, like the 3 major web engines, but also quite a few ones outside the web. And I don't know how many of those will like survive in the long term, because it might become too much of a burden to follow all these things. On the other hand, I also think that like the list of features I showed you here is probably like kind of a feature hump we are now getting over. It's all the kind of things we already wanted to do when we put out WebAssembly 1.0, when we designed it initially, but kind of consciously deferred because, yeah, we need to get something out quick. And now we are finally kind of, all these features are done and we can merge them in. And then after that, I would hope or expect there's a bit more of a long tail of other things following, but I hope it will not continue with that velocity.
Okay, thanks.
I think we're way over time anyway.
Yeah, that's a good place to stop. Thank you, Andreas. So I'll just end very quickly by saying thank you all for coming again to our inaugural WebAssembly workshop. If you have any comments about ways you think we should do this differently, or things you liked, or things you think we should change next time, please let me or Andreas know on Discord, by email, anything you'd like. But just apart from that, thanks again for coming, and please come back next year if we do this again.
Thank you, Conrad and Andreas, for organizing.
I have to say, Conrad did